The universe we inhabit is far from ordinary. Its mysteries stretch beyond the confines of our current understanding, pushing the boundaries of human knowledge and imagination. Each new discovery about the cosmos challenges our deepest assumptions, revealing a reality far stranger and more complex than we ever dreamed. Black holes, for example, are not mere astronomical oddities. These enigmatic objects warp the very fabric of space and time, creating regions where the laws of physics seem to break down. Dark matter, an invisible force that shapes galaxies, remains undetected by our instruments, yet its presence is undeniable. Even more bewildering is dark energy, a mysterious force driving the universe's accelerating expansion. Though it makes up the majority of the cosmos, we barely grasp its true nature. These are not mere speculative ideas, they are fundamental components of our universe, confirmed through rigorous observation and testing. Stars, for instance, collapse into singularities, the point of no return, where all the known rules of physics cease to apply. Quantum particles behave in ways that defy classical laws, appearing in multiple states at once, or even influencing one another over vast distances. Time, too, is not a universal constant. It flows differently depending on the strength of gravity or the velocity at which an object moves. Are we alone in this vast expanse? Could there be parallel universes lying just beyond our grasp? What exists beyond the edge of what we can observe? These profound questions touch upon the origins of the universe itself, a topic that has fascinated scientists, philosophers, and curious minds for centuries. Among the many theories proposed to explain the universe's birth, one of the most widely accepted is the Big Bang theory. This theory suggests that, at the very beginning, the universe was an infinitesimally small, hot, and dense point, an idea so bizarre that it challenges our very concept of space and time. Imagine a balloon so small it could fit in the palm of your hand. Now, picture it suddenly expanding, growing exponentially, and you have an inkling of how the universe began its rapid and violent expansion. This expansion, the theory suggests, created all the space, time, and matter that we see today. In those initial moments of the universe's existence, everything was chaos. Extremely hot, incredibly dense, and incomprehensibly violent. Yet, as the universe continued to expand, it began to cool, allowing particles to form. These particles eventually came together under the influence of gravity, and over millions of years, they combined to create atoms. From these atoms, stars and galaxies slowly emerged, marking the first steps in the universe's ongoing evolution. The Big Bang theory offers a remarkable explanation not only for the universe's initial explosion, but also for its continuing expansion. Observations show that galaxies are still moving away from us, suggesting that space itself is stretching even now. This movement, observed as redshift, the stretching of light from distant galaxies, further supports the idea that the universe has been expanding since its inception. It is as though the universe itself is slowly but surely stretching apart, a phenomenon that confirms the explosive beginnings of our cosmos. Furthermore, scientists have detected a faint, pervasive glow that fills the universe, cosmic microwave background radiation. This afterglow of the Big Bang, still traveling through space after billions of years, is the most direct evidence of the universe's fiery birth. It provides a glimpse into the universe's earliest moments, confirming the theory's predictions about the state of the cosmos right after the explosion. The theory of cosmic inflation, an integral part of the Big Bang model, proposes that just after the Big Bang, the universe underwent an incredibly rapid, exponential expansion. In a fraction of a second, the universe grew to a size far larger than we can easily conceptualize. This sudden burst of expansion helps explain why the universe appears so uniform today, why no matter where we look, the cosmic microwave background radiation looks the same in all directions. Despite its compelling nature, the Big Bang theory is not without controversy. One of the key debates revolves around the very first moments of the universe's existence, those earliest instants that remain hidden from direct observation. What happened in that first fraction of time when the universe was so small and dense that traditional laws of physics break down? Some scientists question whether we can ever fully understand the precise events of the Big Bang. Moreover, the theory of cosmic inflation, while helpful in explaining some phenomena, has raised its own set of questions. The rapid expansion it suggests would require a very specific set of conditions, some of which remain unsupported by current observations. While the idea of inflation helps account for the uniformity of the cosmos, the lack of direct evidence has led to the exploration of alternative theories. At the same time, the mysterious nature of dark matter and dark energy adds further complexity to our understanding of the universe's origins. We know they exist because of their gravitational effects on visible matter, but we cannot directly detect them. Dark matter, which affects the motion of galaxies, and dark energy, which accelerates the expansion of the universe, represent some of the greatest unsolved puzzles in modern physics. Their elusive nature makes them difficult to study, and this uncertainty casts doubt on whether the Big Bang theory as currently understood can provide a complete picture of the cosmos. Philosophical questions also abound. What does the Big Bang mean for our understanding of time, causality, and the very nature of existence? If everything began with the Big Bang, what existed before it? Can time itself have a beginning, or is the universe part of an infinite cycle of birth and rebirth? These questions blend science with deep existential inquiry. Turning the Big Bang theory into more than just a scientific model, it becomes a platform for profound debates about the nature of reality itself. One particularly intriguing idea that has emerged is the concept of multiple Big Bangs. Could the universe we know be just one in a series of cosmic cycles, each one beginning with its own Big Bang and ending in a cosmic collapse, only to start again? Imagine the universe as a series of bubbles in a vast ocean, each one representing a different universe, each born from its own Big Bang, only to eventually be destroyed and reborn. This model suggests that our universe is not a singular event, but part of a much larger, repeating cycle, a never-ending series of cosmic rebirths. If this idea is true, it could imply the existence of a multiverse, an interconnected or separate collection of universes, each with its own unique laws of physics, structures, and histories. The implications of such a concept are mind-boggling. It would mean that the universe we call home is just one chapter in an infinite cosmic story, each chapter beginning and ending in its own way. Our universe, with its vast galaxies, stars, and black holes, could simply be one of many existing within a larger, incomprehensible multiverse. The search for answers to these questions continues, driven by ongoing research, new observations, and the ever-deepening mystery of the cosmos. Every discovery takes us one step closer to understanding the vast, intricate dance of creation and destruction that shapes the universe. And while we may not have all the answers, the questions themselves push us to keep looking, to keep exploring, and to keep wondering. What is out there, beyond the edge of our current knowledge, waiting to be discovered? The exploration of the universe's origins has long been a subject of fascination, with concepts like the Big Bang theory providing an essential framework for understanding the vast cosmos. However, this framework may be more complex than originally thought. New theories suggest that time and space might not always follow a linear progression, but could instead move in cyclical patterns. Imagine, for a moment, the possibility of multiple Big Bangs, not just a singular event that set everything in motion, but rather a grand cycle of creation, destruction, and rebirth. Such an idea would profoundly alter how we understand the universe, urging us to reconsider the nature of reality itself. For instance, certain phenomena we observe today, like the uniformity of cosmic background radiation or the distribution of galaxies, could be better explained by the existence of repeated Big Bang events. This insight opens the door to a broader cosmic saga, one that stretches beyond our current comprehension and challenges the very foundation of what we know about existence. Central to this expanded understanding is cosmic inflation theory. This theory adds another layer of complexity to the Big Bang model by offering solutions to questions that the original theory could not fully address. The Big Bang describes the universe's beginning as a point of extreme density and heat, followed by an immediate, rapid expansion. However, it left certain questions unanswered. Why is the universe so remarkably uniform across vast distances? Why do regions of space, seemingly separated by enormous expanses, share similar properties despite no direct communication between them? Inflation theory proposes a brief but incredibly rapid period of expansion that occurred immediately after the Big Bang. To illustrate, imagine inflating a balloon. Initially, the rubber stretches slowly, but as air fills the balloon, it rapidly expands. Similarly, in the early moments of the universe, expansion happened at a speed far greater than the speed of light, smoothing out any irregularities and establishing a more uniform universe. This period of inflation also helps explain the tiny temperature fluctuations seen in the cosmic microwave background radiation, the faint afterglow of the Big Bang. These fluctuations, although minuscule, were crucial in shaping the large-scale structure of the universe, giving rise to galaxies, stars, and clusters. Without inflation, such patterns would be almost impossible to reconcile, as regions that were separated during the early universe could not have had any influence on one another. Thus, while the Big Bang Theory gives us the universe's origin, cosmic inflation bridges the gap, explaining its uniformity and vastness, highlighting a dynamic and evolving cosmos that has been shaped by processes starting just moments after its birth. At the very heart of understanding the universe's beginnings is quantum mechanics, the theory that governs the behavior of particles at the smallest scales, such as atoms and subatomic particles. When contemplating the origins of the cosmos, quantum mechanics takes on a crucial role, particularly during the earliest moments of time, the Big Bang itself. Under conditions of extreme heat and density, the classical laws of physics begin to break down, and quantum mechanics becomes essential for understanding what happened in those first moments. In this realm, particles can exist in multiple states simultaneously, and they exhibit dual characteristics of both waves and particles. This strange behavior introduces an element of randomness and uncertainty, creating fluctuations in energy that play a pivotal role in the formation of the universe. These fluctuations, though tiny, created variations in the density of the cosmos, which in turn acted as seeds for the formation of galaxies, stars, and other large-scale structures. Without these quantum fluctuations, it would be difficult to explain how a uniform universe could evolve into the vast and varied cosmos we observe today. Moreover, quantum mechanics also introduces the concept of the quantum vacuum, not an empty space, but one that is teeming with potential energy. This vacuum can spontaneously generate particles in a process known as quantum fluctuation. Some scientists believe that these fluctuations played a significant role in the rapid expansion of the universe during the inflationary period. Without the influence of quantum mechanics, the universe's vastness and complexity would be much harder to explain. When we look back at the history of human thought, we see that various cultures and civilizations have developed their own unique stories about the origin of the universe. These ancient myths and beliefs often reflect the values and perspectives of the societies that created them, blending spirituality with attempts to understand the mysteries of existence. In many indigenous cultures, the creation of the universe is intertwined with a deep connection to nature. Earth and the cosmos are seen as interconnected, with powerful beings or spirits guiding the process of creation. These stories often emphasize balance and harmony, reflecting a worldview where creation is an ongoing, cyclical act rather than a one-time event. In ancient Mesopotamia, for example, myths describe a chaotic void from which gods emerged, bringing order to the universe. The Sumerians spoke of freshwater seas mixing with saltwater, giving birth to life and shaping the heavens and the earth. This imagery captures the eternal tension between chaos and order, a theme that resonates deeply in humanity's quest to understand the world. In contrast, Hindu cosmology presents a cyclical vision of the universe. Rather than seeing the cosmos as a one-time event, it envisions an ongoing process of creation, preservation, and destruction. The universe is said to emerge from a cosmic ocean, with a divine being awakening to initiate the cycle. This eternal dance of expansion and contraction highlights the belief that beginnings are not absolute, but part of an ongoing process of renewal. The ancient Greeks, on the other hand, contributed to philosophical thought on existence and the material world. Thinkers like Plato proposed the existence of a realm of perfect forms, sparking debates about the nature of reality and its origins. These discussions laid the foundation for Western philosophy, shaping the intellectual landscape for millennia. In many indigenous African traditions, creation is often tied to the spoken word. A high god, through language, brings the world into existence. a concept that underscores the power of communication and the divine connection between speech and creation. These creation myths often contain moral lessons, emphasizing the importance of community and respect for nature. Each of these creation stories brings a unique perspective to the table, offering insight into how different cultures view the cosmos and their place within it. While modern science provides a more precise framework for understanding the universe's origins, these ancient stories remind us of the diversity of thought that has shaped humanity's understanding of existence. One of the most profound mysteries in our exploration of the universe is the existence of dark matter. This elusive substance makes up about 26% of the universe, yet it remains largely invisible. Imagine being in a room so dark you can barely see anything, but you can sense that it's full. You know something is there, but you can't touch it or interact with it in a traditional sense. Dark matter behaves in a similar way. Though it cannot be observed directly, its gravitational effects on visible matter, like stars and galaxies, reveal its presence. Despite its invisibility, dark matter is believed to play a key role in shaping the structure and evolution of the cosmos. It helps explain why galaxies spin faster than expected based on the visible matter we can detect. Essentially, dark matter acts as an invisible scaffolding, exerting a gravitational pull that keeps galaxies intact and influences how they form and cluster together. Without dark matter, the universe as we know it would be unrecognizable, with galaxies and stars failing to maintain their shape and structure. Though scientists cannot directly detect dark matter, its gravitational influence on visible objects provides the primary evidence for its existence. The search for dark matter remains one of the most exciting and challenging endeavors in modern astrophysics. Understanding its true nature could unlock secrets of the universe's history, offering new insights into the forces that govern the cosmos. In the end, the quest to understand the universe's origins is ongoing. Whether through scientific theories like cosmic inflation and quantum mechanics, or through the rich tapestry of ancient creation stories, humanity continues to search for answers about the nature of existence. Each discovery brings us one step closer to unlocking the mysteries of the cosmos, yet there remains so much more to explore. Vast, mysterious, and full of potential waiting to be understood. The universe, vast and unfathomable, is a realm of constant mystery, where invisible forces shape the cosmos in ways that we are only beginning to understand. Among the most puzzling phenomena that scientists are investigating today is the enigmatic substance known as dark matter. This elusive material does not emit, absorb, or reflect any form of electromagnetic radiation, making it completely invisible to our most powerful telescopes. Despite its invisibility, dark matter is believed to make up approximately 85% of the total mass in the universe, affecting galaxies, galaxy clusters, and even the very fabric of space itself. The first step in unraveling the mystery of dark matter came through its gravitational influence on visible matter. Astronomers noticed that galaxies were behaving in ways that could not be explained by the gravitational effects of visible matter alone. Take, for example, a galaxy cluster, a collection of hundreds or even thousands of galaxies bound together by gravity. According to the laws of physics, the galaxies within these clusters should move at much slower speeds, given the visible mass present. However, scientists observed something startling. These galaxies were moving far faster than expected, and the amount of visible mass in these clusters could not account for their observed velocities. This discrepancy pointed to the presence of an invisible force, dark matter, exerting additional gravitational pull, holding the galaxies together and preventing them from flying apart due to their high speeds. In addition to this gravitational clue, scientists have also turned to a technique called gravitational lensing to study dark matter. This phenomenon occurs when light from a distant galaxy passes near a massive object, like a galaxy cluster, and is bent by the object's gravitational field. The bending of light causes the distant galaxy to appear distorted, creating multiple images or even a ring-like structure. By studying these distortions, astronomers can infer the distribution and quantity of dark matter in the foreground galaxy cluster, even though the dark matter itself remains invisible. It is as though dark matter is casting a shadow on the light of distant galaxies, providing scientists with another means to measure its presence and properties. Yet another approach scientists are using to detect dark matter involves underground laboratories where they employ highly sensitive detectors designed to spot the faintest interactions between dark matter particles and regular matter. These detectors are buried deep underground to shield them from cosmic rays and other forms of background radiation that could obscure the signals scientists are trying to detect. The goal is to capture rare collisions between dark matter particles and the atoms of the detector, which might provide the first direct evidence of dark matter. While these experiments have yet to yield definitive results, they represent a critical frontier in the search for the elusive substance. Despite the fact that dark matter has never been directly observed, its presence is inferred through its extraordinary effects on the structure and behavior of the universe. It serves as a cosmic glue, holding galaxies and clusters of galaxies together, and shaping the very structure of the universe. It is a testament to the ingenuity of scientific methods that, although dark matter remains hidden from direct observation, we are able to study it through the profound influence it has on the cosmos. If dark matter were ever to be proven non-existent, it would have profound implications for our understanding of the universe. All of our current models, which are based on the assumption that dark matter exists, would have to be completely rethought. The existence of dark matter was proposed to explain several unexplained phenomena, including the way galaxies rotate and the gravitational effects observed in galaxy clusters. Without dark matter, these observed behaviors would contradict the known laws of physics. If dark matter is removed from the equation, scientists would need to reconsider the fundamental principles governing the universe. This could involve developing new theories of gravity or reworking the very laws of motion that govern celestial bodies. The current models of galaxy formation and behavior are built upon the premise that dark matter exists, so its absence would force researchers to rethink the basic structure of the cosmos. In such a scenario, scientists might turn to alternative theories, such as modified gravity, which propose adjustments to the laws of motion and gravity to account for the observed phenomena. This shift could spark a new era of scientific exploration, with numerous experiments designed to test these new frameworks and challenge our understanding of the universe. The implications of disproving dark matter would reach far beyond theoretical physics. It could alter our understanding of the composition of the universe and its history. It would open up a Pandora's box of questions about the fundamental forces that govern the cosmos, propelling scientists to explore new ideas and challenge the very fabric of reality itself. In parallel to the quest for understanding dark matter, another mysterious force known as dark energy plays a critical role in the evolution of the universe. While dark matter works as an invisible glue that holds galaxies and clusters together, dark energy is a force that is causing the universe to expand at an accelerating rate. Imagine the universe as a balloon being inflated. As air fills the balloon, the surface stretches and the points on it move farther apart. Similarly, the universe is expanding and galaxies are moving away from each other. But while gravity is trying to pull everything back together, dark energy is acting like an anti-gravity force, pushing everything apart. This dynamic has led scientists to postulate that dark energy accounts for roughly 70% of the total energy in the universe, yet its true nature remains a profound mystery. The discovery of dark energy was one of the most surprising and groundbreaking revelations in modern cosmology. Observations of distant supernovae in the late 1990s revealed that rather than slowing down over time, the expansion of the universe was actually speeding up. This was a stark contrast to previous expectations, as gravity should have been decelerating the expansion. The realization that some unknown force was accelerating the expansion led to the hypothesis of dark energy. However, despite its dominant presence, scientists have never been able to directly detect dark energy. Instead, its existence is inferred from its impact on the large-scale structure of the universe and the way galaxies and clusters behave. Understanding dark energy is crucial for understanding the future of the universe. If dark energy continues to dominate, the universe could expand indefinitely, leading to a scenario known as the Big Freeze, where galaxies drift farther apart, stars burn out, and the universe becomes a cold, dark place. Alternatively, if other forces counteract dark energy, the universe could evolve in a very different direction, potentially leading to a big crunch or some other cosmic fate. The true nature of dark energy remains one of the greatest mysteries in science, and many theories attempt to explain it. Some suggest that dark energy is related to the vacuum of space itself, while others propose entirely new forms of physics that could account for the force. The search for answers to the questions posed by dark matter and dark energy is a journey that captivates scientists and stirs the imagination of anyone curious about the cosmos. These two forces, working in tandem yet in opposition, hold the key to understanding the very structure, behavior, and fate of the universe. As we push the boundaries of our knowledge, we continue to unravel the deepest mysteries of existence, uncovering new truths that challenge our understanding of the universe and the forces that shape it. However, around the halfway point in the universe's life, something remarkable occurred. The balance that had existed between the forces of gravity and the expansion of the cosmos began to shift. Dark energy, a mysterious and largely incomprehensible force, began to assert itself more forcefully, eventually becoming the dominant influence on the universe's expansion. Despite extensive study, no one fully understands the nature of dark energy. What is clear, however, is that it operates in stark contrast to gravity. Rather than drawing objects together, as gravity does, dark energy pushes them apart. This unseen force seems to have a singular purpose: to accelerate the universe's expansion. As time passes, the rate of expansion continues to increase, an effect that scientists have termed the accelerated expansion of the universe. It is as though the universe, instead of gradually slowing down due to the gravitational forces pulling everything inward, is being propelled forward at increasing speed by this enigmatic energy. Dark energy is integral to our understanding of the cosmos's fate, suggesting that the universe will continue to stretch, expanding farther and faster with each passing moment. The hunt to understand dark energy has taken scientists on a journey as perplexing as it is exciting. Researchers employ a range of innovative techniques to uncover its secrets. One of the key methods for studying dark energy involves observing distant supernovae, explosive events marking the death of stars. These stellar explosions, incredibly bright and visible from vast distances, provide valuable clues about the universe's expansion. By analyzing how these supernovae appear from Earth, scientists can deduce how far away they are and how fast they are receding from us, which in turn helps to infer the role dark energy plays in this cosmic expansion. In addition, scientists have launched large-scale galaxy surveys, mapping the vast expanse of galaxies across the night sky. These surveys allow researchers to measure the distribution and movement of galaxies over enormous distances. As galaxies cluster together or drift apart, understanding their patterns gives important insight into the influence of dark energy on galactic formation, motion, and the overall structure of the universe. Another valuable tool in the study of dark energy is the cosmic microwave background radiation, the faint afterglow left over from the Big Bang. Tiny fluctuations in this radiation provide a window into the universe's infancy, offering glimpses of how dark energy might have shaped the early cosmos. Furthermore, the detection of gravitational waves, ripples in the fabric of space-time caused by massive cosmic events, adds another layer of understanding. By studying these waves and their sources, scientists can gain deeper insight into how dark energy interacts with the universe. Lastly, the power of computer simulations plays a crucial role. By running simulations that recreate the universe's expansion under various conditions, researchers can test different models of dark energy, refining their understanding of its properties and how it might influence the cosmos in the future. With all of these methods combined, scientists are slowly piecing together the mystery of dark energy, uncovering its profound impact on the universe. If we were to ever unlock the true nature of dark energy and its equally elusive counterpart, dark matter, the implications for our understanding of the universe would be nothing short of revolutionary. Currently, dark matter accounts for a significant portion of the universe's mass. Though it cannot be seen directly, scientists know of its existence by how it exerts a gravitational influence on its surroundings. It behaves as an invisible glue, binding galaxies together and governing their motions through its gravitational pull. Understanding what dark matter is could radically transform our comprehension of the cosmos, offering insights into the formation and evolution of galaxies over billions of years. Dark energy, however, is even more enigmatic. This force is responsible for the accelerated expansion of the universe, driving galaxies away from each other at an ever-increasing pace. If we could decipher the mechanics of dark energy, it might unlock the answers to some of the deepest questions in cosmology. Why is the universe expanding at such a rapid rate? Will this expansion continue forever, or could it someday reverse? These profound questions could one day be answered, reshaping our understanding of the universe's future and the laws of physics that govern it. Moreover, the discovery of dark energy's true nature would have far-reaching consequences for our current theories of physics. It could potentially offer a bridge between some of the most fundamental and mysterious forces of nature: gravity, quantum mechanics, and the fundamental particles of the universe. By unlocking the secrets of dark energy and dark matter, we might not only refine our existing models of the universe, but also trigger a revolution in our understanding of existence itself, opening the door to groundbreaking discoveries in both cosmology and particle physics. Black holes, with their mysterious and extreme properties, are another area of cosmic study that continues to fascinate scientists and laypeople alike. These cosmic giants have gravitational forces so intense that nothing can escape them, not even light itself. But how do black holes form? To understand that, we must first consider the life cycle of a massive star. Stars, the building blocks of galaxies, are born from massive clouds of gas and dust. As these clouds collapse under their own gravity, nuclear fusion begins, converting hydrogen into helium and releasing vast amounts of energy. This energy acts as a counterforce to gravity, preventing the star from collapsing further. However, when a star exhausts its fuel, the balance between the outward pressure from fusion and the inward pull of gravity is broken. The core of the star begins to collapse under the immense force of gravity, leading to a violent explosion, a supernova. The outer layers of the star are ejected into space, while the core remains behind. If the remaining core is massive enough, typically several times the mass of our sun, it will continue to collapse under its own weight, becoming denser and denser. Eventually, it reaches a point of infinite density, a singularity, surrounded by a boundary known as the event horizon. This boundary marks the point of no return. Once an object crosses the event horizon, it cannot escape the black hole's gravitational pull, no matter how fast it travels. Black holes can also form in other ways, such as when two neutron stars collide, or when enormous amounts of gas and dust accumulate in a specific region of space, compressing under gravity. Once formed, black holes can continue to grow by merging with other black holes, or by accreting matter from surrounding stars, gas, and dust, and making them even more massive over time. Black holes present a significant challenge to our understanding of physics, as they represent a collision between two fundamental theories: general relativity and quantum mechanics. General relativity, formulated by Albert Einstein, explains how gravity works on large scales, such as with planets, stars, and galaxies. It shows that massive objects like black holes warp the fabric of space-time around them, creating extreme gravitational forces that even light cannot escape. On the other hand, quantum mechanics governs the behavior of particles at the smallest scales, dealing with the fundamental forces and the interactions between particles. At the heart of a black hole lies the singularity, where the laws of physics as we know them seem to break down. The gravitational forces here are so intense that space and time themselves become distorted. This raises profound questions about what happens to matter and information when it crosses the event horizon. According to quantum mechanics, information cannot be destroyed. Yet, once something falls into a black hole, it appears that all information about it is lost. This creates a paradox, the black hole information paradox, pushing scientists to explore new theories that might unify general relativity with quantum mechanics, such as quantum gravity. In understanding black holes, we are delving into the very nature of reality itself. These enigmatic objects are the key to unlocking a deeper understanding of time, space, and the fundamental forces that shape the universe. By studying black holes, we may one day uncover new laws of physics that could reshape everything we know about the cosmos. The event horizon, the boundary surrounding a black hole, is one of the most fascinating and mysterious features of these objects. It represents the point of no return, where the black hole's gravitational pull becomes so powerful that not even light can escape. It is often likened to the edge of a cliff. Once crossed, there is no going back. The event horizon is crucial because it defines the size and shape of a black hole. It is the boundary where the black hole's intense gravitational effects start to dominate, bending the fabric of space-time itself. For an outside observer, any object crossing the event horizon appears to freeze in time, gradually becoming more and more stretched out as it gets closer to the boundary. This is due to the way gravity distorts both space and time. In a sense, objects crossing the event horizon appear to slow down in time, even as they disappear from view. This phenomenon provides a glimpse into the strange, warped nature of reality around black holes and the forces that govern them. The study of the event horizon is key to unlocking the mysteries of black holes, offering a window into the most extreme environments in the universe. Through this, we may gain insights into the very nature of time, space, and the fundamental laws of physics, changing our understanding of the universe forever. Moreover, the event horizon of a black hole holds a pivotal position in the exploration of information theory and the fundamental laws of physics. It raises profound questions about the nature of information in our universe. Specifically, if an object or particle falls into a black hole, does its information vanish completely, or is it preserved in some way? This question touches on the deepest layers of quantum mechanics and challenges our understanding of reality itself. Consequently, the event horizon is far more than just a boundary. It is a key player in the cosmic drama unfolding in our universe, forcing us to reconsider our concepts of time, space, and even knowledge. The study of black holes offers unparalleled insights into the workings of the cosmos. To begin with, black holes function as extreme laboratories that push the limits of our understanding of physics. In these regions of space, the force of gravity is so intense that not even light can escape. This extraordinary characteristic allows scientists to explore the outermost boundaries of our physical theories, particularly those of gravity and relativity. Observing how black holes interact with their surroundings, whether through gravitational forces or the behavior of nearby objects, provides us with crucial data. For example, as matter is drawn toward a black hole, it spirals inwards, heats up, and emits powerful radiation. This radiation not only reveals the black hole's properties, such as its mass and spin, but it also offers critical clues about the dynamics of galaxies and their ongoing evolution. Furthermore, black holes are intricately connected to the larger-scale cosmic events that govern the universe. One such event is the collision of two black holes, which generates ripples in the fabric of space-time, ripples known as gravitational waves. The detection of these waves has opened a new frontier in astronomical observation, allowing us to study previously invisible phenomena. In addition to their role in gravitational waves, black holes are intimately linked to the mystery of dark matter and dark energy. These elusive forces, which account for the majority of the universe's mass and energy, remain some of the greatest unknowns in modern physics. By studying the effects black holes have on their environment, scientists hope to unlock some of the secrets behind the forces that drive the accelerating expansion of the universe. Black holes are far from being mere voids or endpoints in the cosmos. They are key players in shaping the very structure and evolution of the universe. The study of these cosmic objects is helping us answer fundamental questions about the universe's origins, its structure, and its ultimate fate. At the core of every black hole lies a singularity, a point of infinite density where gravity is so intense that space-time itself becomes infinitely warped. This concept of singularity challenges our very understanding of the universe. As matter collapses inward toward this point, the gravitational forces become overwhelming, and at the very heart of it, predictions suggest that density becomes infinite. Space-time curves beyond comprehension, and conventional physics breaks down entirely. This is where current theories of physics, particularly general relativity, reach their limits. General relativity, which has been remarkably successful in describing large-scale cosmic phenomena, fails to explain the extreme conditions present within a black hole. As such, scientists face a paradox. General relativity and quantum mechanics, which governs the behavior of the smallest particles, seem to be at odds when it comes to black holes. This contradiction raises fundamental questions about the nature of reality itself, and scientists are currently searching for a unified theory that could reconcile these differences. However, no such theory has been discovered yet, leaving us on the edge of an exciting frontier in the quest for new physics. Perhaps one of the most intriguing aspects of black holes is their relationship with information. When matter falls into a black hole, it appears to disappear completely, raising the age-old question: is the information contained within that matter lost forever? This so-called information paradox has been the subject of much debate among physicists. Some theories suggest that information might be encoded on the event horizon, the boundary surrounding the black hole, and thus preserved in some way. Yet, this theory remains unproven, and the question of whether information can truly be lost continues to divide the scientific community. The idea of the singularity and the role it plays in black holes forces us to rethink our understanding of space, time, and existence itself. As research progresses, singularities in black holes might hold the key to unlocking some of the most profound secrets of the universe. They challenge our notions of the cosmos and may lead us to discover new laws of physics, revolutionizing our understanding of the nature of reality. Black holes are not just elusive, enigmatic objects hidden in the depths of space. They are critical to the very structure of galaxies. There are two main types of black holes that influence galactic evolution: stellar black holes and supermassive black holes. Stellar black holes form from the remnants of massive stars after they undergo supernova explosions, while supermassive black holes reside at the centers of most galaxies, including our own Milky Way. The mass of these supermassive black holes can be millions or even billions of times that of the Sun. The presence of a supermassive black hole profoundly affects the galaxy it inhabits. One of its most significant impacts is on the movement of stars and gas within the galaxy. As material spirals toward the black hole, it generates immense amounts of energy, emitting powerful radiation and jets that can travel far beyond the galaxy itself. This activity can have a substantial impact on the surrounding environment, heating up gas and dust, which in turn influences the process of star formation. In some cases, the black hole's gravitational pull and energetic outbursts can either stabilize or destabilize the galaxy's structure, affecting how new stars are born and how existing stars evolve over time. Beyond star formation, black holes also play a crucial role in maintaining the overall dynamics of galaxies. Their gravitational pull anchors clusters of stars in stable orbits, thus preserving the galaxy's shape. However, the interactions between the black hole and its surrounding stars can lead to some dramatic effects. Some stars may be pulled closer to the black hole, while others might be ejected entirely, flung out into the vast emptiness of space. These dynamic processes contribute to the evolution of the galaxy and provide valuable clues about how galaxies form and change over time. In this way, black holes are not passive objects. They are active participants in the cosmic dance that shapes the universe. Through their influence on galactic formation, their interactions with surrounding matter, and their ability to challenge our understanding of physics, black holes remain one of the most fascinating and mysterious phenomena in the cosmos. Every new discovery about these enigmatic objects brings us one step closer to understanding the true nature of the universe. The process of black hole formation and their growth is deeply intertwined with the evolution of galaxies, a connection that is especially apparent when galaxies collide or merge. During these cosmic events, the supermassive black holes at their centers may eventually come together, leading to the creation of a larger, more powerful black hole. This merger is not just a monumental shift in the structure of the galaxy. It also sends ripples through the fabric of space-time itself, creating gravitational waves that spread out across the universe. These waves, though faint and incredibly distant, are detectable by scientists, providing a glimpse into some of the most violent and energetic processes in the cosmos. As black holes grow, their influence extends far beyond their immediate vicinity. They can impact the rate at which stars form within their host galaxies, creating a feedback loop that can alter the galaxy's future trajectory. The presence of a massive black hole can both stimulate and suppress star formation, shaping the galaxy in ways that would otherwise be impossible. Over millions and billions of years, these cosmic giants, black holes, serve as both creators and destroyers. They contribute to the dynamics of stars, shaping the structure of galaxies and driving their evolution through time. Despite their crucial role in the universe, humans have never directly observed a black hole in the way we see ordinary objects. Black holes do not emit light in the conventional sense, making them invisible to our eyes. However, through meticulous scientific work, we have come to understand their presence and the impact they have on their surroundings. The region around a black hole is often incredibly energetic, particularly when matter is drawn toward it. As this matter spirals into the black hole, it heats up, forming a hot, luminous accretion disk of gas and dust. This disk emits radiation across a wide range of wavelengths, including X-rays, which can be detected by specialized telescopes. These observations, while indirect, have provided crucial insights into the nature of black holes. In 2019, a groundbreaking achievement in black hole research was made when scientists captured the first ever image of a black hole's shadow. This particular black hole resides in the galaxy M87, a galaxy located billions of light years away. To capture this image, researchers used a network of radio telescopes scattered across the globe. By combining data from these telescopes, they created an effective planet-sized instrument capable of observing an object so distant and mysterious. The result was an image of the shadow of the black hole, surrounded by the glowing gas and dust that circles it. This iconic image not only provided a tangible representation of a black hole, but also confirmed many of the theoretical models that had been proposed over the years. Beyond imaging, astronomers have also turned to the behavior of nearby stars to study black holes. By observing the orbits of stars that are close to a black hole, scientists can determine the black hole's mass and infer other important characteristics. The intense gravitational pull of a black hole warps the paths of these stars, allowing researchers to indirectly deduce the black hole's size, location, and power. This method has become one of the primary ways to study these invisible giants, providing a window into a world that would otherwise remain hidden. Technological advancements have revolutionized our understanding of black holes in ways that were once beyond our imagination. Powerful new telescopes now allow us to observe the universe in a variety of wavelengths, including infrared and radio waves. These wavelengths can penetrate cosmic dust clouds, revealing objects and phenomena that would be invisible to traditional optical telescopes. This ability to observe black holes and their surroundings in greater detail has opened up new avenues for research, offering a deeper understanding of their behavior and their influence on the galaxy around them. In addition to these new telescopes, innovations in imaging techniques and sensors have enhanced our ability to capture fine details of black holes. The Event Horizon Telescope (EHT) project, which produced the first image of a black hole's shadow, is an exemplary case. This global collaboration, along with improvements in data collection and processing, has made it possible to visualize black holes in ways that were once unthinkable. As technology continues to evolve, sharper and more detailed images will undoubtedly emerge, revealing facets of black holes that have remained a mystery for centuries. Advances in computational power have also played a crucial role in black hole research. Today's powerful computers can simulate the complex dynamics of black holes with unprecedented precision. These simulations help scientists visualize phenomena such as the merger of two black holes or the behavior of matter near the event horizon, the point beyond which nothing, not even light, can escape. These simulations, when compared with real observational data, provide a means of testing and refining our theories about the behavior of these enigmatic objects. Moreover, machine learning is becoming an increasingly powerful tool in black hole research. By training algorithms to recognize patterns in large sets of astronomical data, scientists can detect the presence of black holes and monitor their activity more efficiently than ever before. This technology has the potential to speed up the discovery of new black holes and refine our understanding of their evolution. As a result, we are now able to explore the universe in ways that were once thought to be the stuff of science fiction. These technological breakthroughs are not just advancing our knowledge of black holes. They are transforming our understanding of gravity, fundamental physics, and the very fabric of the universe itself. With each new discovery and each leap in technology, we come one step closer to unraveling the mysteries of these cosmic giants. Every advancement offers a deeper, more detailed view of the universe, one that brings us closer to understanding the forces that govern the cosmos. The concept of the multiverse, an idea suggesting that our universe is just one of many parallel universes, expands the scope of our understanding even further. If we think of our universe as a single bubble in a vast ocean of bubbles, the multiverse theory proposes that each of these bubbles could represent a different universe, possibly with its own laws of physics and unique dimensions. This is in stark contrast to the traditional view that our universe is the only reality that exists. The multiverse suggests that there are an infinite number of possibilities, some of which may resemble our own universe, while others could be entirely alien, with completely different rules governing existence. One of the ways scientists approach the multiverse theory is through quantum mechanics, the branch of physics that deals with the behavior of subatomic particles. In the quantum realm, particles can exist in multiple states simultaneously, a concept known as superposition. This bizarre behavior gives rise to the many worlds interpretation, which posits that every time a decision is made or an event occurs, the universe splits into multiple branches, creating a parallel reality for each possible outcome. This means that, in theory, every choice we make could result in the creation of a new universe, each with its own distinct path. Another avenue for exploring the multiverse is through the concept of cosmic inflation, which describes the rapid expansion of the universe shortly after the Big Bang. Some theories propose that during this period of inflation, different regions of space could have expanded at different rates, creating bubble-like universes that are isolated from one another. Each of these bubbles could have its own unique set of physical laws and constants, further expanding the possibilities of what might exist beyond our observable universe. While the multiverse theory is an intriguing and compelling idea, it remains speculative, with no direct evidence to confirm the existence of parallel universes. Nonetheless, it challenges our conventional understanding of reality and pushes the boundaries of what we think is possible. The multiverse invites us to reconsider the very nature of existence and explore the vastness of possibilities that may lie beyond our own universe. One piece of evidence that some scientists point to in support of the multiverse theory is the cosmic microwave background radiation, CMB. This faint afterglow from the early universe shows a remarkable degree of uniformity, with slight fluctuations that suggest the universe began in a highly complex and turbulent state. Some scientists argue that if our universe underwent cosmic inflation, this rapid expansion could have resulted in different regions developing unique characteristics, essentially creating multiple universes. Each of these universes could have its own physical laws, constants, and even histories, raising profound questions about the very nature of reality and our place within it. String theory, which strives to merge the seemingly incompatible worlds of general relativity and quantum mechanics, introduces the compelling idea that there may be multiple dimensions beyond the familiar 3 dimensions of space and one of time. In some of these scenarios, these extra dimensions could give rise to a landscape of vastly different universes, each with its own unique properties. This concept has captured the imaginations of physicists and philosophers alike, offering a tantalizing glimpse into a more intricate and complex cosmos. However, the road to proving the multiverse theory is riddled with obstacles. One of the most significant challenges is the notion that these other universes might be completely isolated from ours, so much so that they are unobservable and unreachable. If we cannot gather direct empirical evidence of their existence, the theory remains firmly in the realm of speculation. Science, at its core, thrives on observation, experimentation, and testability. Without the means to confirm or deny the existence of these alternate universes, the multiverse remains a theoretical construct, an idea that cannot yet be substantiated. Furthermore, discussions surrounding the concept of fine-tuning, specifically why our universe appears to have such finely tuned conditions for life, are central to multiverse debates. Some proponents of the multiverse suggest that if there are indeed countless universes, it becomes statistically probable that at least one would possess the ideal conditions for life as we know it. After all, with so many possible outcomes, one universe would inevitably have the perfect recipe for the emergence of life. However, critics argue that this explanation may not be as robust as it seems. The idea that the conditions of our universe were randomly fine-tuned across an infinite spectrum of possibilities is highly speculative, as it depends on assigning probabilities to events that lack any empirical support. Although theoretical physicists continue to explore various ways in which the multiverse might be realized, these concerns underscore the limitations of the concept. Despite the theoretical elegance of the multiverse, the scientific community has yet to find a clear path toward proving or disproving its existence. At the heart of the multiverse concept lies a profound rethinking of reality itself. Traditionally, we view our universe as a singular, contained system governed by consistent laws of physics. Everything we know, the stars, the planets, the particles, exists within this system, which unfolds according to a set of predictable rules. Yet the multiverse challenges this perception, suggesting that our universe is merely one of many, each coexisting within a vastly more complex structure. In this new framework, reality is no longer confined to a single universe. Imagine your life as a single path winding through a dense forest. Every decision you make, every twist and turn, leads you down a different trail, forming a unique path through the wilderness. In the context of the multiverse, every possible decision or event spawns a new universe. Each choice you make could lead to the creation of an alternate reality, one where different outcomes unfold, each branching into new possibilities. Some of these universes might be nearly identical to our own, while others could be radically different. In some, the laws of physics might operate differently, or entirely new forms of matter could exist. Life could take forms we cannot even imagine, or it might not exist at all. The very notion of parallel universes introduces a mind-boggling diversity of possibilities, suggesting that the fabric of existence itself is far more expansive than we ever realized. This idea leads to questions about the nature of individuality and uniqueness in a multiverse. If there are infinite versions of every possible reality, is anything truly singular? Is our universe the primary one, or is it merely one iteration among many? If every possible path leads to the creation of a different universe, what does that mean for our sense of self, our sense of identity, and the choices we make? The multiverse also intersects with some of the deepest questions in physics and cosmology. For instance, it could offer a new way to address the fine-tuning problem, why the conditions of our universe appear so perfectly calibrated for life. In a multiverse scenario, it would be expected that at least one of the infinite universes would have the right conditions for life to arise. This might mean that our universe, with all its complexity and apparent perfection, is simply one random outcome in an endless sea of possibilities. While this view reshapes our understanding of existence, it also challenges the idea of the universe as a unique, self-contained system. If the multiverse exists, it suggests that there are potentially infinite versions of reality, each with its own set of physical laws and properties. The implications for our understanding of reality, both scientifically and philosophically, are profound. If the multiverse theory is ever proven to be true, the ramifications would be far-reaching. First and foremost, it would suggest that our universe is merely one of many, each with its own laws of physics and history. The concept of existence would expand exponentially, indicating that the reality we know is just a fragment of a much larger, more complex cosmic tapestry. One of the most striking consequences of the multiverse theory is the expansion of possibility itself. Every decision we make, every choice, every action, could result in the creation of a new universe with its own unique timeline. This would lead to a scenario in which countless versions of ourselves exist, living out alternate lives in parallel universes. In some of these universes, we might have made entirely different choices, or events might have unfolded in radically different ways. These alternate realities could represent what could have been, providing a window into countless other versions of our lives. This idea could prompt deep philosophical inquiries about the nature of fate, choice, and identity. If infinite versions of ourselves exist, how do we define our individuality? Is there a central you, or are you simply one manifestation of a broader, more complex set of possibilities? The existence of the multiverse also raises intriguing scientific questions about the nature of the physical laws that govern our universe. Are the laws we observe here the only ones that are possible, or are they simply one set of rules among many? If there are countless universes with different physical properties and constants, could our understanding of physics need to be rewritten entirely? This realization would push scientists to think beyond the confines of our own universe, seeking to understand how these universes might interact, or if they even do. One of the most pressing challenges to the multiverse theory lies in the difficulty of testing it scientifically. If the universes are truly isolated from one another, the possibility of observing or interacting with them may be inherently impossible. This raises questions about the very nature of scientific inquiry. Traditional methods of observation and experimentation may not be sufficient to explore the realm of the multiverse. To make any progress, new frameworks and methodologies might need to be developed, ones that can account for realities beyond our direct perception. On a more existential level, the discovery of the multiverse could alter how we view our place in the cosmos. If every possible reality exists, it might diminish the significance we place on our own universe. We could begin to see ourselves not as the center of existence, but as a part of a much broader spectrum of experiences. The discovery of infinite realities could alter our sense of meaning and purpose, inspiring a shift in how we view our lives and actions. The multiverse theory also comes in a variety of forms, each offering its own take on how these universes might be structured and formed. One of the most well-known variations is the bubble universe theory, which imagines the universe as a vast foam of bubbles, each one representing a different universe. These bubbles would have different properties, with some potentially supporting life and others being completely inhospitable. Each universe would float independently, unable to interact with the others, existing separately yet simultaneously. Another compelling version of the multiverse comes from the many worlds interpretation of quantum mechanics. In this framework, every possible outcome of a quantum event creates a new branch of reality. If you make a choice, one universe follows one path, while another follows a different decision. This creates an infinite number of parallel universes, with each decision leading to a different outcome. It's like a vast tree of possibilities, where every branch represents a different version of reality. Then there is the string theory-based multiverse, where our universe is one of many slices in a larger framework composed of vibrating strings. Each variation in how these strings vibrate could result in entirely different physical laws, creating a patchwork of universes with varying properties. These universes would coexist within the same overarching structure, but each would operate according to its own set of rules. Finally, some theories focus on the idea of cosmic inflation, a rapid expansion of space that occurred shortly after the Big Bang. In these models, different regions of space expanded at different rates, leading to the formation of pocket or island universes, each with its own unique properties. These isolated pockets would continue to expand, forming an ever-growing multiverse. Each of these theories offers a unique perspective on the nature of the cosmos, expanding our understanding of what is possible in the universe. While they differ in their specifics, they all share the core idea that our universe is just one of many, each with its own set of physical laws and constants. The idea of the multiverse has captivated the human imagination because it suggests that we are not alone in existence, but part of a much grander and more diverse cosmic landscape. In the end, the idea of a multiverse presents us with a profound challenge to our traditional understanding of reality. It forces us to reconsider our place in the universe, to question the very nature of existence itself. And perhaps, most importantly, it invites us to dream of what might be possible in a reality far grander than we ever thought possible. The multiverse theory presents an extraordinary framework for exploring fundamental questions about our universe's origin and structure. Rather than seeking a singular event that triggered the beginning of everything, it encourages us to view our universe as one outcome among a vast array of possibilities. These possibilities branch out from different initial conditions, offering a new way to think about how our current reality came to be. This perspective allows us to step beyond conventional thinking, broadening our exploration into the mysteries of the cosmos. In the traditional view, scientists search for a first cause or a singular moment that initiated everything. However, the idea of a multiverse proposes that the origin of our universe may not be tied to a single unique event. Instead, it could be the result of countless different scenarios, each branching off into its own universe. This opens up avenues for creative solutions to long-standing cosmic questions that have puzzled scientists for centuries. One key area where the multiverse theory sheds light is the question of fine-tuning. This concept addresses the puzzling fact that the physical constants of our universe, such as the strength of gravity or the mass of the electron, are perfectly set to allow life to exist. If we consider the possibility of an infinite number of universes, each with varying physical constants, the fact that our universe supports life becomes much less surprising. Instead of requiring special explanations for why our universe is conducive to life, the multiverse theory suggests that life is a natural outcome of the vast possibilities available. Given an infinite number of universes, it stands to reason that some would have the precise conditions necessary for life to flourish. In a statistical sense, the multiverse theory proposes that with so many potential realities, it is inevitable that some would contain conditions suitable for life. This provides a refreshing alternative to the notion that our universe's particular properties are uniquely tailored for life. Rather, it suggests that we may simply be one of many possibilities that happen to fall into favorable circumstances. The multiverse theory also provides a potential resolution to one of the greatest challenges in modern physics, the reconciliation of quantum mechanics and general relativity. These two pillars of science have long been at odds, as they describe the universe in fundamentally different ways. Quantum mechanics governs the microscopic world of particles and their bizarre behaviors, while general relativity deals with the large-scale structure of space-time and gravity. The multiverse theory opens up new ways of thinking that might bridge the gap between these two frameworks, offering fresh insights into the fundamental workings of the universe. Moreover, the multiverse concept pushes researchers to think beyond the observable universe, considering realms that we cannot directly access. This interdisciplinary approach encourages scientists to break free from the constraints of our current understanding and explore new pathways that could lead to groundbreaking discoveries. The potential existence of multiple universes beckons us toward a richer, more diverse understanding of reality, inspiring us to venture deeper into the unknown. As we confront mysteries of existence, the multiverse theory challenges us to ask bold questions. It offers a lens through which we can view the cosmos not as a solitary reality, but as part of a vast, interconnected web of possibilities. What once seemed like insurmountable questions might, through this new perspective, become stepping stones toward a deeper and more profound knowledge of the universe and our place within it. At the heart of the multiverse theory lies the strange and fascinating realm of quantum mechanics. This branch of physics, which explores the behavior of the tiniest particles, has long intrigued scientists and philosophers alike. One of the most puzzling aspects of quantum mechanics is the phenomenon of superposition. In this state, particles can exist in multiple conflicting states simultaneously, much like a coin spinning in the air, being both heads and tails until it lands. This idea challenges our traditional understanding of reality, suggesting that the universe at its most fundamental level behaves in ways that are profoundly different from what we experience in our everyday lives. When we make a measurement in the quantum world, it appears to force the system to choose one of these possible states, collapsing the superposition into a single outcome. However, some interpretations of quantum mechanics, such as the many worlds interpretation, suggest a more radical idea. Instead of collapsing into one state, every possible outcome is realized in its own separate universe. Each time a measurement is made, the universe splits, creating a new branch where each possible outcome unfolds. This idea presents a radically different view of reality, one where the universe is constantly branching into new possibilities with every decision or event. This concept is often visualized as a tree, where each decision or measurement creates a new branch. In this view, every possible outcome of every event leads to its own unique universe, each with its own distinct reality. Such a perspective invites us to reconsider our understanding of time and space, as the boundaries of our universe may not be as fixed as we once thought. The very nature of reality, it seems, is more fluid and dynamic than we could have imagined. One of the most intriguing aspects of quantum mechanics is the phenomenon of entanglement, where particles become linked in such a way that the state of one particle instantaneously affects the state of another, even if they are separated by vast distances. This seemingly magical connection between distant particles suggests that the universe may be more interconnected than we realize, and it hints at the possibility of hidden dimensions or realities beyond our own. If entanglement occurs across multiple parallel universes, it could imply that what happens in one universe may influence others, transcending the limitations of space and time as we currently understand them. As we explore these ideas, quantum mechanics does not offer easy answers, but it raises fascinating possibilities. It forces us to reconsider the very nature of reality and our place within it. The multiverse, as viewed through the lens of quantum mechanics, opens up a realm of infinite potentialities, each one offering a unique vision of how the universe might work. Time, as we experience it, is another fundamental aspect of the universe that has fascinated scientists for centuries. In many ways, time is the framework within which the events of the universe unfold. Just as we use a ruler to measure distances in space, we use time to measure changes, motions, and the passage of events. From the birth of the cosmos at the Big Bang to the gradual movement of stars across the night sky, time helps us to understand the unfolding of cosmic events. In physics, time is not absolute. Instead, it is relative, meaning it passes at different rates depending on the observer's frame of reference. This idea was first proposed by Albert Einstein in his theory of relativity, which demonstrated that time is linked to the fabric of space itself. For instance, if you were traveling in a rocket at speeds close to the speed of light, time would appear to pass more slowly for you than for someone who remains on Earth. This phenomenon, known as time dilation, illustrates how time is not a constant, but rather a fluid dimension that can stretch and contract depending on the conditions of the surrounding space. Time is not just a background in which events occur, it is intricately tied to the very structure of the universe. The expansion of the cosmos, the formation of galaxies, and the birth of stars are all processes that unfold in time. Without the progression of time, we would be unable to make sense of the sequence of events that led to the universe's current state. As time continues to unfold, it brings with it a sense of change and evolution, shaping the universe in ways that we are only beginning to understand. In this context, time travel becomes an intriguing concept. Several theories propose how time travel might be possible, though many of them remain speculative and theoretical. One popular idea involves the concept of wormholes, hypothetical tunnels in space-time that could allow for travel between distant points in both space and time. If wormholes could be discovered or artificially created, they might allow someone to journey backward or forward through time, as easily as traveling from one point in space to another. However, the challenges involved in creating a stable wormhole are immense, and for now, the idea remains firmly in the realm of theory. Another time travel theory is based on the speed of light. According to Einstein's equations, as an object approaches the speed of light, time slows down for that object relative to someone who is not moving as fast. This means that if you could somehow travel at or near the speed of light, you could experience time much more slowly than those around you. While this might allow you to travel into the future at an accelerated rate, reaching such speeds would require energy far beyond what we are currently capable of harnessing. Finally, there are theories that involve closed time-like curves, paths in space-time that loop back on themselves, potentially allowing an object to return to a previous point in time. These solutions to Einstein's equations suggest that time could have a cyclical nature, looping back in on itself in certain conditions. While such ideas are still far from being proven or practical, they offer a tantalizing glimpse into the possibility of time travel and the nature of time itself. As we continue to explore these concepts, we find that time, much like the multiverse, challenges our understanding of the universe and invites us to think more deeply about the fundamental nature of reality. Time is not just a measure of change. It is a force that shapes the universe, propelling it forward and perhaps opening doors to the possibilities of the future. Time travel, a concept that has long captivated the human imagination, presents intriguing possibilities, but also deep paradoxes that challenge our understanding of reality. A well-known example is the grandfather paradox, the idea that altering events in the past could result in a scenario where the time traveler never exists. This paradox raises complex questions about causality and the potential consequences of tampering with time. What happens if a time traveler were to prevent their own birth or stop a crucial event from ever occurring? Would they simply vanish, or would the timeline adapt in a way that preserves their existence? These paradoxes illustrate just how difficult, if not impossible, it would be to make sense of time travel within the framework of our current understanding. In addition to paradoxes, the theory of parallel universes emerges as a potential way to address these issues. Some theorists suggest that time travel might not result in altering the past in the way we typically think. Instead, traveling to the past could cause the formation of a new parallel timeline, leaving the original one untouched. This idea is captivating because it offers the possibility of revisiting historical moments without disrupting the fabric of reality. However, while this theory presents a tantalizing solution to the paradox of time travel, the existence of parallel universes is still purely speculative. We have no definitive evidence to suggest that such alternate realities exist, making this idea a fascinating yet uncertain aspect of time travel discussions. At the heart of these debates lies the question of whether time travel, as we envision it, could ever become a reality. Despite the theoretical allure, the practical challenges remain overwhelming. From the colossal energy requirements to the potential for paradoxes, the concept of time travel remains in the realm of science fiction. The laws of physics, as we understand them, suggest that the conditions necessary for time travel are far beyond our current technological capabilities. Until we make significant advances in our understanding of the universe, time travel remains an exciting possibility, but one that is not yet feasible. The theory of relativity, proposed by Albert Einstein, fundamentally changed our understanding of time. Traditionally, we think of time as a constant, a steady progression that ticks away at the same pace no matter where we are or what we're doing. However, Einstein's theory suggests that time is far more flexible, shaped by factors such as speed and gravity. It's no longer an unchanging backdrop to our lives, but a dynamic and malleable dimension that can stretch and contract. Consider two observers, one standing on Earth and the other traveling in a spaceship near the speed of light. For the person in the spaceship, time would appear to pass more slowly than for the person on Earth. This phenomenon, known as time dilation, reveals that time is experienced differently depending on one's motion relative to others. If the traveler in the spaceship were to make a journey at near light speed and then return home, they would find that far more time had passed on Earth than they had experienced. This illustrates a fundamental insight of relativity. Time is not a universal constant, but a flexible dimension influenced by motion. Gravity plays an equally important role in the flow of time. The stronger the gravitational field, the more significantly time slows down. For instance, clocks on satellites in orbit, which are farther from Earth's gravitational pull than clocks on the ground, tick slightly faster. This difference in the passage of time is not just a theoretical concept. it has practical implications such as the adjustments that must be made to keep GPS systems accurate. Time runs differently depending on where you are in the universe. The farther you are from a massive object, the faster time appears to pass, and the closer you are to one, the slower it moves. This relationship between space and time, dictated by both gravity and velocity, is a central tenet of Einstein's theory of relativity. Time, in the context of the universe, is not just a measure of our individual lives. It is a critical factor in the broader evolution of the cosmos. Time intertwines with space to form the fabric of space-time, which governs everything from the motion of subatomic particles to the behavior of massive galaxies. As the universe expands, time becomes an essential element in understanding how the universe evolves. From the birth and death of stars to the movement of galaxies, time shapes the events that unfold in the universe, making it a key to understanding not just the past, but the future. In the early moments after the Big Bang, time began its journey. As the universe cooled and expanded, both space and time evolved together, setting the stage for the cosmic processes that followed. This is why distant galaxies appear to be moving away from us. The fabric of space itself is stretching, causing the light from these galaxies to take longer to reach us, thus providing a snapshot of their past. Understanding time's role in the universe is crucial for predicting its future as well. The fate of the cosmos could be determined by the interplay of matter, energy, and time. Depending on these factors, the universe could continue expanding indefinitely, slow down, or even collapse back in on itself. These possibilities unfold over immense time frames, which is why time itself is so vital to our understanding of the universe's eventual destiny. Time also affects how we think about the cosmos on a human scale. 1,000,000 years may seem like an unfathomably long period, but in the life of a galaxy, it is nothing more than a blink of an eye. And when we consider the full span of the universe, the concept of time becomes even more incomprehensible. Our experience of time is limited by our human perspective, but on a cosmic scale, time operates on a vastly different plane, influencing the formation of stars, the movement of galaxies, and the expansion of the universe itself. Time is not just a measurement, it is the force that drives the story of the cosmos, and understanding it is crucial to grasping the true nature of existence. As we contemplate the nature of time, it becomes clear that it is not experienced uniformly across the universe. The influence of gravity and speed creates fascinating differences in how time is perceived and measured. For example, near massive objects like planets and stars, time moves more slowly than in areas with weaker gravitational forces, such as in the vacuum of space. If you were to stand near a black hole, you would experience time much more slowly than someone far away on a distant planet. This phenomenon, known as gravitational time dilation, has been observed in satellites orbiting the Earth, where clocks in space run slightly faster than those on the ground. Moreover, speed plays a critical role in shaping our experience of time. If you were to travel at velocities close to the speed of light, time would appear to slow down for you, while those remaining at rest would experience time normally. This means that if you embarked on a journey at such high speeds, you could return to find that far more time had passed for those who remained behind. The universe, it seems, offers a rich tapestry of time experiences, all influenced by the forces of gravity and motion. This leads to the profound conclusion that time is not a constant, but a malleable feature of the cosmos, shaped by the location and movement of objects within it. The relationship between time and space is central to our understanding of the universe. Together, they form a unified concept known as space-time. Imagine space-time as a fabric, with each thread representing not just the three dimensions of space, up and down, left and right, forward and backward, but also the flow of time. If time were to exist separately from space, it would suggest a universe where events could occur without any spatial context. This raises intriguing questions about the nature of reality. Could something change or evolve without space for it to occupy? Such a scenario challenges our fundamental understanding of existence. In our current understanding of physics, every event, whether it's the explosion of a star or the orbit of a planet, is tied to both a specific location and a moment in time. If time were somehow detached from space, it could imply a reality where events unfold without any spatial reference. This idea could lead to radically new frameworks for understanding the universe, perhaps suggesting new dimensions or even entirely different forms of existence. But such a separation of time and space would be so radically different from our current worldview that it's difficult to even imagine. The nature of time has also inspired profound philosophical debates. One key discussion revolves around whether time is an objective feature of the universe or merely a subjective experience. Some philosophers argue that time exists independently of human perception. It flows steadily like a river, regardless of whether anyone is observing it. In contrast, others suggest that time is a construct of human consciousness, shaped by our memories and expectations. This perspective implies that our experience of time is personal and can vary from one individual to another. It raises fascinating questions about how we perceive time differently during moments of joy versus moments of suffering. Another important debate centers on the direction of time. Does time flow in one direction, from past to present to future, as we experience it? This is known as the arrow of time. Some argue that this forward progression is tied to the second law of thermodynamics, which states that in a closed system, entropy or disorder always increases over time. In other words, the universe tends to move from order to chaos, and this directional flow of time reflects that process. However, some philosophers propose a different view, that time is a more static dimension, like space, where all moments exist simultaneously. If this were true, past, present, and future might not be distinct, but could instead be interconnected, forming a larger, more complex structure of time. These debates about the nature of time invite us not only to consider the mechanics of time, but also to reflect on our own experiences. How we perceive time can shape our emotions, our memories, and our understanding of life. Time is not just a measurement, it is a deeply personal and philosophical concept that influences every aspect of our existence. Whether we see it as a linear progression or as a more fluid and subjective experience, time continues to be one of the most fascinating and mysterious aspects of the universe. In Hinduism, the concept of time is viewed in a profoundly cyclical manner, but it extends beyond the simpler understanding of endless repetition. Time in Hindu thought is characterized by vast, sweeping cycles, known as yugas, that span millions of years. These yugas follow a pattern of creation, preservation, destruction, and renewal, offering a view of time that is as expansive as the universe itself. This perspective reflects not only a deep connection to spirituality, but also an intimate understanding of the cosmic forces that govern existence. The endless repetition of these cycles suggests that all things, life, the cosmos, the very fabric of the universe, are locked in a perpetual dance of transformation and renewal. The universe, in this view, is never static. It is always in motion, always evolving, always beginning again. This cyclical view of time is mirrored by the Mayan civilization, which developed its own unique methods of measuring time. The Maya created intricate systems of interlocking calendars, each designed to track the various cycles of the natural world and human life. These calendars aligned with astronomical events, recognizing that time is deeply intertwined with the movements of the cosmos. The Mayans understood that time was not just a human construct, but a divine principle that reflected the will of the gods. The cycles they tracked included agricultural patterns, religious observances, and celestial phenomena, all of which were vital to their way of life. Their complex understanding of time reveals a profound spiritual connection to the universe, underscoring the idea that the passage of time is not a mere chronological progression, but a sacred rhythm that governs all existence. In both Hinduism and the Mayan worldview, time is not just a measurement. It is a spiritual force, a cosmic principle that shapes human experience and belief. These diverse interpretations of time show how cultures across the world have sought to understand the cosmos, not only in terms of its astronomical phenomena, but also in the deeper spiritual sense of the universe's eternal cycle of birth, death, and rebirth. In this way, time itself becomes a thread that ties humanity to the vast, unknowable cosmos, reinforcing the timeless relationship between Earth and the greater universe. In modern science, this relationship between humanity and the cosmos is explored through the search for extraterrestrial life. Scientists are employing an array of innovative methods to uncover evidence of life beyond our planet. One of the primary avenues of exploration focuses on the planets and moons within our own solar system, particularly those that may have the conditions necessary for life. Mars, for example, with its frozen surface and potential for liquid water beneath, is a prime candidate for exploration. Similarly, the icy moons of Jupiter and Saturn, such as Europa and Enceladus, are being investigated for signs of life. By analyzing soil and ice samples from these celestial bodies, scientists hope to uncover organic molecules that could indicate the presence of past or present life. Another key method in the search for extraterrestrial life involves the use of powerful telescopes to examine exoplanets, planets that orbit stars outside our solar system. Through a technique known as spectroscopy, scientists can examine the light passing through a planet's atmosphere and identify its composition. Specific gases, such as oxygen or methane, could suggest biological processes occurring on these distant worlds. This technique provides a powerful tool in the search for life, allowing scientists to study distant planets without ever leaving Earth. Beyond these methods, there are ambitious projects like SETI, the Search for Extraterrestrial Intelligence, which focuses on detecting signals from advanced alien civilizations. Through this initiative, scientists listen for radio waves or other forms of communication that could originate from intelligent beings located in far-off galaxies. The search for alien signals involves analyzing vast amounts of data, looking for any patterns or anomalies that could indicate the presence of intelligent life. Additionally, laboratory experiments simulate extraterrestrial environments to test how organisms might survive in extreme conditions. By recreating environments similar to those found on distant planets, where temperatures are freezing, atmospheres are thin, or radiation levels are high, scientists can observe how life might adapt to such harsh environments. These experiments offer crucial insights into the types of life forms that could potentially exist on planets or moons with extreme conditions. Each of these methods contributes to our growing understanding of the cosmos and our place within it. By employing diverse approaches, scientists expand the scope of the search for extraterrestrial life, creating a multifaceted scientific endeavor that spans the entire universe. The prospect of discovering life beyond Earth is not merely a scientific question. It challenges our fundamental understanding of life itself. It raises profound philosophical questions about what it means to be human, the nature of consciousness, and our unique place in the cosmos. For centuries, humanity has gazed at the stars, asking the age-old question, are we alone? The vastness of the universe, with its countless galaxies and stars, seems to suggest that life could emerge in forms unimaginable to us. With each new discovery in the search for extraterrestrial life, the likelihood grows that life exists somewhere beyond Earth. This realization challenges the notion that Earth is a rare haven for living beings, prompting scientists to reconsider what conditions might be necessary for life to thrive. The search for extraterrestrial life extends beyond finding planets with Earth-like conditions. Scientists are now expanding the definition of habitable zones, regions in space where life could exist, not just to planets with warm, stable climates, but to more extreme environments. What if life could exist beneath the icy surface of a distant moon or high in the clouds of a gas giant? Could life, in forms we cannot yet comprehend, thrive in places we have not yet explored? If life is discovered elsewhere, it would not just confirm that life can exist in conditions different from those on Earth. It would reshape our entire understanding of biology, evolution, and what it means to be alive. Such a discovery would prompt deep questions about the nature of consciousness itself. Are our minds truly unique, or are they simply one of many possible expressions of life in the universe? What does it mean to be human in a universe filled with intelligent beings? These questions would force a reevaluation of existing scientific theories and provoke profound philosophical reflection. In the pursuit of understanding the universe, we are continually confronted with mysteries that defy our comprehension. The very fabric of the cosmos is stranger than we imagined. Black holes, those enigmatic objects that warp space and time, continue to challenge our understanding of physics. Dark matter, which makes up most of the mass in the universe but cannot be seen or directly detected, shapes the very structure of galaxies. Dark energy, a mysterious force driving the accelerating expansion of the universe, remains one of the greatest unsolved puzzles in modern science. These concepts, though initially abstract, are no longer just theoretical ideas. They have been confirmed through rigorous observation and experimentation. The universe, it seems, is not just a vast collection of stars and planets. It is an intricate, dynamic system governed by forces that are invisible to the naked eye. At the quantum level, particles behave in ways that defy the laws of classical physics, and time itself flows differently depending on the strength of gravity or the speed of an object. These discoveries beg the question, are we alone in this vast universe? Could there be parallel universes existing alongside our own? What lies beyond the edge of what we can observe, beyond the limits of our current technology? These questions point to the fundamental mysteries of existence, mysteries that continue to drive scientific inquiry and shape our understanding of the cosmos. The origins of the universe remain one of the most fascinating and enigmatic subjects in science. The prevailing theory, known as the Big Bang Theory, suggests that the universe began from an incredibly small, dense point, roughly 13.8 billion years ago. Imagine a tiny balloon compressed to the size of a dot and then suddenly expanding. This is similar to how the universe began. The initial explosion was not a violent detonation, but a rapid expansion of space itself. As the universe expanded, it cooled, allowing for the formation of elementary particles, which later combined to form atoms. Over millions of years, these atoms gathered, forming stars and galaxies. The Big Bang Theory not only explains the origin of the universe, but also its ongoing expansion. Observations show that galaxies are moving away from each other, suggesting that space itself is still stretching. This ongoing expansion is a testament to the initial burst of energy that set the universe in motion. The afterglow of that moment, the cosmic microwave background radiation, still lingers, providing evidence of the universe's fiery birth. Scientists have also proposed additional theories, such as the concept of cosmic inflation, which suggests that the universe expanded exponentially in the first moments after the Big Bang, growing faster than we can fully imagine. This theory helps explain why the universe appears so uniform, with similar properties in all directions. Alternative models, like the cyclic model, offer a different perspective. In this view, the universe undergoes infinite cycles of expansion and contraction akin to the beating of a heart. In this model, the universe has no true beginning or end. Instead, it flows through an eternal series of births and rebirths. Each of these theories, whether it's the Big Bang or the cyclic model, offers a glimpse into the profound and complex nature of the cosmos. As scientists continue to study the origins of the universe, they are constantly inching closer to understanding how everything came to be. With each discovery, the universe becomes a little less mysterious and a little more accessible, yet it remains as wondrous and awe-inspiring as ever. Scientists have made groundbreaking discoveries that have reshaped our understanding of the universe. One of the most compelling pieces of evidence comes from the detection of cosmic microwave background radiation. This faint, pervasive glow filling the entire universe is a remnant of the immense heat that permeated the cosmos during its earliest moments. This discovery offers strong confirmation of the Big Bang Theory, which posits that the universe began from an extraordinarily hot and dense state and has been expanding ever since. The idea that the universe's evolution traces back to such an explosive origin has not only revolutionized cosmology, but also provided a powerful framework for understanding the ongoing dynamics of the cosmos. The Big Bang Theory serves as a guide, helping us trace the history and development of the universe. From its fiery, chaotic beginnings to the expansive and complex cosmos that we observe today, the theory paints a picture of a universe that is constantly changing, evolving, and expanding. Over the past several decades, scientists have painstakingly gathered evidence through various observations and experiments, each piece contributing to a broader, ever clearer image of the universe's birth and evolution. The detection of cosmic microwave background, CMB radiation, stands out as one of the most significant pieces of evidence supporting the Big Bang. This radiation, often referred to as the afterglow of the Big Bang, represents heat that has been traveling through space for over 13 billion years. Imagine it as a signal from the universe's earliest moments, a faint glow that fills the expanse of the cosmos, a direct connection to the cataclysmic event that sparked the universe's existence. The discovery of CMB radiation was akin to finding an echo of the universe's infancy, preserved through time, providing an invaluable link to a moment in the distant past. In addition to the CMB, scientists have observed the redshift of galaxies, which further strengthens the case for the Big Bang theory. The redshift phenomenon occurs when light from distant galaxies shifts toward the red end of the spectrum, a telltale sign that these galaxies are moving away from us. This effect is a direct consequence of the universe's expansion, much like how the pitch of a passing siren decreases as the vehicle moves farther away. The greater the distance of a galaxy, the faster it appears to be receding, reinforcing the notion that the universe was once compacted into a singular, incredibly dense state. The abundance of light elements such as hydrogen and helium scattered throughout the cosmos also supports the Big Bang theory. These elements were formed during the first few minutes after the universe's birth, when conditions were extremely hot and dense. The ratio of these elements aligns with predictions made by the Big Bang model, providing a chemical fingerprint of the universe's early moments. Studying these ratios allows scientists to verify how much of each element should exist, further solidifying the theory's credibility. Moreover, the concept of cosmic inflation introduces an additional layer of understanding to the universe's early history. This theory suggests that in the fraction of a second after the Big Bang, the universe expanded at an astonishingly rapid rate, far faster than the speed of light. Evidence for cosmic inflation comes from the minute fluctuations in the cosmic microwave background radiation. These tiny variations, when scrutinized, match the predictions made by the inflationary model, offering another piece of evidence that strengthens the Big Bang theory. Together, these pieces of evidence weave a coherent narrative, a compelling story that supports the idea that the universe began as a singular explosive event and has been expanding and evolving ever since. The Big Bang theory, with its emphasis on an initially dense and hot universe that has been continuously expanding, has brought about both awe and controversy. It offers a framework that explains much about the universe's origins, but also leaves unanswered questions that fuel scientific debate. One of the primary controversies surrounding the Big Bang theory revolves around the events that transpired during the very first moments of the universe's existence. While the theory offers a robust explanation for the universe's evolution, the specifics of what happened in that initial instant remain elusive. Theoretical models based on current understanding may never fully capture the details of this primordial event, leaving some scientists to question whether the Big Bang theory provides a complete picture of the universe's formation. A further point of contention is the concept of cosmic inflation, which proposes that the universe underwent a rapid and expansive growth just after the Big Bang. While this idea helps explain some of the observed patterns in the cosmos, such as the uniformity of the cosmic microwave background radiation, it also raises its own set of questions. For instance, inflation implies a very specific set of conditions, but not all researchers agree that these conditions are entirely supported by current observations. The absence of direct evidence for inflation has prompted some scientists to consider alternative theories for the universe's early evolution. Another challenge lies in the existence of dark matter and dark energy, mysterious components that influence the expansion and structure of the universe but remain largely invisible. We infer their presence based on their gravitational effects, but their true nature is still a profound mystery. The lack of direct evidence for dark matter and dark energy adds an additional layer of complexity to the Big Bang theory, prompting some to question whether the theory is entirely complete. Some argue that a deeper understanding of these elusive components is necessary for a fully accurate picture of the universe's evolution. Furthermore, the Big Bang theory doesn't just spark scientific debates, it touches on deeper philosophical inquiries about the nature of reality itself. Questions arise about the concept of time, causality, and the very structure of the universe. Can there be a before the Big Bang? Does the universe require a cause for its existence, or does it emerge from nothingness in a way that defies traditional understanding? These are not just scientific questions, but profound philosophical ones, adding an existential dimension to the discussion. As such, the Big Bang Theory has become not only a scientific model, but also a platform for contemplating the very fabric of existence, reality, and the universe's ultimate nature. This combination of scientific exploration and philosophical reflection keeps the Big Bang Theory dynamic, continually evolving as new data and insights emerge. It opens the door for further discoveries and fresh perspectives on the origins and nature of the universe, ensuring that the conversation surrounding the Big Bang remains vibrant and ongoing. One particularly intriguing idea that has emerged in recent years is the possibility of multiple Big Bangs. This hypothesis suggests that the universe may not be a singular event, but rather part of a cyclical process of cosmic rebirths. Imagine, if you will, the Big Bang not as a one-time explosion, but as a recurring event, with universes being created and destroyed in an endless cycle. This concept hints at the existence of a multiverse, a vast collection of universes, each potentially governed by its own set of physical laws and principles. Each universe in this grand multiverse might begin and end in its own distinct way, with different configurations of matter, energy, and physical laws. If multiple Big Bangs have indeed occurred, it suggests that our universe is only one chapter in a much larger, never-ending cosmic saga. This idea challenges the traditional notion of time, which is usually understood as linear and one-directional. In a universe marked by multiple Big Bangs, time might not simply flow in one direction, but could cycle through different phases, with each cycle giving birth to new universes, each with its own unique characteristics. The existence of multiple Big Bangs could also help explain certain cosmic phenomena, such as the distribution of galaxies or the uniformity of the cosmic background radiation. If we are indeed part of a much larger cosmic narrative, it would radically alter our understanding of existence and prompt us to rethink everything we know about reality. Cosmic inflation theory, which was proposed to explain some of the Big Bang's unresolved questions, adds another layer of complexity. While the Big Bang Theory describes how the universe began as an extremely hot and dense point that rapidly expanded, cosmic inflation provides a detailed mechanism for how this rapid expansion occurred in the moments after the Big Bang. It offers a possible explanation for why the universe appears so uniform on large scales, and why distant regions of the cosmos seem to have similar properties despite being separated by vast distances. As we continue to study the universe, each new discovery builds upon the foundation laid by the Big Bang Theory. While there is still much to learn, the evidence we have gathered so far paints a compelling picture of a universe that began in an explosive event and has been expanding and evolving ever since. The mysteries of the universe, its origins, its structure, and its future continue to challenge our imaginations, inviting us to probe deeper into the nature of existence itself. The universe, in all its vastness, remains an enigma in many respects. While the Big Bang Theory provides a broad understanding of the origins of the cosmos, it doesn't fully explain some key aspects of the universe's structure and behavior. For example, why does the universe appear so uniform across enormous distances, despite vast regions seemingly having no interaction with one another? And why do distant areas of space, separated by unimaginable distances, share similar properties? This is where the theory of cosmic inflation enters the picture, offering a compelling answer to these questions. Just after the Big Bang, there was an extraordinarily brief yet intense period of exponential expansion. Picture the process like inflating a balloon. Initially, when you start blowing air into the balloon, it expands slowly, but as the air fills it, the expansion speeds up rapidly. Similarly, during the early moments of the universe, it grew at an unprecedented rate, faster than the speed of light, over an incredibly short span of time. This sudden and rapid expansion played a critical role in smoothing out irregularities in the universe, helping to create the uniform and vast cosmos we observe today. Inflation theory accounts for this uniformity by suggesting that the universe was stretched out so quickly that variations were evened out. The incredible speed of this expansion also resolved a crucial puzzle. It helped make sense of the tiny temperature fluctuations observed in the cosmic microwave background, CMB, the afterglow of the Big Bang. These fluctuations, while minuscule, were not random, but had profound consequences. They acted as the seeds for the large-scale structures, like galaxies and clusters, that populate the universe today. Without inflation, the patterns in the CMB would be difficult to explain. After all, in a universe expanding so rapidly, regions separated by vast distances would not have been able to communicate or influence each other. Therefore, while the Big Bang Theory helps us understand the birth of the universe and its early conditions, inflation theory provides an essential framework for understanding the uniformity and grand scale of the cosmos, bridging gaps left unexplained by the original model. Together, they offer a more complete picture of a dynamic and ever-evolving universe, shaped by processes that began almost instantaneously after its birth. Another cornerstone of our understanding of the universe is quantum mechanics, a fundamental theory that governs the behavior of particles at the smallest scales, such as atoms and subatomic particles. When we delve into the very origins of the universe, quantum mechanics plays a pivotal role, especially in the moments immediately following the Big Bang. Imagine a point in time when the universe was infinitely hot and dense. Under these extreme conditions, the familiar laws of classical physics, which describe the behavior of larger objects, began to break down, and the bizarre rules of quantum mechanics took over. Quantum mechanics reveals a reality that is not only strange, but also deeply counterintuitive. For example, particles can exist in multiple states simultaneously, behaving as both waves and particles. This weirdness allows for randomness and uncertainty at the smallest scales, which turns out to be incredibly important for the formation of the universe. One of the fascinating aspects of quantum mechanics is the concept of energy fluctuations. At the birth of the universe, tiny fluctuations in energy could have occurred, leading to small variations in density across space. These fluctuations became crucial seeds for the formation of the galaxies, stars, and other cosmic structures that we see today. Without these initial variations in energy, it would be hard to explain how a diverse and complex cosmos emerged from such a uniform state. Furthermore, quantum mechanics introduces the concept of the quantum vacuum. Not an empty void, but a space filled with potential energy. This vacuum can spontaneously generate particles in a phenomenon known as quantum fluctuation. These fluctuations may have been integral to the rapid expansion of the universe during the period of cosmic inflation. During this time, the universe grew exponentially, smoothing out initial irregularities and setting the stage for the large-scale structures we observe today. Quantum mechanics helps us understand how the fabric of reality itself can change under extreme conditions. It also shows how minute differences in the early universe could lead to the intricate and diverse cosmos that has emerged, with galaxies, stars, planets, and life itself. These quantum fluctuations at the universe's dawn were not just random noise, but the fundamental building blocks for everything we see in the universe today. Across human history, different cultures and civilizations have crafted their own narratives about the origins of the universe. These myths and beliefs, often rich in symbolism, reflect the worldviews and values of the societies that produced them. For instance, many indigenous cultures view the cosmos as deeply connected to nature. Their creation stories often involve powerful beings or spirits that shape the world, emphasizing harmony and balance with the earth. Creation in these traditions is not seen as a singular event, but as an ongoing process of relationship with the natural world. In the ancient Near East, particularly in Mesopotamia, myths describe a chaotic primordial void from which gods emerged to bring order to the universe. The Sumerians, for example, spoke of a freshwater sea mixing with salt water to create life and the heavens. These stories illustrate the age-old human struggle to make sense of an unpredictable and seemingly chaotic world, giving rise to creation myths that blend metaphysical questions with the forces of nature. Meanwhile, in Hindu cosmology, the universe is not viewed as having a singular beginning or end, but rather as a cyclical process of creation, preservation, and destruction. According to this tradition, the universe starts in a cosmic ocean, where a divine being rests. Upon awakening, this being begins the process of creation, and the universe expands and contracts in an eternal cycle. This view emphasizes the idea that creation is not a one-time event, but part of an ongoing rhythm of birth and rebirth. The ancient Greeks, too, contributed significantly to cosmological thought. Philosophers like Plato debated the nature of existence, introducing concepts such as the realm of perfect forms. These early cosmological ideas sought to understand the material world through logic and observation, providing the intellectual foundations for Western thought and influencing centuries of philosophical inquiry. In contrast, many indigenous African traditions emphasize the power of language in the creation of the world. The stories often tell of a high god who creates the universe through the spoken word. These myths highlight not only the connection between the divine and the earthly realm, but also underscore the profound relationship between language, morality, and human existence. Despite these diverse cultural narratives, one common theme emerges: the human need to understand the universe's origins and the forces that shaped it. These stories provide not only answers to questions about our beginnings, but also offer insights into the values, beliefs, and cultural identities of the societies that created them. Finally, the question of dark matter remains one of the most intriguing puzzles in modern cosmology. Dark matter is a mysterious and invisible substance that makes up about 26% of the universe's total mass. Although it cannot be directly observed or measured using conventional tools, its existence is inferred through its gravitational effects on visible matter. Imagine standing in a room where you can't see anything, but you can sense that the room is full. The space feels occupied, even though you can't touch or see what's there. This is similar to the role of dark matter. Though it doesn't emit, absorb, or reflect light, scientists know it must be present because of its influence on galaxies and other cosmic structures. For example, when scientists observe galaxies, they move much faster than they should, given the mass of the visible matter alone. It's as if something unseen is exerting extra gravitational force, keeping everything in balance. Without dark matter, galaxies wouldn't hold together the way they do, and the universe's large-scale structure would look very different. One of the primary methods scientists use to study dark matter is through its gravitational effects. For example, by observing how galaxies move and cluster together, astronomers can infer the presence of dark matter. Another tool in the search for dark matter is gravitational lensing. This occurs when light from a distant galaxy passes near a massive object like a galaxy cluster. The gravity of the object bends the light, distorting the image of the distant galaxy. By studying these distortions, scientists can determine the amount of dark matter present in the massive object, even though the dark matter itself remains invisible. Dark matter continues to captivate scientists, and the ongoing search to understand it could hold the key to unlocking many of the mysteries surrounding the universe's history, its expansion, and its underlying principles. Beneath the Earth's surface, a series of extraordinary experiments are taking place in the shadowy depths of underground laboratories. Here, in environments far removed from the chaos of cosmic rays and other cosmic disturbances, scientists have constructed specialized detectors designed to capture the most elusive of all particles: dark matter. These detectors are extraordinarily sensitive, isolated in deep underground caverns to avoid any interference from the constant bombardment of cosmic radiation. The goal? To detect faint interactions between dark matter and regular matter, an endeavor that would provide a glimpse into the most mysterious substance in the universe. Dark matter, although invisible and undetectable by traditional telescopes, is believed to make up around 27% of the universe's total mass. Its existence is inferred not through direct observation, but through the profound gravitational effects it exerts on visible matter. These effects are so strong that they alter the very structure and behavior of galaxies and galaxy clusters. For instance, the rotation speeds of galaxies, the movements of galaxy clusters, and the bending of light in space all point to the presence of this unseen force. Without dark matter, galaxies would fly apart, unable to hold themselves together, yet here they are, existing and rotating at speeds that seem impossible without the unseen hand of dark matter holding them in place. However, if scientists were to conclusively prove that dark matter does not exist, if experiments reveal that it is but a figment of our scientific models, then we would face a radical shift in our understanding of the cosmos. The implications would be profound, forcing a complete rethinking of the laws that govern everything from the motion of galaxies to the way light bends in space. Such a revelation would challenge the very framework of modern physics, prompting researchers to reconsider the nature of mass, gravity, and the formation of galaxies. At the heart of this rethinking lies the issue of mass, the mass we can see, such as stars and planets, and the mass we cannot, which we infer through gravitational effects. If dark matter were eliminated from the equation, scientists would likely turn to alternative theories to explain these phenomena. One such possibility is the theory of modified gravity. This would involve tweaking the established laws of motion and gravitation to account for the peculiar behavior of galaxies and galaxy clusters. This approach could give rise to entirely new models of the cosmos, with experiments designed to test these new frameworks and potentially open up fresh, unexplored avenues in astrophysics. But the questions do not end there. The discovery or the disproving of dark matter would have consequences far beyond the realms of theoretical physics. It could reshape our very understanding of the universe's history, its composition, and its fate. If dark matter were proven to be a mirage, then scientists would have to delve even deeper into the nature of the universe's forces. The quest for answers would likely ignite a new wave of exploration, as researchers grapple with questions that have the potential to change everything we know about existence. In this cosmic puzzle, dark matter is not the only mystery that haunts the minds of scientists. There is also dark energy, a completely different phenomenon that plays an equally crucial role in the fate of the universe. While dark matter is like the invisible glue that holds galaxies together, dark energy works in an entirely different way. It is the force responsible for the accelerated expansion of the universe. Imagine for a moment blowing air into a balloon. As the air fills the balloon, it stretches, expanding and pushing the surface farther and farther apart. Dark energy functions in much the same way, pushing galaxies away from one another and causing the expansion of the universe to speed up over time. This expansion is counterintuitive, given what we know about gravity. Gravity, the force that pulls objects together, would naturally slow the expansion of the universe. In the early moments after the Big Bang, gravity dominated and the universe's expansion slowed down. Yet over time, something strange began to happen. The expansion of the universe began to accelerate, as if something were working against gravity itself. This something was named dark energy, and it is now thought to account for about 70% of the universe's total energy. Despite its overwhelming influence on the cosmos, dark energy remains elusive. It has never been directly observed, and scientists are still struggling to understand what it is and how it works. One of the most intriguing aspects of dark energy is that it appears to be a kind of anti-gravity, a force that pushes everything in the universe apart rather than pulling it together. As a result, galaxies are receding from one another at an accelerating rate, leading to what scientists call the Big Freeze scenario, in which the universe continues to expand indefinitely, eventually leaving stars to burn out and galaxies to drift apart. But what exactly is dark energy? Its true nature remains one of the greatest unsolved mysteries in modern cosmology. Some theories propose that dark energy is linked to the vacuum of space itself, a form of energy that arises from the very fabric of empty space. Other theories suggest that dark energy might be a sign of entirely new physics, waiting to be discovered. Whatever its true nature, dark energy is crucial for understanding the future of the universe. If its influence continues to dominate, it could ensure that the universe expands forever, never slowing down and never contracting. Scientists are actively seeking ways to study dark energy and gain insights into its role in the universe's evolution. One of the most effective tools at their disposal is the observation of distant supernovae, exploding stars whose light can be used as a cosmic yardstick. By measuring how quickly these supernovae are moving away from us, scientists can gauge the rate of expansion of the universe and, in turn, infer the presence of dark energy. Another crucial method involves large-scale surveys of galaxies. By mapping the distribution of galaxies across vast stretches of space, scientists can observe how they cluster and move apart, offering more clues about the underlying influence of dark energy. The study of the cosmic microwave background radiation, the faint afterglow of the Big Bang, is also helping to unravel the mysteries of dark energy. Tiny fluctuations in this radiation carry vital information about the universe's early moments and the forces at play in its formation. Additionally, the detection of gravitational waves, ripples in the fabric of space-time caused by the collision of massive objects, offers another avenue for understanding the role of dark energy in shaping the universe. In the search for answers, one thing is clear. Whether it is dark matter or dark energy, these invisible forces are not just intriguing. They are fundamental to our understanding of the cosmos. As scientists continue to probe the deepest mysteries of the universe, their work may eventually uncover truths that not only redefine our knowledge of the universe, but also illuminate the very nature of reality itself. The quest for understanding is far from over, and as we continue to push the boundaries of our knowledge, the universe's secrets may be closer than ever to being revealed. The role of computer simulations in understanding the universe's most mysterious forces is undeniable. These simulations are critical tools that help recreate the expansive and dynamic nature of the cosmos under varying conditions, offering a deeper insight into the uncharted territories of dark matter and dark energy. With their ability to model the universe's evolution across time, these simulations allow researchers to test diverse theories and models of dark energy, while simultaneously uncovering the properties that govern its existence. As a result, through the combined efforts of simulation, observation, and theoretical work, scientists are slowly piecing together the enigma of dark energy and its immense influence on the cosmos. Dark energy, although invisible and intangible, is one of the most significant forces that shape the universe. It is the mysterious force behind the accelerated expansion of the universe, pushing galaxies farther apart at an ever-increasing rate. Understanding dark energy is pivotal, not just for explaining the present state of the cosmos, but for offering a glimpse into its future. Will the universe continue to expand indefinitely, or is there a possibility of its expansion slowing down, halting, or even reversing in the distant future? By answering these questions, scientists could fundamentally alter our understanding of cosmic evolution, providing insights into the fate of everything in existence. Equally perplexing is dark matter, another invisible component of the universe. Comprising about 27% of the cosmos, dark matter cannot be directly seen. We only know it exists because of its gravitational effects on the objects around it. It acts like a kind of invisible glue, influencing the motion of galaxies and helping them stay intact. Without dark matter, galaxies would fly apart due to their own rotational velocities. If scientists were to unravel the true nature of dark matter, it could potentially illuminate how galaxies formed, how they evolved over billions of years, and how matter itself behaves on a universal scale. The discovery of dark matter would not just explain cosmic phenomena, but could also lead to a deeper understanding of the universe's large-scale structure. While dark energy and dark matter represent fundamental mysteries that challenge our current understanding of physics, they are far from the only cosmic enigmas. Black holes, for instance, remain some of the most fascinating and perplexing objects in the universe. A black hole is a region of space with gravitational forces so intense that not even light can escape its grasp. To truly comprehend how black holes form, we must first look at the life cycle of a massive star. Stars are born from clouds of gas and dust that collapse under the influence of gravity. During their lifetimes, they undergo nuclear fusion, converting hydrogen into helium and releasing energy that counteracts the force of gravity, keeping the star stable. However, when a massive star exhausts its fuel, the balance between the outward pressure from fusion and the inward pull of gravity is lost. The core of the star collapses under extreme gravitational pressure, leading to an explosive event known as a supernova. This explosion ejects the outer layers of the star, while the core is left behind. If the remaining core is heavy enough, several times the mass of our sun, it continues to collapse into an incredibly dense point known as a singularity, surrounded by an event horizon. The event horizon is the boundary beyond which nothing, not even light, can escape. It marks the point of no return. Once anything crosses this line, it is inexorably drawn toward the singularity at the center, where the laws of physics as we know them cease to function normally. The intense gravitational field warps both space and time, creating extreme distortions that we can only begin to grasp. Black holes also form through other processes, such as the collision of neutron stars or the accumulation of vast amounts of gas and dust that collapse under their own weight. Once a black hole is formed, it can grow even larger by merging with other black holes or by consuming surrounding stars and matter, continuing to increase in mass. Despite their intriguing nature, black holes present significant challenges to our understanding of physics. They serve as a meeting point for two of the most fundamental theories of the universe: general relativity and quantum mechanics. Albert Einstein's theory of general relativity explains the behavior of gravity on a large scale, describing how massive objects like black holes warp the fabric of space-time around them. It shows how gravity can pull matter together so strongly that not even light can escape. Quantum mechanics, on the other hand, governs the behavior of the tiniest particles, dictating how the fundamental forces of nature work on the smallest scales. The problem arises when these two theories are applied to the singularity at the center of a black hole. At this point, where gravitational forces are extreme and space-time is infinitely warped, general relativity breaks down and quantum mechanics fails to provide clear answers. The central issue surrounding black holes is the fate of information. According to quantum mechanics, information cannot be destroyed. However, when matter falls into a black hole, it seems that the information about its state is lost once it crosses the event horizon. This paradox, the so-called black hole information paradox, has been a source of intense debate among physicists. Does the information vanish forever, or is it somehow encoded on the surface of the event horizon? Resolving this paradox is one of the greatest challenges in theoretical physics, as it could lead to a deeper understanding of how gravity and quantum mechanics intersect. The study of black holes could ultimately provide profound insights into the nature of reality itself. By understanding how black holes work, we might unlock new laws of physics that could radically reshape our comprehension of space, time, and the universe at large. In many ways, the event horizon of a black hole represents a boundary not just in space, but in our understanding of the universe. As we explore these cosmic giants, we may be able to test the limits of our current theories, leading to groundbreaking discoveries in both cosmology and particle physics. The event horizon plays a crucial role in shaping our understanding of black holes. It marks the point at which the gravitational effects of a black hole become so overwhelming that nothing can escape, not even light. As an object approaches the event horizon, time itself seems to slow down, and from the perspective of an outside observer, it appears to freeze in place just before crossing the threshold. This phenomenon offers a stark reminder of the strange and often paradoxical nature of black holes, where the very fabric of space and time is distorted. The study of black holes also sheds light on some of the most profound questions in physics. For instance, when a black hole forms from the collapse of a star or the merging of two stellar remnants, it sends out ripples through spacetime, gravitational waves, that can be detected by sophisticated instruments like LIGO, Laser Interferometer Gravitational Wave Observatory. These ripples carry valuable information about the nature of black holes and the events that led to their formation, allowing scientists to peer into previously invisible aspects of the cosmos. Ultimately, black holes serve as natural laboratories for testing the limits of our understanding. By studying the ways in which black holes interact with their surroundings, scientists can observe how matter behaves under extreme conditions. The radiation emitted as matter falls into a black hole provides insights into the properties of these enigmatic objects, such as their mass, spin, and electric charge. These observations, along with the detection of gravitational waves, are helping to expand our knowledge of black holes, dark matter, dark energy, and the fundamental forces that govern the universe. Black holes offer profound insights into some of the most mysterious and fundamental aspects of our universe, including the elusive phenomena of dark matter and dark energy. These enigmatic components, which constitute the majority of the cosmos, remain largely unknown to us. By studying how black holes interact with their environments, scientists are beginning to unlock the secrets of these forces, which seem to govern the universe's very expansion. Black holes, far from being mere cosmic endpoints, are actually integral to our understanding of the universe, acting as pivotal gateways to exploring the origin, structure, and ultimate fate of the cosmos itself. At the very core of a black hole lies the concept of the singularity, a region where gravity becomes so intense that even light cannot escape. As matter collapses into this point, density approaches infinity, and the fabric of space-time curves beyond measure. This idea challenges our most basic understandings of physics. Current theories, such as Albert Einstein's general theory of relativity, fail to describe the extreme conditions at a singularity. While general relativity excels in explaining cosmic phenomena on a large scale, it falters when trying to account for the immense forces present within a black hole. This gap in understanding has led to a range of interpretations, sparking new questions about the very nature of reality itself. Furthermore, the singularity presents a paradox when considered alongside quantum mechanics, the branch of physics that governs the behavior of the smallest particles in the universe. Quantum mechanics, with its counterintuitive principles, often seems incompatible with the extreme gravity of black holes, creating a conflict between the laws of the very small and the very large. Scientists are actively searching for a unified theory that could merge these two realms of physics, but as of now, no such theory has been found. This gap between the two could suggest that new, yet-to-be-discovered laws of physics could await us, offering entirely new ways of understanding the universe. One of the most intriguing and unresolved mysteries surrounding black holes involves the nature of information. When objects fall into a black hole, they appear to vanish completely. This raises a critical question. Is the information contained within those objects lost forever? This paradox, often called the information loss paradox, has sparked intense debate among scientists. Some suggest that information may not be entirely lost, but rather encoded in some way, possibly on the event horizon, the boundary beyond which nothing can escape a black hole's gravitational grip. However, this idea remains speculative and unproven. The singularity and the questions it raises forces us to reconsider everything we think we know about space, time, and existence. It encourages not only scientists, but also philosophers to stretch the limits of their imaginations and theories. As research continues to evolve, the singularities at the heart of black holes may reveal secrets that push the boundaries of our knowledge, leading us to a deeper understanding of the universe itself. Beyond these philosophical and theoretical concerns, black holes also play a crucial role in the very structure and evolution of galaxies. There are two primary types of black holes: stellar black holes, which form from the remnants of massive stars that have exploded, and supermassive black holes, which reside at the centers of most galaxies, including our own Milky Way. These supermassive black holes can be millions or even billions of times more massive than our Sun, and their influence on their host galaxies is profound. The gravitational pull of a supermassive black hole affects not only the movement of stars within its galaxy, but also the gas and dust surrounding it. As matter is drawn into the black hole, it releases vast amounts of energy in the form of radiation and powerful jets of particles that can extend far beyond the galaxy's core. This process can heat up nearby gas, affecting star formation and influencing the evolution of the galaxy. In fact, the presence of a supermassive black hole can stabilize or destabilize a galaxy's structure, influencing the birth of new stars and the fate of existing ones. In addition to shaping the dynamics of stars, black holes also play a role in the overall gravitational structure of a galaxy. The massive pull of a supermassive black hole helps maintain the orbits of star clusters, keeping the galaxy intact over time. The interactions between the black hole and surrounding stars can also lead to the migration of stars. Some of them might be drawn closer to the black hole, while others could be ejected into the vastness of space. Black holes are also intimately connected to the evolution of galaxies. When galaxies collide or merge, their supermassive black holes may eventually converge, leading to the formation of an even larger black hole. This merger produces gravitational waves, ripples in the fabric of space-time, that can be detected across vast distances. As black holes grow and evolve, they can influence the rate of star formation in their host galaxies, creating a feedback loop that dictates the future trajectory of galaxy growth. In this way, black holes are not just destroyers of matter, but also essential architects of cosmic evolution. While black holes remain unseen directly by the human eye because they do not emit light, we have devised clever ways to detect their presence and study their effects. One of the most remarkable breakthroughs in black hole research came in 2019 when scientists captured the first ever image of a black hole's shadow. This particular black hole resides in the galaxy M87, located billions of light years away. To obtain this image, astronomers used a network of radio telescopes around the world, effectively creating a planet-sized telescope. By combining the data collected from these telescopes, scientists were able to visualize the shadow cast by the black hole against the glowing material surrounding it, providing an unprecedented look at one of the universe's most mysterious objects. In addition to capturing images, scientists also study the orbits of stars around black holes. By observing how these stars move in response to the black hole's gravity, astronomers can infer the mass and other properties of the black hole itself. These observations allow researchers to deduce not only the existence of black holes, but also to gain a deeper understanding of their nature. Technological advancements have revolutionized our ability to study black holes, enabling us to peer deeper into their mysteries than ever before. The development of powerful telescopes has allowed scientists to observe the universe across various wavelengths of light, such as infrared and radio waves, which can penetrate cosmic dust and reveal hidden objects. This capability provides new insights into the environments surrounding black holes, allowing for a clearer understanding of their behavior and their impact on nearby matter. Another breakthrough comes in the form of advanced imaging techniques and sensors that allow astronomers to capture increasingly detailed images of black holes and their environments. The Event Horizon Telescope, which produced the first ever image of a black hole's shadow, is a prime example of how technological advancements are pushing the boundaries of what we can observe. As these technologies continue to improve, we can expect even sharper images, offering us deeper insights into the inner workings of black holes. Computational power has also expanded dramatically, allowing researchers to simulate black hole dynamics with unprecedented accuracy. These simulations help visualize complex phenomena such as the collision of two black holes or the behavior of matter near the event horizon. By comparing simulation data with real-world observational data, scientists are able to test and refine their theoretical models. Machine learning, another cutting-edge technological tool, is becoming increasingly valuable in black hole research. By training algorithms to recognize patterns in vast amounts of astronomical data, researchers can identify black holes more quickly and efficiently. This rapid data analysis allows for the discovery of new black holes and provides new avenues for studying their evolution. Together, these technological advancements are not only reshaping our understanding of black holes, but also transforming our entire approach to understanding the fundamental laws of physics. As we continue to push the boundaries of our knowledge, black holes may hold the key to some of the universe's most profound secrets, revealing new truths about gravity, the nature of space-time, and the very essence of reality. Finally, the concept of the multiverse, the idea that our universe is just one of many, offers a fascinating and speculative perspective on the cosmos. Imagine our universe as a single bubble floating in a vast ocean of bubbles, each representing a different universe, potentially governed by its own unique laws of physics and dimensions. Some of these parallel universes might resemble our own, possibly even containing alternate versions of ourselves. Others could be vastly different, where the very rules of existence diverge in unimaginable ways. One avenue through which scientists explore the idea of the multiverse is quantum mechanics. In this realm, particles can exist in multiple states simultaneously until they are observed. This strange phenomenon gives rise to the many worlds interpretation, which suggests that every decision or event creates new branches, resulting in a multitude of parallel realities. Another perspective on the multiverse is rooted in the theory of cosmic inflation, which describes the rapid expansion of the universe shortly after the Big Bang. Some scientists propose that different regions of space expanded at different rates during this period, leading to the creation of separate bubble universes, each with its own unique properties. While the multiverse theory remains speculative, it has sparked fascinating debates within the scientific community. There is no direct evidence to support the existence of parallel universes, but some discoveries, such as the cosmic microwave background radiation, hint at a complex and vast early universe. If the universe underwent inflation, it could have created multiple regions with distinct characteristics, potentially giving rise to a multiverse. In this way, the theory challenges our understanding of reality itself, suggesting that there may be far more to existence than we can currently measure or comprehend. String theory, an ambitious framework in theoretical physics, is designed to reconcile two of the most successful yet contradictory theories in physics: general relativity, which explains the force of gravity on large scales, and quantum mechanics, which governs the behavior of particles on the smallest scales. However, string theory introduces something even more astonishing: the possibility of multiple dimensions, far beyond the familiar 3 dimensions of space and 1 dimension of time that we experience daily. In this view, our universe may be just one of many, each existing with its own distinct physical properties, laws of physics, and even histories. These extra dimensions could open the door to a multiverse, a vast, possibly infinite landscape of universes, each with a unique set of characteristics. Yet, despite the tantalizing implications, the multiverse theory faces considerable challenges. One of the most significant hurdles lies in the fact that these other universes, if they exist, could be completely isolated and unobservable from our own. This renders direct empirical evidence for their existence virtually impossible to obtain. Science, at its core, relies on observation and testability, and without a means to confirm or deny the existence of these other universes, the multiverse theory remains speculative. For now, it exists more in the realm of theoretical physics than in the domain of proven science. At the heart of this speculation lies the fine-tuning problem, which asks why our universe seems so perfectly set up to support life. The constants of nature, such as the strength of gravity or the mass of elementary particles, appear to be finely tuned to allow for the existence of life. Some proponents of the multiverse theory argue that if there are indeed many universes, each with different laws and constants, it becomes statistically likely that at least one would have the right conditions for life. In this context, our universe's suitability for life could simply be a matter of chance, a product of the sheer number of possible universes. However, critics of the multiverse hypothesis contend that this reasoning is insufficient, as it assumes that we can assign meaningful probabilities to scenarios that are not directly observable and thus lack empirical support. Despite the lack of definitive proof, there are intriguing theoretical frameworks and some indirect evidence that suggest the multiverse might be more than just a philosophical idea. The search for understanding the true nature of our universe continues to propel theoretical physicists into exciting and challenging territory, raising profound questions about the very fabric of reality. If the multiverse theory is proven true, it would radically transform our understanding of existence. Traditionally, we have thought of our universe as a singular, isolated entity, with everything we know contained within it. The laws of physics, from the behavior of subatomic particles to the movements of galaxies, govern the universe uniformly. However, the multiverse theory shatters this notion by suggesting that there might be not one, but many universes existing simultaneously, each with its own set of rules. Imagine our universe as a small island in a vast archipelago, with each island representing a different universe. This raises a question that has intrigued scientists and philosophers for centuries. Is our universe unique, or is it just one of many, coexisting with others in a more complex reality? The implications of the multiverse are profound, stretching far beyond the realm of physics. If each possible outcome of every event creates a new universe, then every decision, no matter how small, could lead to the creation of a new reality. In this view, life itself becomes a vast and ever-expanding web of possibilities, with each individual decision branching off into a new universe. Some of these universes might be nearly identical to ours, with only subtle differences. Others, however, could be drastically different, potentially harboring alien life forms, alternate forms of matter, or even entirely new laws of physics. This raises further questions about the nature of existence and individuality. If there are infinite versions of ourselves, making infinite variations of the same choices, then what does it mean to be unique? Does our life, with its distinct choices and experiences, hold the same meaning if it is mirrored by an infinite number of parallel versions of ourselves in other universes? If the multiverse exists, then our reality might just be one possibility among countless others, each with its own version of us, leading lives that range from eerily similar to radically different. The multiverse theory also addresses the fine-tuning problem in a more expansive way. If there are many universes, it is not surprising that one might have the ideal conditions for life. We just happen to exist in the one that does. In this way, the theory reshapes our understanding of existence itself, suggesting that the very fact that our universe allows life to thrive might be a mere accident of which universe we inhabit in the vast multiverse. However, proving the existence of the multiverse would not be a simple task. If these other universes are truly isolated and unobservable, how can we gather empirical evidence for their existence? For the multiverse theory to be scientifically valid, new methods of investigation would need to be developed, ones that can explore realities beyond our own, perhaps through indirect observations or entirely new technologies. On a more existential level, the confirmation of the multiverse could profoundly alter our sense of significance in the cosmos. If every conceivable reality exists, what does it mean for our individual lives? The discovery of the multiverse could lead people to reassess the importance of their actions, seeing them not as unique, but as part of a broader spectrum of possibilities. This shift in perspective could inspire deep philosophical reflections about fate, free will, and the meaning of life itself. If every choice and every event creates new realities, then is there any true finality to any decision? The multiverse would present an entirely new way of thinking about purpose, existence, and identity. There are several different models of the multiverse, each offering a distinct perspective on how these universes might be formed and what they might look like. One of the most widely discussed models is the bubble universe theory, which likens the multiverse to a growing foam of bubbles. In this scenario, each bubble represents a separate universe with its own physical properties. Some bubbles might support life, while others may not. The bubbles float independently, with no interaction between them. This suggests that the universe we know is just one of many, each existing separately in its own corner of the multiverse. Another intriguing model is the many worlds interpretation, which arises from the principles of quantum mechanics. According to this theory, every time a quantum event occurs, all possible outcomes are realized, but in separate, branching universes. For example, if you make a decision, one universe follows one path and another follows a different path. This means that every possible outcome creates a new universe, leading to an infinite number of realities that exist concurrently. This perspective paints the multiverse as a vast tree of possibilities, with each branch representing a different outcome of a quantum event. A third possibility comes from string theory, which posits that the universe is made up of tiny vibrating strings. According to this model, each universe in the multiverse is the result of different vibrations of these strings, leading to variations in physical laws and dimensions. This would imply that the multiverse is not simply a collection of isolated universes, but rather a patchwork of realities, all existing within the same overarching framework of string theory. Finally, some versions of the multiverse theory are based on cosmic inflation, the rapid expansion of space that occurred just after the Big Bang. According to this model, different regions of space expanded at different rates, creating pocket or island universes within an ever-expanding multiverse. Each of these pocket universes could develop its own unique properties and laws, creating a dynamic and ever-growing multiverse. Each of these models provides a unique perspective on the multiverse, contributing to a richer and more complex understanding of the cosmos. While they differ in their specifics, they all share a common thread: the notion that our universe is not the only one, and that existence itself may be far more intricate and interconnected than we ever imagined. The multiverse theory invites us to imagine a universe, or rather, a collection of universes, that extends far beyond the confines of our own reality. It is a concept that captivates the imagination and challenges our understanding of everything from the laws of physics to the nature of existence itself. The idea of the multiverse opens up a world of possibilities. Imagine every choice you've ever made, every event that has unfolded, not leading to a single path, but branching into countless realities. Each universe may have its own version of physical laws, varying constants, or even entirely different timelines. This concept compels us to reconsider the nature of existence. What if there are worlds where you made different decisions, or where certain events didn't happen at all? The potential is limitless, and the more we delve into the mysteries of the multiverse, the more we realize how much we have yet to understand about the cosmos. The multiverse theory presents an exhilarating frontier in modern cosmology, yet it also stands at the center of intense debate, challenging not only our scientific understanding, but also the very boundaries of what we consider possible. At its core, the idea that multiple, perhaps infinite universes could exist, parallel to our own, pushes the limits of traditional scientific thinking. This theory seems to step beyond the conventional methods of observation and experimentation, relying on concepts that lie outside the scope of direct empirical testing. Such a radical proposition raises significant questions about the nature of science itself. Is the multiverse concept more akin to speculative philosophy, or can it be validated through rigorous scientific methods? Critics argue that without the ability to observe or test these alternate realities, the idea remains nothing more than a fascinating but untestable hypothesis, teetering dangerously close to the realm of science fiction. Yet, despite the skepticism, the allure of the multiverse is undeniable. It offers an opportunity to explore not just the universe we inhabit, but also the very fabric of reality itself. In traditional scientific inquiry, observation is a cornerstone. Science relies on the ability to observe, test, and replicate. However, in the case of the multiverse, our current tools and technologies do not allow us to directly observe these other realms. So how can we engage with something that eludes direct perception? This tension between the limits of scientific observation and the boundless possibilities of theoretical exploration makes the multiverse an especially captivating, if contentious, subject in both the scientific and philosophical domains. The multiverse theory suggests that our universe may simply be one among many, each governed by its own set of physical laws and constants. Imagine a scenario where the constants of physics, such as the strength of gravity or the charge of an electron, are not fixed but vary across different universes. In some, the laws of physics may be unrecognizable to us, while in others, they may mirror our own universe. If such a theory holds, it could radically alter our understanding of fundamental scientific puzzles. Take, for example, the mysterious phenomena of dark matter and dark energy, which continue to perplex cosmologists. In a multiverse framework, these enigmatic forces might behave differently across universes, offering alternative explanations for their elusive nature and possibly helping us unlock the secrets of their existence. Beyond dark matter and dark energy, the multiverse invites us to rethink our conception of the universe's origin. Instead of searching for a single cataclysmic event that set everything in motion, the idea of a multiverse suggests that our universe may be just one of countless outcomes, each branching off from different initial conditions. This perspective challenges the traditional Big Bang model and expands our view of the cosmos as a landscape of infinite possibilities. If the universe is just one thread in a vast tapestry of multiversal creation, then the answers to some of our most profound questions about the origin of life and the nature of existence may lie not in a singular event, but in a broader, more complex series of cosmic developments. Such a view encourages scientists to embrace creative, even speculative, solutions to long-standing mysteries, pushing them to look beyond the limits of the observable universe and think in terms of infinite potential outcomes. Furthermore, the multiverse theory has profound implications for discussions surrounding the fine-tuning of the universe. Why the constants and conditions in our universe are seemingly perfect for the emergence of life. If an infinite number of universes exist, each with varying physical conditions, the existence of a universe like ours, one that supports life, becomes statistically inevitable. The theory offers a shift in perspective, suggesting that it is not the result of some special one-time event, but rather the product of countless possibilities, some of which naturally lead to life-supporting environments. From this statistical view, our universe's life-friendly constants become less remarkable and more a natural consequence of an overwhelmingly diverse multiversal landscape. Another significant area where the multiverse could offer new insights is in reconciling two of the most foundational but currently incompatible theories in physics, quantum mechanics and general relativity. These two pillars of modern science, one governing the subatomic world and the other the macroscopic fabric of space-time, currently fail to align. Quantum mechanics explains the behavior of particles at the smallest scales where probabilities reign, while general relativity describes the gravitational interactions of massive objects and the curvature of space-time at large scales. The tension between these two frameworks has long posed a challenge for physicists. The multiverse theory, however, could provide a bridge between them, offering fresh pathways for reconciling these two seemingly contradictory theories. In this sense, the multiverse isn't just a speculative idea, but a tool for exploring the very nature of reality itself. When we turn our attention to quantum mechanics, we encounter a fascinating lens through which to explore the concept of the multiverse. Quantum mechanics, the science of the very small, introduces the idea of superposition. Particles can exist in multiple states simultaneously. To illustrate this, imagine flipping a coin. While the coin is in the air, it's not just heads or tails. It has the potential to be both at the same time. The concept of superposition challenges our classical understanding of reality, suggesting that multiple possibilities coexist until one is observed. Some interpretations of quantum mechanics propose that rather than collapsing into a single outcome when observed, every possible outcome actually exists in a separate, parallel universe. This is known as the many worlds interpretation, MWI, of quantum mechanics. According to MWI, every time a decision or measurement is made, the universe splits into multiple branches, each corresponding to a different possible outcome. Picture it like a vast branching tree, where each choice leads to a new branch, each with its own unique reality. This interpretation not only challenges our concept of time and space, but also forces us to reconsider the very nature of existence itself. Moreover, the phenomenon of quantum entanglement, where particles can instantaneously affect each other across vast distances, adds a layer of complexity to the multiverse theory. If entangled particles can influence one another across space, could similar connections exist between parallel universes? Could events in one universe have an effect on another, defying the limitations of space and time as we know them? Such possibilities stretch the boundaries of our understanding, offering tantalizing hints that the universe might be far more interconnected and far-reaching than we ever imagined. Of course, while quantum mechanics provides a compelling framework for the multiverse, it also raises more questions than answers. The theory challenges our deepest assumptions about reality and existence, forcing us to confront the vast unknown that lies beyond the observable universe. In many ways, it beckons us to expand our curiosity and embrace the mysteries that might one day illuminate the very nature of the cosmos. In considering time itself, we find yet another dimension of the multiverse theory. Time, often described as the fourth dimension in physics, is essential for organizing our perception of events and understanding the sequence of occurrences that shape our universe. From the Big Bang to the cosmic dance of galaxies, time helps us make sense of change and movement. Yet, in the context of relativity, time is far from absolute. It is relative, meaning that it ticks at different rates depending on the observer's motion and position. For example, a person traveling close to the speed of light would experience time more slowly than someone at rest on Earth. This phenomenon, known as time dilation, illustrates how time is intricately woven into the fabric of space-time itself. Time is not merely a backdrop against which events unfold, but an integral component of the universe's evolution. Time, then, is not just a measure of intervals. It is part of the very structure that governs cosmic events. Understanding time in this broader sense is essential for grasping the dynamic and ever-changing nature of the universe. The notion of time travel captures the imagination and has given rise to many speculative theories, including the idea of wormholes. These hypothetical shortcuts through space-time could, in theory, allow one to travel between 2 points in time. While this concept is captivating, the practical challenges of finding or creating a stable wormhole are immense, leaving this idea firmly in the realm of theoretical physics. Another intriguing theory about time travel revolves around traveling at the speed of light. According to Einstein's theory of relativity, as an object approaches the speed of light, time slows down for that object relative to someone who is stationary. This raises the possibility that traveling at near light speeds could allow someone to experience far less passage of time while the rest of the universe continues as normal. However, reaching such speeds would require an immense amount of energy, far beyond our current technological capabilities, making time travel a distant dream. Finally, there are solutions to Einstein's equations that propose the existence of closed time-like curves, paths through spacetime that loop back on themselves. These theoretical curves suggest that an object could, in principle, return to a previous point in time. However, these scenarios often give rise to paradoxes, such as the famous grandfather paradox, where actions taken in the past could prevent the time traveler from ever existing in the first place. These paradoxes further highlight the complexities and challenges of reconciling time travel with the fabric of reality. In the end, while the multiverse theory remains speculative and controversial, it serves as a powerful catalyst for expanding our understanding of the cosmos. It encourages us to rethink not just the universe we see, but the very nature of reality itself. Whether or not we ever uncover the truth of parallel universes, the journey to explore these possibilities promises to lead us into new realms of scientific discovery, philosophical contemplation, and a deeper understanding of the vast mysteries that lie beyond our current reach. The concept of time is more than just a ticking clock or a unit of measurement. It is an ever-evolving, ever-expanding dimension of the universe, intricately woven into the fabric of existence itself. Philosophers, scientists, and thinkers have long speculated about its nature, and some have even pondered the possibility of parallel universes where time might behave differently, or where travel to the past could open up new realities altogether. One theory suggests that traveling back in time might not alter one's own past, but instead create a new timeline altogether. Imagine, instead of changing the events that shaped you, you step into a different reality, a parallel universe where the events unfold differently. This concept touches on the intriguing possibility of alternate timelines, where each choice and event creates a new branch in the river of time. Yet despite its compelling nature, the existence of such parallel universes remains firmly in the realm of speculation. Scientists and theorists debate its feasibility, and while these ideas offer tantalizing glimpses into what could be possible, the practical reality of such time travel is still very much theoretical. The debate on time travel also brings us to the groundbreaking work of Albert Einstein, whose theory of relativity reshaped our understanding of time. Historically, time was thought to be an absolute, unyielding constant. It was something that flowed steadily no matter where you were or what you were doing. But Einstein's theory introduced a revolutionary idea. Time, far from being a fixed constant, is flexible, shaped by the forces of gravity and speed. To better understand this, imagine two observers, one standing on Earth and the other aboard a spaceship traveling close to the speed of light. The person on the spaceship would experience time at a different rate than the one on Earth. For the traveler, time would seem to pass more slowly, and if they made a long journey at near light speeds and returned home, they would find that more time had passed on Earth than they had experienced. This phenomenon, known as time dilation, challenges our conventional understanding of time, showing us that it is not experienced uniformly by all. Gravity plays an equally critical role in how we experience time. The stronger the gravitational field, the slower time runs. This effect has been observed in the real world, such as with clocks on satellites. These clocks, which orbit far above Earth's gravitational pull, tick slightly faster than those on the ground. In fact, satellites must account for this time difference to ensure the accuracy of GPS systems. The relationship between space and time is profound, and the theory of relativity tells us that time is not an independent force, it is intertwined with the fabric of space itself. This understanding reshapes our perception of reality. Time no longer seems like a static, ever-moving stream, but more like a malleable thread woven into the vast expanse of space. As the universe expands, time and space continue to evolve together, constantly influencing one another. The early moments of the universe, right after the Big Bang, offer a perfect example of how time and space are inextricably linked. As the universe cooled and expanded, both space and time began to evolve. This dual evolution is why distant galaxies appear to be moving away from us. As the space between us and these galaxies expands, their light takes longer to reach us, offering us a glimpse into their past. The expansion of the universe itself, driven by dark energy, is a direct consequence of this dynamic relationship between space and time. The fate of the universe, whether it will continue to expand indefinitely, slow down, or even collapse, depends on the intricate balance of time, energy, and matter. And as we look to the future, understanding the nature of time will be essential in predicting how the universe will evolve. On a much smaller scale, the flow of time also influences our day-to-day lives. A single second may seem like a brief moment in our own experience, but on a cosmic scale, time is fluid, stretching and contracting depending on where you are in the universe. For instance, near massive objects like black holes, time appears to slow down. If you were to stand near such an object, time would pass far more slowly for you than it would for someone far away. Similarly, the faster you travel through space, the slower time would appear to pass for you. If you were to journey at speeds close to the speed of light and then return home, you might find that more time had passed on Earth than you experienced during your journey. These fascinating differences in time perception are not just theoretical concepts, they are real, measurable effects that have been confirmed by experiments. Scientists have observed that time is not uniform across the universe. It is a malleable feature, shaped by the gravitational forces of nearby objects and the speed at which an object is moving. The idea that time can stretch and compress depending on these factors challenges the very notion of time as a constant entity. It suggests that the passage of time is far more dynamic, more complex than we could have ever imagined. But can time exist independently of space? To explore this, we must first understand how time and space are intertwined. In our universe, they are inseparable, joined together in what we call space-time. Think of space-time as a fabric that weaves together the three dimensions of space, up and down, left and right, forward and backward, with the dimension of time. If time could exist separately from space, it would imply that events could occur without a physical location, without a place to be measured. This idea raises fundamental questions. Could change occur in a universe where there is no space for it to happen? Could something evolve or move without a location to occupy? These questions challenge the very fabric of our understanding of the universe. The current laws of physics, which govern everything from the orbit of planets to the ticking of a clock, are based on the inseparability of space and time. If time and space were separate, it would lead to a complete overhaul of our understanding of physics. So such a discovery could suggest new dimensions or types of reality that we have yet to explore. It could transform not only our scientific models, but also our very perception of existence and consciousness. The philosophical implications of time are equally profound. For centuries, thinkers have debated whether time is an objective, universal force or a subjective experience. Some philosophers argue that time exists independently of human perception. They believe it flows steadily, much like a river, regardless of whether anyone is observing it. In contrast, others contend that time is a construct of human consciousness, shaped by our memories and expectations. This perspective suggests that time is not experienced uniformly. It varies from person to person, and how we experience it can be influenced by our emotions, moods, and circumstances. This debate raises fascinating questions about the nature of time itself and how it influences our understanding of life, consciousness, and the universe. Another area of philosophical inquiry revolves around the direction of time. Is time truly linear, moving only in one direction? from the past through the present and into the future. This is known as the arrow of time. Some propose that this unidirectional flow is tied to the second law of thermodynamics, which states that the entropy or disorder of a closed system always increases over time. In simple terms, this means that the universe becomes more disordered as time progresses. Others, however, challenge this view and suggest that time might not flow in one direction at all. They propose that past, present, and future are not distinct, but could be part of a larger interconnected tapestry of time. This idea has profound implications for how we think about causality, free will, and the significance of our actions. The exploration of time extends beyond the boundaries of Western thought, with different cultures offering unique perspectives on its nature. Many ancient civilizations, for instance, viewed time as cyclical, shaped by the rhythms of the cosmos, the rise and fall of the sun, the phases of the moon, the changing of the seasons. In these cultures, time was not a linear progression, but a repeating cycle, where past, present, and future were intertwined, much like the cycles of nature itself. In contrast, Western culture, influenced by the ancient Greeks, has traditionally viewed time as linear, a sequence of events unfolding from one moment to the next. Our quest to understand the universe has led us to explore some of its most mysterious and fundamental aspects. Black holes warp the fabric of space-time, dark matter shapes galaxies without being seen, and dark energy drives the accelerating expansion of the universe. These are not abstract theories. They are realities confirmed through decades of rigorous observation and testing. The universe continues to unfold in ways that challenge our understanding, raising new questions about our place in the cosmos. Are we alone in this vast expanse? Could parallel universes exist? What lies beyond the edge of what we can observe? The origins of the universe itself remain one of the greatest mysteries of all. The Big Bang Theory, which is one of the most widely accepted explanations, posits that the universe began as an incredibly small, hot, and dense point. From this initial state, the universe began to expand rapidly, much like a balloon inflating, creating all the space, time, and matter that we know today. This expansion continues to this day, shaping the cosmos in ways that we are only beginning to understand. Time, in all its complexity, is a key player in this ongoing story. It is both the backdrop against which all events unfold and the force that shapes the very fabric of the universe. Whether we are contemplating the distant past, the present moment, or the unknowable future, time is the thread that connects all things, giving structure and meaning to the vast, ever-expanding universe around us. As the universe began to expand, it cooled down, and over the course of millions of years, particles began to form, coalesce, and eventually come together to create the simplest atoms. This process laid the groundwork for the next monumental stages in cosmic evolution. Gravity, that omnipresent force, acted as a catalyst, pulling together these atoms, forging clusters, and eventually sparking the creation of stars. Over time, these stars, along with the accumulation of gas and dust, combined to give rise to entire galaxies, massive collections of stars and other celestial objects, all bound by gravity. The expansion of the universe didn't stop with the formation of stars and galaxies. It continued to shape the cosmos, stretching space itself, causing stars to move farther apart with time. This unfolding narrative, the birth, expansion, and ongoing evolution of the universe, stems from the framework known as the Big Bang Theory. At its core, this theory suggests that the universe began from a singular point, a dense, incredibly hot mass, essentially a speck smaller than a dot. Around 14 billion years ago, this incredibly concentrated matter exploded outward in a rapid expansion. But this wasn't an explosion in the traditional sense. Rather than a blast of matter flying outward from a central location, it was space itself stretching, pushing everything farther and farther apart in all directions. In those first fleeting moments, the universe was a hot, chaotic soup, teeming with high-energy particles. But as it expanded, it cooled down, allowing the formation of more stable particles, which eventually merged to create the most fundamental elements, hydrogen and helium. Over the course of millions of years, gravity would pull these atoms together, and with this accumulation, the first stars began to ignite, shedding light in a dark universe. Galaxies began to form, swirling masses of stars, gas, and dust, their structures laid down by the forces of gravity. From a primordial haze of energy and particles, the universe slowly evolved into the intricate and diverse cosmos we observe today. The Big Bang Theory doesn't just account for the universe's beginnings, it also offers a plausible explanation for the universe's continuing expansion. When astronomers study the distant reaches of the universe, they notice something remarkable. Galaxies are moving away from us. This observation provides critical evidence that space itself is still stretching, still expanding, in line with what the Big Bang Theory predicted. The universe didn't just begin in an explosion, it continues to stretch, creating new space between galaxies as time marches forward. One of the key pieces of evidence supporting the Big Bang Theory is the cosmic microwave background radiation, CMB. This faint glow, which fills the entire universe, is essentially the afterglow of the Big Bang itself. It is the residual heat from the universe's explosive beginning, cooled and stretched over billions of years, now detectable as faint radiation. This radiation offers a snapshot of the universe as it was when it was just 380,000 years old, long before stars and galaxies had formed. The CMB is one of the clearest pieces of evidence that the universe began from a hot, dense state and has been expanding ever since. Alongside the CMB, the observation of redshift in the light from distant galaxies further supports the Big Bang model. When light from distant galaxies reaches Earth, its wavelength is stretched as those galaxies move away from us. This phenomenon, known as redshift, is akin to the change in pitch you hear as a car passes by with its siren blaring. When the car moves away, the sound drops in pitch. Similarly, the farther a galaxy is, the faster it appears to be moving away, a clear sign that the universe itself is stretching. This observation strongly aligns with the idea that the universe began from a single, extremely hot and dense point and has been expanding ever since. The presence and distribution of light elements like hydrogen and helium in the universe further support the Big Bang Theory. These elements were forged in the first few minutes after the Big Bang, in a process called nucleosynthesis. In those early moments, the universe was so hot and dense that nuclear reactions could occur, forming the simplest and lightest elements. By studying the ratios of hydrogen, helium, and other elements across the universe, scientists can test and confirm predictions made by the Big Bang Theory about the quantities of each element that should exist. Then there's the idea of cosmic inflation, a concept that revolutionized our understanding of the universe's earliest moments. Cosmic inflation proposes that just moments after the Big Bang, the universe expanded exponentially at an unimaginable rate, far faster than we can comprehend. This rapid expansion explains why the universe looks so uniform on large scales. Despite regions of space being far apart, they appear nearly identical in temperature and structure. Without this inflationary period, such uniformity would be difficult to reconcile with the Big Bang Theory. The patterns observed in the cosmic microwave background radiation offer compelling evidence for inflation. Tiny fluctuations in temperature, imprinted on the CMB, are thought to be the remnants of quantum fluctuations in the very fabric of space-time during the universe's earliest moments. These fluctuations were the seeds from which galaxies, stars, and all cosmic structures grew. Without inflation, these fluctuations would have been too small to have had the effects we observe today. While the Big Bang Theory is well supported by a wide range of evidence, it is not without its challenges and controversies. One of the most debated aspects is the exact nature of the first moments of the universe's existence. The period of time right after the Big Bang is incredibly difficult to observe, and there are gaps in our understanding of what transpired during those early moments. This has led some scientists to question whether the Big Bang Theory offers a complete picture of the universe's formation. Another area of contention is the concept of cosmic inflation. While inflation theory helps explain many features of the universe, like its large-scale uniformity and the patterns seen in the cosmic microwave background radiation, it raises its own set of questions. Some researchers argue that the specific conditions required for inflation to occur are not entirely supported by current observations. The lack of direct evidence for inflation has pushed scientists to explore alternative theories that might better explain the universe's birth. Compounding this complexity is the existence of dark matter and dark energy, two mysterious components of the universe that we infer through their gravitational effects but cannot observe directly. These invisible elements are believed to make up most of the mass and energy in the universe, and they play a crucial role in its expansion. However, their true nature remains a profound mystery. Some critics argue that the inability to directly identify dark matter and dark energy challenges the completeness of the Big Bang theory, as it suggests there are unknown forces at play that our current models cannot fully explain. The philosophical implications of the Big Bang theory add yet another layer of complexity. If the universe began with the Big Bang, what does that say about the nature of time itself? Does time have a beginning? And if so, can we even speak of before the Big Bang? What caused this immense cosmic event, if anything? These are questions that touch on the very nature of reality, existence, and causality, and they push the boundaries of scientific inquiry into the realm of philosophy. In this context, the idea of multiple Big Bangs emerges, suggesting that the universe might not be a singular event, but rather part of a never-ending cycle of birth, death, and rebirth. Imagine, if you will, that the Big Bang was not the universe's first birth, but rather the latest in a series of cosmic explosions. Each Big Bang could mark the beginning of a new universe, with its own laws of physics and structures, only to collapse and give rise to another in a continuous cycle. This view aligns with the concept of a multiverse, a collection of interconnected or isolated universes, each following its own distinct cosmic story. If multiple Big Bangs indeed occurred, the implications for our understanding of space, time, and reality would be profound. The universe we inhabit would be just one chapter in an ongoing cosmic narrative. The nature of time itself might be cyclical, with each universe undergoing a birth and eventual destruction, only to be reborn again. This idea challenges our conventional understanding of time as linear and could open the door to entirely new perspectives on the universe's existence. Meanwhile, cosmic inflation theory offers an intriguing explanation for the uniformity of the universe. The Big Bang theory sets the stage for the universe's explosive birth, but inflation helps us understand why the universe appears so smooth and uniform on large scales. After the initial explosion, the universe underwent a rapid expansion that helped smooth out any irregularities. This inflationary period was faster than the speed of light, and it stretched space-time in such a way that it erased any initial imbalances. What we are left with is a universe that, on large scales, appears incredibly uniform and homogeneous, from the distribution of galaxies to the temperature fluctuations in the cosmic microwave background radiation. But at its core, quantum mechanics remains a critical piece of this puzzle. The laws of quantum mechanics govern the behavior of particles at the smallest scales, and they played a crucial role in the formation of the universe. At the time of the Big Bang, the universe was so hot and dense that classical physics couldn't describe what was happening. Instead, the strange and unpredictable behavior of quantum particles became essential in shaping the cosmos. Quantum fluctuations in the early universe, tiny variations in energy levels, were responsible for creating the small irregularities that would later grow into the galaxies, stars, and other structures we see today. These fluctuations were the seeds of cosmic evolution, laying the foundation for the universe's vast complexity. Without them, the universe would have remained a nearly featureless expanse, incapable of giving rise to the intricate structures we observe now. In the end, the origins of the universe remain one of the most captivating mysteries of science. The Big Bang theory, along with its complementary concepts like inflation and quantum mechanics, has brought us closer than ever to understanding how the universe began and evolved. Yet, as we delve deeper into the cosmos, new questions and challenges continue to emerge, reminding us that the journey to unravel the universe's story is far from over. Quantum mechanics opens a window into a strange and fascinating realm, one that challenges our deepest intuitions about the nature of reality. Central to this theory is the concept of the quantum vacuum, a void that is far from empty. Instead, it brims with potential energy, waiting to give rise to particles out of seemingly nothing. This phenomenon, known as quantum fluctuation, plays a pivotal role in the universe's vast and complex tapestry. These fluctuations, tiny yet profound, could have been instrumental in the universe's rapid expansion during a period known as cosmic inflation. Cosmic inflation, occurring just after the Big Bang, was an era of unparalleled growth, where the universe expanded exponentially in mere fractions of a second. This rapid expansion smoothed out the initial irregularities that were present in the early cosmos, setting the stage for the large-scale structures, galaxies, stars, and planets that would later emerge. The principles of quantum mechanics governing this early era provide the keys to understanding how such a complex and organized universe could arise from such simple beginnings. It highlights how, under extreme conditions, the very fabric of reality can bend and warp, creating vast differences from what we observe in our day-to-day lives. It also illustrates the incredible sensitivity of the cosmos, how even the smallest initial fluctuations in energy and matter can snowball, leading to the breathtaking complexity we experience today. Yet, while quantum mechanics offers a scientific lens through which we can peer into the universe's birth, it is not the only perspective. Throughout history, many cultures have sought to explain the origins of the cosmos in their own unique ways, reflecting not just their environment, but also their spiritual beliefs, values, and emotions. These creation stories are rich in symbolism and offer profound insights into the human condition. For example, indigenous cultures often describe the creation of the universe as a deeply spiritual event, one that reflects the interconnectedness of all things. The Earth and the cosmos are seen not as separate entities, but as parts of an intricate web with nature at its core. Powerful beings or spirits are often invoked in these stories, shaping the world in ways that emphasize balance and harmony. Creation is viewed not as a singular event, but as an ongoing process, one that is intimately tied to the cycles of nature and the well-being of the Earth itself. These narratives not only explain the origins of the world, but also teach respect and responsibility towards nature. In ancient Mesopotamia, the myths surrounding the birth of the universe were rooted in chaos and conflict. The Sumerians spoke of a primordial freshwater sea mixing with salt water, from which life emerged, bringing with it the heavens and the earth. This image of the struggle between order and chaos mirrors humanity's ongoing search for understanding in a world that often seems unpredictable and uncontrollable. The gods, emerging from this chaos, were seen as bringing stability and structure to the universe. In contrast, Hindu cosmology presents a cyclical view of the universe, one that is ever expanding and contracting in an eternal dance. Here, the cosmos begins with a vast cosmic ocean, upon which a divine being sleeps. Upon awakening, this being initiates the act of creation, followed by the cycles of birth, preservation, and destruction. This vision of creation emphasizes the notion that beginnings are not finite, but part of an ongoing, eternal process, a dance of existence that never truly ends. The ancient Greeks, renowned for their philosophical contributions, approached the question of the universe's origin with a focus on logic and reason. Philosophers like Plato imagined a world of perfect forms, separate from the imperfect material world we experience. Their musings on the nature of existence, grounded in observation and philosophical debate, have influenced Western thought for millennia. Their cosmological theories sought to explain the relationship between the ideal and the material, laying the foundation for future scientific inquiry. Meanwhile, many indigenous African traditions emphasize the power of language in creation. The universe is often said to have been spoken into existence by a high god, with the spoken word carrying immense power. These creation stories are intertwined with teachings about morality, human existence, and the profound connection between the divine and the everyday world. Through these narratives, we learn that the way we speak and act shapes not just our world, but our very understanding of it. Across all these cultures, one common thread emerges: the enduring human desire to understand our place in the cosmos. While modern science provides a framework for understanding the universe's origins, these ancient stories and beliefs offer a different kind of wisdom, one that speaks to the heart of our humanity. They showcase the diversity of thought across civilizations and the creativity with which we have sought to make sense of the vast, mysterious universe that surrounds us. One of the most intriguing mysteries that modern science has uncovered is the existence of dark matter, a substance that makes up about 26% of the universe but remains elusive to our instruments. Dark matter cannot be seen, touched, or measured using conventional tools, yet its presence is undeniable. Imagine standing in a room where you can barely see anything, but you can feel that the room is full, as though something invisible is exerting a subtle influence on your surroundings. This is similar to how scientists detect dark matter. They infer its presence from the gravitational effects it has on visible matter, such as stars and galaxies. Dark matter is called dark because, unlike ordinary matter, it does not emit, absorb, or reflect light. It is invisible to our telescopes and other instruments that rely on electromagnetic radiation. Yet, its gravitational pull is unmistakable. For instance, when scientists observe galaxies spinning, they notice that they move much faster than expected based solely on the visible mass they contain. It's as if there is an invisible hand pulling on these galaxies, keeping them in motion and preventing them from flying apart. Without dark matter, the universe as we know it would look very different. Stars and galaxies might not be able to hold together, and the cosmic structures we see today might never have formed. Dark matter also plays a crucial role in shaping the large-scale structure of the universe. It acts as a kind of scaffolding, providing a framework around which visible matter can gather and form galaxies, clusters, and other cosmic structures. It is an invisible architect of the cosmos, quietly influencing the expansion and formation of the universe, even though we cannot directly observe it. Detecting dark matter is no easy task, but scientists have developed several ingenious methods to study it. One of the most promising techniques is through its gravitational influence on visible matter. By observing the movement of galaxies and galaxy clusters, scientists can infer the presence of dark matter. If only the visible matter were present, galaxies would move much slower than they actually do. The high velocities at which galaxies move suggest that dark matter is present, exerting a gravitational force that helps hold these galaxies together. Another way scientists study dark matter is through a process known as gravitational lensing. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, the gravity of that object bends the light, creating distorted images. By studying these distortions, scientists can infer the amount and distribution of dark matter in the foreground galaxy cluster, even though the dark matter itself remains unseen. These methods are among the most effective ways scientists are piecing together the puzzle of dark matter. As we continue to explore the universe, dark matter remains one of its greatest mysteries. Its discovery and study may reveal secrets about the universe's history, its structure, and its underlying principles, offering new insights into the very fabric of reality itself. Scientists have long been captivated by the elusive and enigmatic nature of dark matter, and they are now conducting experiments deep underground, using cutting-edge detectors designed to observe the faintest of signals. These detectors are not just built to detect ordinary matter. They are specially shielded from cosmic rays and other forms of interference that could drown out the incredibly weak interactions between dark matter and the matter we are familiar with. These experiments aim to detect the rare instances when dark matter particles collide with atoms, an event so subtle that only the most advanced technology and isolation can allow us a glimpse. While we cannot observe dark matter directly with our eyes or telescopes, its presence is inferred from its powerful effects on the universe's structure and behavior, effects that cannot be explained by any other known forces. Even though dark matter eludes direct detection, its profound influence on galaxies, galaxy clusters, and the cosmos as a whole suggests its existence with striking certainty. The ingenuity of scientists in their quest to uncover the true nature of dark matter showcases the brilliance of modern scientific methods, pushing the boundaries of what we know about the universe and how it works. If, one day, it is conclusively proven that dark matter does not exist, this would send shockwaves through the field of cosmology and beyond, fundamentally altering our understanding of the universe itself. At its core, dark matter is a concept developed by scientists to explain several inexplicable cosmic phenomena. One of the most puzzling aspects is the way galaxies spin and behave. When scientists look at galaxies, they see that the outer regions are rotating much faster than expected, given the visible mass in the galaxy. Without some unseen force, galaxies would fly apart. Dark matter provides the missing mass that holds these galaxies together with its gravitational pull, acting as an invisible glue that prevents these celestial bodies from disintegrating. It does not emit light, nor does it interact with electromagnetic radiation in the same way that ordinary matter does. As such, it remains hidden to our most powerful telescopes and detectors. But what would happen if dark matter were proven not to exist? In such a scenario, researchers would be forced to reconsider the very foundations of physics as they apply to cosmic structures. The current models we have of galaxy formation and behavior would require significant revisions. Much of our understanding of the universe is based on the assumption that dark matter is present, shaping the mass of galaxies and galaxy clusters. Without it, scientists might turn to alternative explanations, one of the most discussed being theories that propose modifications to gravity itself. These ideas, known as modified gravity theories, suggest that the laws of motion and gravitation might need to be adjusted to account for the observed behaviors of galaxies and other cosmic phenomena. This shift in perspective would likely spur a new wave of experiments and explorations into the fundamental laws of nature. It could lead to groundbreaking new theories that would forever alter our understanding of the universe and its behavior. Beyond the realm of theoretical physics, the discovery of dark matter's non-existence would also have profound implications for our understanding of the very fabric of reality, the nature of matter, and the forces that govern the cosmos. The search for answers to the mysteries of dark matter and dark energy is not just a theoretical pursuit. It is a journey that could uncover the most profound secrets about our universe. Dark matter and dark energy are two of the most critical, yet mysterious components of the cosmos, each playing a distinct role in shaping the structure and behavior of the universe. However, they operate in fundamentally different ways. To begin with, dark matter can be thought of as an invisible form of mass. It does not emit, absorb, or reflect light, making it impossible to detect directly with our eyes or any ordinary telescopes. Despite its invisibility, dark matter's gravitational influence is undeniable. It helps bind galaxies together, ensuring they do not simply fly apart due to their rapid rotation. Imagine a group of dancers spinning on a stage. Without any visible force to hold them together, they would drift away from each other. In this analogy, dark matter is the invisible force that keeps the dancers in line, maintaining the coherence and structure of the dance. Similarly, it is dark matter's gravitational influence that holds galaxies and even entire galaxy clusters together, ensuring they do not break apart despite their immense motion. On the other hand, dark energy is an entirely different beast. While dark matter works to pull things together, dark energy is thought to be responsible for the accelerated expansion of the universe. To understand its role, imagine blowing up a balloon. As you add air, the balloon expands, and the points on the surface move further apart from each other. This is similar to how the universe is expanding, with galaxies moving away from one another. But unlike the uniformity of air filling a balloon, dark energy is a mysterious force that drives this expansion, pushing galaxies further apart at an ever-increasing rate. Whereas gravity acts as a force that pulls objects together, dark energy appears to act in the opposite way, pushing objects apart and accelerating the expansion of the universe. This is a major departure from what was once the prevailing understanding of cosmic expansion, where it was believed that gravity would gradually slow down the expansion of the universe over time. Instead, observations have shown that the universe's expansion is actually speeding up, a discovery that led to the introduction of dark energy as a concept to explain this unexpected behavior. Understanding dark energy is crucial for our comprehension of the ultimate fate of the universe. If dark energy continues to dominate, the universe could keep expanding forever, leading to a scenario known as the Big Freeze. In this scenario, galaxies would continue to drift farther apart, and over billions of years, stars would burn out, leaving a cold and empty cosmos. Alternatively, if other forces were to intervene, the universe's expansion could slow or even reverse, leading to very different outcomes, such as a big crunch. Yet, despite dark energy's overwhelming influence, accounting for approximately 70% of the universe's total energy, scientists have never directly observed it. Its existence has been inferred primarily through its effects on distant galaxies and other large-scale cosmic structures. The pursuit of understanding dark energy continues to be one of the most significant challenges in cosmology. The true nature of dark energy is still a matter of debate among scientists. Some theories propose that dark energy might be related to the vacuum of space itself, while others suggest that it could be a manifestation of entirely new physics. The mystery surrounding dark energy is one of the most captivating aspects of modern science, and every new discovery offers a glimpse into the deepest questions about existence itself. In their quest to understand dark energy, scientists use a variety of innovative techniques. One of the most important methods involves the study of distant supernovae. These massive stellar explosions serve as cosmic beacons, providing valuable information about the rate at which the universe is expanding. By measuring how these supernovae appear from Earth, scientists can determine their distance and velocity, helping to estimate the influence of dark energy on the cosmos. Another critical tool in the study of dark energy is large galaxy surveys. By mapping the distribution of galaxies across vast regions of space, scientists can observe how these galaxies are moving and clustering together. These surveys reveal patterns that offer insight into the underlying forces, such as dark energy, that drive cosmic expansion. In addition, the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, provides a snapshot of the universe's early moments, offering further clues about how dark energy may have shaped the universe's evolution. Gravitational waves, the ripples in space-time caused by massive cosmic events, are also being explored as a means of studying dark energy. By detecting these waves, scientists can probe the distant past and uncover new details about the role dark energy has played in the development of the universe. Furthermore, advanced computer simulations help recreate the universe's expansion under various conditions, allowing researchers to test different models of dark energy and explore its potential properties. All of these efforts contribute to an ever-growing understanding of dark energy's role in the cosmos. But even as we come closer to unraveling its mysteries, we are reminded of just how much there is still to learn. The true nature of dark energy and dark matter remains one of the greatest unsolved puzzles in modern science. If we were to ever unlock the secrets of these two cosmic phenomena, it would revolutionize our understanding of the universe. Dark matter, with its vast presence throughout the cosmos, could provide the missing link that connects the structure and behavior of galaxies over billions of years. Meanwhile, dark energy could help explain the accelerating expansion of the universe, offering profound insights into the universe's future. These discoveries could lead to a new framework for physics, uniting concepts like gravity, quantum mechanics, and the fundamental forces of nature. The eventual unification of dark matter and dark energy would not only refine our models of the universe, but might also spark a revolution in scientific thinking, one that challenges our deepest assumptions and reshapes how we view the very nature of existence. In the end, the search for these mysterious forces holds the potential to unlock the greatest secrets of the cosmos, revealing a universe far more intricate and fascinating than we ever imagined. And as we continue to probe the depths of space, we may one day come to understand the true nature of the forces that govern it, forces that, until now, remain hidden in the shadows of the universe. When a massive star reaches the end of its life cycle, it undergoes a dramatic transformation. Throughout its existence, the star maintains a delicate balance between the outward pressure from nuclear fusion at its core and the inward pull of gravity. However, as the star exhausts its nuclear fuel, this equilibrium is shattered. Unable to sustain the outward pressure, the core collapses under the immense force of its own gravity. This collapse is so powerful and rapid that it leads to an explosive event, an occurrence that has fascinated astronomers and physicists for centuries. Known as a supernova, this explosion expels the outer layers of the star into the vast expanse of space, leaving behind a dense core. If the mass of the core is above a critical threshold, often described as being several times the mass of our Sun, the gravitational pull at its center continues to intensify. The collapsing core compresses into an incredibly dense point, a singularity, where the laws of physics as we know them no longer apply. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape, not even light. This is the point of no return. Once an object crosses the event horizon, there is no escape from the black hole's relentless gravitational pull. Black holes can also form through other cosmic events, such as the collision of neutron stars or the accumulation of enormous amounts of gas and dust in a particular region of space. As gravity compresses this matter, it can eventually lead to the formation of a black hole. Regardless of the method by which they are formed, once black holes come into existence, they can continue to grow. Through mergers with other black holes or the gradual accumulation of surrounding matter, black holes can gain mass and become even more powerful. These enigmatic objects are some of the most captivating results of stellar evolution, embodying the incredible power and complexity of gravity. Yet, black holes present some of the most profound challenges to our understanding of the universe. Their existence forces us to confront the limits of modern physics, particularly in the realm of general relativity and quantum mechanics. General relativity, formulated by Albert Einstein, explains the behavior of gravity on a grand scale, offering insight into how massive objects like planets, stars, and galaxies warp the fabric of space and time. According to this theory, black holes exert such extreme gravitational forces that they bend space and time to the point where even light cannot escape. On the other hand, quantum mechanics describes the behavior of the smallest particles in the universe, governing the interactions between atoms and subatomic particles at incomprehensibly tiny scales. The conflict between these two theories becomes especially apparent at the heart of a black hole, where the singularity lies. Here, gravity becomes so intense that space and time themselves become distorted, and the known laws of physics break down. This presents a mystery. How can the laws of quantum mechanics and general relativity coexist in such extreme conditions? What happens to matter and information when it crosses the event horizon? The answer to these questions may hold the key to unraveling the deepest secrets of the universe. In addition to these mysteries, black holes challenge one of the fundamental principles of quantum mechanics, the preservation of information. According to quantum theory, information about the state of any particle or object should never be lost. Yet when something crosses the event horizon of a black hole, it seems to vanish. This apparent contradiction has led to the development of the black hole information paradox, a problem that continues to confound physicists. Some have suggested that the information might be preserved in some form, possibly encoded on the event horizon itself, but this hypothesis remains unproven. The event horizon is one of the most intriguing features of a black hole, representing the ultimate boundary between the observable universe and the unknown. Imagine standing on the edge of a precipice. Once you cross it, there is no going back. The event horizon acts in much the same way. It marks the point beyond which no object can escape the black hole's gravitational grip. For an outside observer, objects that approach the event horizon appear to slow down as they get closer, seemingly freezing in time. This effect is a result of the warping of space-time by the black hole's immense gravity. To an observer, these objects seem to stretch and fade as they approach the event horizon, further highlighting how gravity can distort the very fabric of reality itself. The event horizon is not just a theoretical boundary. It plays a crucial role in understanding some of the most profound questions in physics, particularly the nature of information. If objects lose their information when they fall into a black hole, what does that imply about the fundamental structure of the universe? These questions form the backbone of ongoing research in both theoretical physics and cosmology. The search for answers has led to the development of new theories, such as quantum gravity, which aims to reconcile the principles of general relativity with quantum mechanics. Through the study of black holes, scientists are attempting to unlock the mysteries of space, time, and the universe itself. Black holes act as natural laboratories for testing our understanding of the laws of physics. In particular, the study of how black holes interact with their environments can provide crucial insights into the dynamics of galaxies. As matter spirals into a black hole, it heats up and emits radiation. which allows astronomers to observe properties such as the black hole's mass, spin, and charge. This radiation can also shed light on the behavior of stars and gas in the surrounding region, helping us understand the processes that govern the formation and evolution of galaxies. Moreover, black holes are intimately connected with one of the most fascinating and elusive phenomena in the universe: gravitational waves. When two black holes collide, send ripples through the fabric of space-time, detectable as gravitational waves. The detection of these waves has opened up an entirely new field of astronomy, allowing us to observe events that were previously invisible to us. These waves carry information about the nature of black holes and the extreme conditions under which they operate, providing valuable clues about the universe's most mysterious phenomena. Black holes also offer tantalizing hints about the nature of dark matter and dark energy, two of the greatest mysteries in cosmology. By studying the influence of black holes on their surroundings, scientists hope to gather clues about the properties of these unseen forces that make up the vast majority of the universe's mass and energy. Understanding black holes, then, is not just about solving one of nature's puzzles. It's about expanding our knowledge of the universe's fundamental components. The singularity, the heart of the black hole, poses one of the greatest challenges to modern physics. At the singularity, the gravitational pull is so intense that space-time itself curves infinitely. Predictions suggest that the density of matter at the singularity becomes infinite, creating a region where the known laws of physics break down. This presents a paradox for physicists. While general relativity has been extraordinarily successful in explaining large-scale phenomena, such as the motion of planets and the behavior of galaxies, it fails to account for the conditions at the heart of a black hole. In contrast, quantum mechanics, which governs the behavior of the tiniest particles, offers a different set of predictions. The challenge is reconciling these two theories, something that has proven incredibly difficult. The singularity also raises profound questions about the nature of information. When matter crosses the event horizon, it appears to disappear entirely. Does this mean that the information about the matter's state is lost forever? This dilemma has sparked intense debates in the scientific community, with some theorists suggesting that information could be preserved in some way, perhaps encoded on the event horizon. However, this remains speculative, and the true nature of information in black holes is one of the most puzzling aspects of modern physics. As scientists continue to study black holes, the mysteries surrounding singularities may eventually lead to breakthroughs in our understanding of the universe. These objects are not just strange and enigmatic. They represent the frontiers of scientific inquiry. They challenge us to think beyond the limits of our current knowledge, urging us to rethink what we know about space, time, and existence itself. Black holes are more than just strange, invisible objects lurking in the depths of space. They play a vital role in shaping the structure of galaxies. There are two primary types of black holes: stellar black holes and supermassive black holes. Stellar black holes form from the remnants of massive stars after they explode in a supernova. Supermassive black holes, on the other hand, are found at the centers of most galaxies, including our own Milky Way. These supermassive black holes can be millions or even billions of times more massive than the Sun. The presence of a supermassive black hole at the center of a galaxy has profound effects on the galaxy's structure and evolution. The gravitational pull of a supermassive black hole influences the motion of stars and gas within the galaxy. As matter falls into the black hole, it generates enormous amounts of energy, producing powerful jets of radiation that can extend far beyond the galaxy itself. This radiation can heat surrounding gas and dust, impacting star formation. In fact, the activity of supermassive black holes can stabilize or destabilize the structure of a galaxy, influencing how stars are born and how they evolve over time. In addition to their role in shaping galaxies, black holes also help maintain the galaxy's overall structure. The gravitational pull of a black hole can keep clusters of stars in orbit around the galactic center, thereby helping to preserve the galaxy's shape over long periods. The interactions between the black hole and surrounding stars can lead to the migration of stars within the galaxy. Some stars may be pulled closer to the black hole, while others are ejected into intergalactic space. In essence, black holes are not merely cosmic oddities. They are central to the formation, evolution, and dynamics of galaxies. As such, they offer us a unique window into the workings of the universe, challenging our understanding of the fundamental forces that govern everything from the smallest particles to the largest structures in the cosmos. The process of black hole formation and their subsequent growth is inextricably linked to the evolution of galaxies. When galaxies collide or merge, their supermassive black holes may eventually come together, leading to the creation of a larger, more powerful black hole. This cosmic merger, while awe-inspiring, also produces gravitational waves, ripples in the fabric of space-time, that travel across vast distances. These waves are not just a scientific curiosity, but a groundbreaking phenomenon, detectable by sensitive instruments that can pick up their faint echoes, providing us with invaluable insights into the violent yet fascinating nature of the universe. As black holes grow, their influence extends beyond their immediate surroundings, shaping the very formation and evolution of stars within their host galaxies. The gravitational pull exerted by a supermassive black hole can regulate star formation rates, creating a feedback loop that affects the entire galaxy. This intricate relationship highlights the dual role of black holes as both creators and destroyers on an astronomical scale, continuously altering the landscape of the cosmos over millions and even billions of years. Black holes, therefore, are not just passive objects. They are integral to the understanding of galaxy dynamics, serving as powerful engines that drive the complex processes of galactic evolution. Despite their profound importance, black holes remain elusive. Humans have never directly observed a black hole in the same way we perceive ordinary objects, primarily because black holes do not emit light. However, through meticulous scientific observation and the analysis of their effects on surrounding matter, we have been able to confirm their existence. The region surrounding a black hole is often extremely energetic and bright, particularly when matter is drawn into it. As this material spirals inward, it forms a hot, dense accretion disk composed of gas and dust. The immense gravitational forces cause the disk to heat up to temperatures that emit radiation across multiple wavelengths, including X-rays, which can be detected by space telescopes. One of the most remarkable milestones in black hole research occurred in 2019, when scientists, using a vast network of radio telescopes from across the globe, captured the first ever image of a black hole's shadow. This black hole resides in the center of a galaxy called M87, located billions of light years away from Earth. By combining data from these numerous radio telescopes, which effectively created a planet-sized observational network, scientists were able to visualize the shadow cast by the black hole against the glowing material surrounding it. This groundbreaking image not only confirmed previous theories about black holes, but also provided a tangible glimpse into these mysterious and enigmatic cosmic giants. In addition to imaging black holes directly, astronomers also study their influence on nearby stars. By tracking the motion of stars in close proximity to a black hole, scientists can infer critical details about the black hole's mass. The gravitational pull of the black hole affects the orbits of these stars, allowing researchers to deduce not only the existence of the black hole, but also its properties. Through these methods, we are slowly piecing together the unseen world of black holes, uncovering clues from the subtle impacts they have on the surrounding universe. As technology continues to advance, our ability to observe and study black holes is improving exponentially. Modern telescopes, for instance, can observe the universe in a range of wavelengths, infrared, radio, and more, that penetrate the cosmic dust and reveal objects previously hidden from view. This enhanced observational power allows scientists to explore the environments around black holes in greater detail, providing deeper insights into their behavior and impact on surrounding matter. The development of new sensors and imaging techniques is also contributing to this progress. The Event Horizon Telescope, EHT project, which was responsible for the first ever image of a black hole's shadow, is a perfect example of how technology is transforming our understanding of these cosmic phenomena. As technology continues to evolve, we can expect even sharper and more detailed images of black holes, unveiling aspects of their nature that remain a mystery today. Moreover, computational power has seen remarkable strides, enabling researchers to simulate black hole dynamics with unprecedented accuracy. These simulations allow scientists to visualize complex interactions, such as the merger of two black holes or how matter behaves as it approaches the event horizon. These visualizations not only enhance theoretical understanding, but also serve as a means of experimental validation. By comparing simulations with real observational data, researchers can refine their models and gain a deeper understanding of black hole behavior. In addition to simulations, machine learning has become an increasingly valuable tool in analyzing vast amounts of astronomical data. By training algorithms to recognize patterns in the data, scientists can identify black holes and track their activity more efficiently. This cutting-edge approach promises to accelerate the discovery of new black holes and provide a more detailed understanding of their evolution. The speed and accuracy with which machine learning can analyze astronomical data offer unprecedented opportunities for future research. These technological advancements are pushing the boundaries of black hole research and, by extension, our understanding of fundamental physics and the nature of gravity itself. As we continue to refine our tools and methods, we inch closer to unraveling the mysteries that these enigmatic cosmic objects hold. Every new breakthrough brings us a step closer to understanding not just black holes, but the very fabric of the universe. One of the most intriguing, though highly speculative, concepts in modern science is the theory of the multiverse. This idea suggests that our universe is just one of many, each existing in parallel with its own set of physical laws, constants, and possibly even alternate versions of ourselves. To imagine the multiverse, one might think of our universe as a single bubble in a vast ocean, with each bubble representing a different universe, potentially with its own distinct rules of existence. Unlike the traditional view of our universe as the only reality, the multiverse theory proposes that infinite possibilities exist. Some of these universes may be very similar to our own, with alternate versions of familiar stars, galaxies, and even individuals. Others, however, could be radically different, governed by entirely new and unimaginable laws of physics. While these ideas may seem far-fetched, they find support in various branches of theoretical physics, particularly quantum mechanics. Quantum mechanics, the science of the very small, reveals that particles can exist in multiple states at once, a phenomenon known as superposition. This strange behavior forms the basis for the many worlds interpretation of quantum mechanics, which posits that every quantum decision or event spawns new branches of reality, resulting in a multitude of parallel universes. According to this interpretation, the act of observation does not collapse a particle into a single state. Instead, it gives rise to multiple realities, each equally real in its own right. Another avenue for exploring the multiverse comes from the theory of cosmic inflation, which describes the rapid expansion of the universe in the moments following the Big Bang. Some models of inflation suggest that during this rapid expansion, different regions of space-time could have expanded at different rates, leading to the formation of separate bubble universes. Each of these universes could have its own distinct set of physical laws, constants, and even dimensions. While the multiverse theory is undeniably fascinating, it remains speculative at best. To date, there is no direct evidence to support the existence of other universes. However, the theory challenges our conventional understanding of reality and invites us to reconsider the very nature of existence. The possibility that there may be countless other universes, each with its own set of rules and possibilities, expands our view of the cosmos and underscores how little we truly know about the universe we inhabit. One piece of evidence that has been cited in support of the multiverse theory comes from the cosmic microwave background radiation, CMB. This faint glow, which is a remnant of the early universe, contains slight fluctuations that some scientists interpret as the result of inflationary processes. These fluctuations could suggest that our universe underwent rapid expansion in the moments following the Big Bang, potentially leading to the creation of multiple universes, each with its own unique characteristics. While this remains a topic of debate, the CMB continues to be one of the most compelling pieces of indirect evidence for the possibility of a multiverse. The multiverse theory, despite its speculative nature, opens up an entirely new realm of possibilities. It suggests that the reality we experience may be just a tiny fraction of a far larger, more complex cosmic landscape. Whether or not other universes exist is still an open question, but the idea challenges us to think beyond the confines of our own universe and consider the infinite possibilities that may lie beyond what we can observe and measure. String theory, a profound concept in modern physics, ventures into the realms of the unknown, aiming to unify two pillars of scientific understanding: general relativity, which governs the vast cosmos, and quantum mechanics, which dictates the behavior of particles at the smallest scales. At its core, string theory proposes that the fundamental building blocks of the universe aren't point-like particles, but rather tiny vibrating strings. These strings, in different vibrational states, could account for the myriad forces and particles that make up our universe. This theory doesn't just aim to bridge gaps in our understanding of the known, it also introduces a mind-bending idea: the possibility of multiple dimensions, extending far beyond the 3 dimensions of space and the 1 dimension of time that we experience daily. In some of the more speculative scenarios of string theory, the concept of extra dimensions offers a tantalizing possibility, one where the universe is not a solitary entity but part of a vast multiverse. Imagine a landscape of diverse coexisting universes, each with its own distinct properties, laws of physics, and constants. While we may only have access to our own universe, the idea that there are many others, each with unique conditions, challenges the very essence of what we know about existence. However, despite the elegance of string theory and its potential to revolutionize our understanding, there is a significant hurdle to its acceptance: the issue of empirical evidence. For many advocates of string theory, proving the existence of other universes, whether those universes are influenced by the theory of multiverses or some other framework, remains an insurmountable challenge. The crux of the issue lies in the possibility that these other universes might be entirely isolated from our own, their existence beyond the reach of our current observational capabilities. Without empirical evidence to test, confirm, or deny the presence of these alternate realities, the multiverse remains a speculative hypothesis, one that for now lies in the realm of theoretical physics. One of the most intriguing aspects of the multiverse theory lies in its potential to explain what is known as the fine-tuning problem. Our universe, as we observe it, is uniquely suited for life. The physical constants, such as the strength of gravity or the charge of an electron, are perfectly calibrated, seemingly by chance, to allow for the existence of life as we know it. Some proponents of the multiverse theory suggest that given an infinite number of universes, it is statistically likely that at least one would have the right conditions for life. This suggests that our universe may not be the only one where life is possible. Rather, it may be just one among many. However, critics of this argument point out that this reasoning hinges on the assumption that probabilities can be applied to scenarios that lack direct observational support. Without concrete evidence, they argue, this theory may not be as robust as it appears. Despite these challenges, the multiverse theory continues to captivate the minds of theoretical physicists and cosmologists. It suggests a reality far grander than the one we currently perceive. Traditionally, we view reality as a singular system, one universe, governed by a set of physical laws that apply uniformly throughout. But what if our universe is just one of many, each existing in parallel, each with its own unique rules? This shift in perspective opens up new possibilities for what it means to exist. Picture for a moment your life as a single path through an expansive forest. Every choice you make leads you down a different trail, and in the multiverse, every possible decision you could have made or every event that could have happened creates a new universe. In this vast, branching cosmos, every decision, every event could create new versions of reality, some almost identical to ours, while others might be radically different. Imagine alternate versions of yourself, existing in parallel dimensions, living out different choices, perhaps even experiencing entirely different flow of life or matter. This concept expands beyond the simple idea of parallel universes. It challenges the very notion of uniqueness. If every choice, no matter how small, gives rise to a new universe, Does anything really stand as singular or exceptional? Are we simply one of many, each reality existing as a fleeting fragment in the grand scheme of an infinite cosmos? Moreover, the multiverse theory raises questions about the very nature of existence, questions about fate, identity, and individuality. In a cosmos where everything exists in multiple versions, where does our sense of self stand? In addition to reshaping our philosophical perspectives, the multiverse theory also intersects with some of the most profound questions in theoretical physics and cosmology. For instance, the idea of the multiverse offers a potential explanation for the fine-tuning problem. Why does our universe appear to have the perfect conditions for life? If there are many universes, then it is not so surprising that at least one would have the right conditions for life to emerge. In other words, we might simply be living in the one that worked out. This idea challenges traditional notions of purpose and design, suggesting that the very fabric of reality could be a vast, unpredictable expanse filled with an endless variety of outcomes. If the multiverse theory is eventually proven to be true, the implications would be nothing short of transformative. It would fundamentally alter how we perceive the nature of existence, offering a view of reality that extends far beyond our own universe. The idea that there are countless other universes, each with its own distinct properties, could change the very way we understand the cosmos. It would offer new ways of looking at possibility, identity, and the fabric of reality itself. Every decision we make could spawn an entirely new universe, an infinite number of realities unfolding with each passing moment. This radical shift in perspective could profoundly alter how we view ourselves, our place in the universe, and our sense of purpose. It might lead us to question whether anything in our universe is truly unique. If there are infinite versions of every possibility, is there anything special about the way things are in our own world? This exploration of the multiverse could lead to deep existential questions about the nature of choice and fate. Could there be alternate versions of us living entirely different lives in parallel dimensions? And if so, what does this mean for our understanding of self and identity? In addition to its existential implications, the multiverse theory also introduces new challenges to the scientific community. The possibility that other universes might be unobservable, existing beyond the limits of our observational reach, raises significant questions about how we might study them. The very nature of science, grounded in observation and testability, would need to evolve in order to accommodate these new possibilities. How can scientists develop tools and methodologies to explore realms that are fundamentally beyond our reach? The answer might lie in new theoretical frameworks that allow us to study realities that we cannot directly observe, expanding the boundaries of scientific inquiry. Ultimately, the discovery of the multiverse would not only transform our scientific understanding of the universe, but also open the door to profound philosophical reflection. It could invite a new way of thinking about the nature of reality itself, providing a more intricate and nuanced view of existence. If proven true, the multiverse theory could reveal that we are part of a far larger, more complex reality, one that extends beyond our wildest imaginations. The multiverse theory is not a monolithic concept. There are several variations, each offering a different perspective on how these universes are formed and what they might look like. One popular version is the bubble universe theory, which compares the multiverse to a growing foam of bubbles. Each bubble represents a different universe, with its own set of physical properties and laws of physics. Some bubbles might support life, while others may not. The universes within this framework are entirely separate from one another, unable to interact. Each one exists independently, floating in a larger, ever-expanding cosmic foam. Another version, known as the many worlds interpretation, arises from the field of quantum mechanics. This theory posits that every possible outcome of an event creates a new branch in the universe. For example, if a person faces a choice, one universe will follow one outcome, while another universe will follow the alternate path. In this scenario, every decision creates a new branch of reality, leading to an infinite number of possible universes. This interpretation envisions the multiverse as a vast tree, with each branch representing a different possible outcome of every decision ever made. Yet another approach to the multiverse comes from string theory, which posits that our universe is just one slice of a much larger framework made up of tiny, vibrating strings. These strings can vibrate in different ways, leading to different universes with varying physical laws and properties. The multiverse in this framework is not a collection of separate universes, but rather a complex, interconnected web of realities, each shaped by the unique vibration of its strings. Lastly, the theory of cosmic inflation offers yet another perspective. According to this theory, shortly after the Big Bang, the universe underwent a rapid expansion, known as inflation. As space expanded at different rates in different regions, it created pockets or island universes, each with its own set of physical properties and laws. In this scenario, the multiverse is not a collection of separate universes, but rather an ever-expanding landscape of pockets of space, each developing its own unique characteristics. While each of these versions of the multiverse theory offers a unique perspective on the nature of reality, they all share one common thread: the possibility that we are not alone in existence. We're part of a vast, interconnected cosmic landscape filled with countless other universes, each with its own possibilities and potential. This idea, although speculative and difficult to prove, captures our imagination as it suggests that our universe is just one of many, perhaps infinite realities. The notion that every choice and event creates a branching universe, leading to an infinite number of possibilities, opens up a realm of infinite exploration and discovery. What if there are worlds where you made different decisions, or where key events in history unfolded in an entirely different way? The possibilities in the context of the multiverse seem boundless. However, this idea is far from straightforward. It sits at the intersection of imagination, science, and philosophy, raising as many questions as it answers. The notion of a multiverse, a reality where countless universes exist beyond our own, has captivated both scientists and thinkers for decades. Yet, it is also deeply controversial. Why? Because it challenges the very foundation of traditional scientific inquiry, which relies heavily on observation, experimentation, and repeatable results. Multiverse theories, in contrast, exist in a realm that eludes direct testing. How can one test something that lies outside the boundaries of our observable universe? Skeptics point to this as a critical flaw, arguing that multiverse ideas veer too far into the domain of philosophy, rather than staying firmly rooted in science. They worry that without the ability to directly observe or experiment on other universes, these theories risk slipping into the realm of speculation, drifting further away from the rigor of the scientific method. This tension, the pull between the boundless realm of imagination and the precise demands of empirical evidence, makes the multiverse a subject of intense debate. Yet it also makes the multiverse an alluring topic. It pushes us to rethink the very limits of reality. Imagine a universe where the laws of physics differ entirely from our own, where the constants that govern the cosmos are not what we know them to be. In the multiverse theory, our universe is not unique. It is merely one of many, each with its own set of physical laws, its own fundamental constants. If this idea holds any weight, it could change how we view the universe in profound ways. Take, for example, the mysteries of dark matter and dark energy. These phenomena are some of the most confounding questions in modern cosmology. In a multiverse framework, dark matter and dark energy might not be anomalies at all. Instead, they could be different in other universes, each with its own version of these mysterious forces. This would offer alternative explanations, potentially making sense of their existence in ways we haven't yet considered. It's a tantalizing prospect, suggesting that answers to some of the universe's most perplexing mysteries might lie in the conditions of other realities. Furthermore, the multiverse invites a radical rethinking of the origins of our universe. For centuries, scientists have grappled with the question, what caused the Big Bang? What was the singular event that set everything into motion? The multiverse suggests that there may not be one answer at all. Instead, our universe could be the result of an infinite number of branching possibilities, each one emerging from different initial conditions. This idea shifts the focus away from a singular point of origin and opens the door to a multitude of explanations for how we arrived at our current state. This notion also resonates with discussions surrounding the fine-tuning of the universe. The fine-tuning argument contends that the constants of nature, such as the strength of gravity or the charge of an electron, are set in such a precise way that had they been even slightly different, life as we know it would not exist. The multiverse offers a way out of this dilemma. If there are countless other universes, each with its own set of physical laws, then it's not surprising that at least one of those universes would have conditions suitable for life. Instead of invoking a divine or special explanation, the multiverse posits that, statistically, a life-permitting universe was bound to emerge somewhere in the infinite expanse of possibility. In the realm of physics, the multiverse could also offer a solution to one of science's greatest challenges, reconciling quantum mechanics with general relativity. These two pillars of modern physics, one explaining the behavior of particles at the smallest scales, the other governing the vast stretches of space and time, currently do not fit together. Quantum mechanics works well on the microscopic level, while general relativity governs the behavior of large-scale objects like stars and galaxies. But they don't mesh easily when applied to situations that involve both. The multiverse opens up new avenues for thinking about this conundrum, encouraging researchers to consider possibilities beyond the confines of our observable universe. As we push the boundaries of knowledge, the existence of a multiverse invites us to embrace a broader, more diverse understanding of reality itself. It pushes us to venture further into the unknown to seek answers to questions that have long eluded us. Through this lens, the mysteries that once seemed insurmountable may turn out to be just the next step in our journey toward greater knowledge. Quantum mechanics, often regarded as the most successful theory in modern physics, provides an intriguing framework for considering the multiverse. At its core, quantum mechanics explores the behavior of particles at the smallest scales. One of its most mind-bending phenomena is superposition, the idea that particles can exist in multiple states at once. Imagine flipping a coin. While it's in the air, it is not just heads or tails. It holds the potential to be both, existing in a superposition of these two states until it lands. This principle challenges our understanding of reality itself. In quantum mechanics, when a measurement is made, the system seemingly chooses one state, collapsing all the possibilities into a single outcome. However, some interpretations suggest that instead of collapsing into just one state, every possible outcome occurs, but in a separate universe. This concept, known as the many worlds interpretation, suggests that every time a choice is made, the universe splits, creating a new branch where each possibility unfolds. It's like a tree with infinite branches, each representing a different version of reality. This notion stretches our understanding of time and space, pushing the limits of how we perceive the universe. Moreover, quantum phenomena like entanglement, where particles can instantaneously influence each other even when separated by vast distances, add further weight to the idea of a connected multiverse. If entanglement exists across multiple realities, then events in one universe might influence others in ways we cannot yet fully comprehend. This idea challenges our perception of space and time as fixed and unchanging, suggesting that the boundaries of reality are far more fluid than we imagined. Ultimately, while quantum mechanics provides a compelling framework for the multiverse theory, it also leaves us with more questions than answers. It invites us to reconsider our fundamental notions of reality, existence, and the nature of the universe itself. Each discovery, each new theory, only deepens the mystery, encouraging us to look beyond our single experience of the cosmos and imagine what might lie beyond. Time, too, plays a crucial role in our understanding of the universe. In the context of physics, time is often treated as a dimension, an aspect of the fabric of the universe that allows us to perceive and sequence events. Just as we use a ruler to measure space, we use time to measure the flow of events, from the birth of stars to the evolution of galaxies. Time allows us to make sense of the universe's grand narrative. But time is not a uniform, unchanging force. It is relative, meaning that it doesn't flow at the same rate everywhere. For example, if you were to travel close to the speed of light, you would experience time at a slower pace compared to someone remaining on Earth. This is a direct result of Einstein's theory of relativity, which links time to the very structure of space itself. In this way, time is not merely a background for events to unfold, it actively shapes how the universe evolves. This dynamic understanding of time is essential to our grasp of the cosmos. It enables us to track the expansion of the universe, the movement of galaxies, and the evolution of stars and planets. Time itself is woven into the very fabric of the universe, guiding its development and revealing the ever-changing nature of reality. The concept of time travel, which has fascinated humanity for centuries, adds another layer of intrigue. Many theories have emerged about how it might be achieved, though few remain practical. One popular idea involves wormholes, hypothetical tunnels through space-time that could allow for travel between different points in time, much like they allow for travel across space. If wormholes could be found or created, they might provide a shortcut through time. But as with all things, the construction or discovery of stable wormholes remains a distant dream. Another theory centers on the speed of light. According to Einstein's theory of relativity, as an object approaches the speed of light, time slows down for that object relative to someone who remains stationary. In theory, traveling at speeds close to the speed of light could allow a person to experience less time passing for themselves, while those left behind would age normally. However, reaching such speeds would require immense amounts of energy, far beyond our current technological capabilities. Lastly, there is the idea of closed time-like curves, paths through space-time that loop back on themselves. According to some solutions to Einstein's equations, such curves could, in theory, allow an object to return to a previous point in time. While this notion has yet to be proven or tested, it opens up fascinating possibilities for how time could be manipulated. The notion of time, like the multiverse itself, continues to challenge our perceptions of reality. It encourages us to think beyond the constraints of our everyday experience, urging us to ask deeper questions about the nature of existence, the structure of the universe, and the possibilities that lie ahead. Time may be one of the greatest mysteries we encounter, but it is also one of the most essential understanding the cosmic tapestry that unfolds before us. Time is a concept that stretches far beyond its usual definition as a mere measurement of moments. It's an idea that has captured the imagination of philosophers, scientists, and poets alike, constantly evoking questions that challenge the very fabric of our understanding. However, when it comes to time travel, particularly traveling backward, we encounter paradoxes that challenge not just our perceptions, but the very foundation of what time itself is. One of the most famous paradoxes is the grandfather paradox, which questions the consequences of altering the past. The idea is simple, yet mind-boggling. If a time traveler were to go back in time and prevent their own grandfather from meeting their grandmother, they would, in theory, cease to exist. Without their existence, how could they travel back in time in the first place? This paradox raises profound questions about causality and whether time travel could ever be truly possible without disrupting the very events that allow for the travel itself. Further complicating the issue are theories about parallel universes. Some suggest that when a time traveler alters the past, rather than erasing their own existence, they may simply create an alternate timeline. This theory proposes that changes to the past could cause a branch to form in the space-time continuum, creating a new reality while leaving the original one intact. This view, known as the many worlds interpretation, suggests that time travel doesn't erase history but creates new possibilities. Yet, as tantalizing as this notion is, it remains speculative. Despite the imaginative potential, we have no concrete evidence to prove that these parallel timelines exist or could be accessed by any known means. Still, even as these theories push the boundaries of imagination, they remain, for now, firmly within the realm of science fiction. The practical feasibility of time travel encounters insurmountable obstacles, chiefly the immense energy required, the complexity of paradoxes, and the laws of physics that govern our universe. Thus, while we can speculate about time travel's possibilities, it remains a fantastical idea rather than a practical reality. The theory of relativity, first introduced by Albert Einstein, fundamentally reshapes our understanding of time. Traditionally, humans perceive time as a constant, an unchanging force that passes at a steady pace no matter where you are or what you're doing. However, Einstein's revolutionary theory shows that time is far more fluid. Rather than being a constant, time is part of the space-time continuum, a fabric that is flexible, bendable, and deeply influenced by the forces around it. This realization comes to life when considering two observers, one standing still on Earth and another traveling in a spaceship moving close to the speed of light. For the person on the spaceship, time passes more slowly compared to the person on Earth. This phenomenon, known as time dilation, shows that time is relative. It doesn't pass at the same rate for everyone or everywhere. If the person aboard the spaceship were to journey through space at near light speeds and then return home, they would find that more time had passed on Earth than for them. This discrepancy is a direct consequence of their high-speed travel, and it has profound implications for how we perceive time across different environments. It suggests that time, rather than being a rigid measurement, is a variable experience, depending on one's relative speed and gravitational position. In this context, time doesn't pass differently for travelers at different speeds. It can also behave differently depending on the gravitational forces at play. A clock on a satellite farther from Earth's gravitational pull ticks slightly faster than one on the ground. The stronger the gravity, the more slowly time passes. For instance, near massive objects like black holes, time literally stretches out. If you were to stand close to a black hole, you'd experience time much more slowly than someone far away in the distant reaches of space. This concept challenges our intuitions about the passage of time and suggests that time is not a universal constant, but a feature of space itself, an aspect of the space-time continuum. As such, everything we know, from the technology we rely on, such as GPS satellites, to our understanding of the universe, is based on a fundamental, ever-present relationship between time, speed, and gravity. Time's malleability is not limited to human-scale scenarios, but extends to the vastness of the cosmos. As the universe expands, time itself becomes a crucial factor in understanding the evolution of everything from the smallest particles to the largest galaxies. In the earliest moments after the Big Bang, time began its journey, evolving in tandem with the cooling and expanding universe. This interplay between space and time is why we see distant galaxies moving away from us. The very fabric of space itself is stretching, causing the light from these galaxies to take longer to reach us. This delayed light serves as a cosmic time capsule, offering us a glimpse into the past. The fate of the universe, too, depends on time. Whether the universe will continue expanding indefinitely, slow down, or eventually collapse in on itself depends on factors such as the amount of matter and energy it contains. These processes unfold on a cosmic timescale, meaning that understanding time is key to predicting the ultimate destiny of the universe. On these vast scales, time becomes even more unfathomable. 1,000,000 years is just a blink in the life of a galaxy, and the entire lifespan of the universe is nearly incomprehensible to human minds. Still, time is the thread that weaves the universe's story, from its origin to its ultimate fate. Even closer to home, our understanding of time is deeply influenced by gravity and motion. As we move further from massive objects like planets or stars, time speeds up. But closer to these objects, it slows down. For instance, in the intense gravitational pull of a black hole, time stretches to an almost infinite degree, making it appear to stand still for an observer at the event horizon. This means that the passage of time is not the same everywhere. The forces of gravity and the motion of objects have time in ways that are still being studied, revealing a universe where time is not just a clock ticking away. It's a dynamic and changing phenomenon that varies depending on where you are and how fast you're moving. This raises the question of whether time can exist apart from space, and if so, what that would mean. Space and time are not independent entities in our universe, but are woven together into what is known as the space-time continuum. Think of space-time as a fabric where each thread represents not only space, the three dimensions of up and down, left and right, forward and backward, but also time itself, the flow that we experience. If time were to exist separately from space, it would suggest a universe where events could unfold without any physical location. This idea pushes the boundaries of our comprehension. How could something evolve or change if it had no place to occur? In current physics, every event, whether a star exploding or a planet moving, is tethered to both space and time. If we were to separate the two, it would upend the very laws of physics that govern reality. Such a split would lead to unanswerable questions about how the universe operates, and could even hint at new dimensions or realities, stretching the very limits of our imagination. Philosophers have long debated the nature of time. Is time an objective, independent force of the universe, flowing in a steady, linear fashion? Or is time merely a subjective experience shaped by human consciousness? The first view suggests that time flows much like a river, continuously and uniformly, regardless of whether anyone is observing it. On the other hand, some philosophers argue that time is an experience shaped by our memories and expectations. We might feel time passing differently in moments of joy compared to moments of sadness. This subjectivity gives rise to the idea that time is not just a universal measure, but a personal experience, felt differently by everyone depending on their own circumstances. One of the central debates about time is its direction. Does time flow in a single direction, from past to present to future? This idea, known as the arrow of time, is closely tied to the second law of thermodynamics, which states that disorder, or entropy, tends to increase over time. In simpler terms, as time progresses, the universe moves from order to chaos, which provides an explanation for why time only moves forward. Yet, some philosophers challenge this view, suggesting that time might be more like space, where past, present, and future exist simultaneously, and our perception of time moving forward is merely an illusion. These philosophical debates open up a profound exploration not only of how time works in the universe, but also how we experience it in our daily lives. Our understanding of time shapes everything, from the way we measure our lives to how we process our experiences. This contemplation of time has been central to humanity's quest to understand our place in the cosmos. How we perceive time, whether as an objective reality or a subjective experience, can influence our emotions, our choices, and ultimately, how we define our existence. Around the world, different cultures have unique ways of understanding time. For many ancient civilizations, the movement of celestial bodies such as the sun, moon, and stars shaped their perception of time. Indigenous cultures, for example, often view time as cyclical, reflecting the repeating patterns of nature, seasons, lunar phases, and other natural cycles. In this view, time is not a linear progression, but a series of interconnected cycles, where the past, present, and future are all linked. In contrast, Western thought, heavily influenced by ancient Greek philosophy, tends to view time linearly, as a continuous forward-moving journey from past to present to future. This linear perspective has shaped much of modern life, influencing everything from our concepts of history to how we organize our daily routines. Ultimately, whether seen as cyclical or linear, time remains one of the most powerful and mysterious forces in the universe. It governs not just the movements of the stars and planets, but also our lives, our decisions, and our understanding of everything that has come before and will come after. In Hinduism, time is not simply a linear progression of events, but is instead understood as cyclical, reflecting a profound spiritual connection with the universe. The concept of time in Hindu philosophy encompasses vast epochs known as yugas, which span millions of years. These yugas repeat in a never-ending cycle, suggesting a view of existence as an eternal rhythm of creation, destruction, and renewal. This expansive perspective on time goes beyond the mechanical ticking of the clock, offering a vision where everything, from the smallest particle to the vast expanse of the cosmos, is engaged in an endless dance of transformation. It highlights a deep interconnection between humanity, nature, and the divine, where each moment carries with it the weight of both cosmic history and spiritual significance. Similarly, the ancient Mayan civilization viewed time through a unique and intricate lens. Their approach to time was deeply tied to their understanding of the cosmos and the cycles that governed not only the heavens, but also their daily lives. The Mayans crafted highly sophisticated calendars, some of which were designed to track the movements of celestial bodies and align with specific astronomical events. These calendars were not just tools for measuring days and months, but also for synchronizing agricultural cycles and religious ceremonies. For the Mayans, time was a sacred rhythm that shaped their rituals, marking the passage of seasons, planting, and harvest, as well as the cyclical nature of human existence. This connection between time, spirituality, and the universe underscores a broader cultural understanding that time is not merely a measurement, but a cosmic force that intertwines with the very essence of life. Both Hinduism and the Mayan civilization offer us rich, layered interpretations of time that go beyond the practicalities of day-to-day living. They reveal how ancient cultures saw time not as a simple chronological order, but as a living, breathing force that guides both the universe and human experience. Through these perspectives, we see how humanity has always sought to understand its place in the cosmos, whether through the cycles of yugas or the movements of planets, emphasizing the deeply spiritual and interconnected nature of existence. In the modern age, scientists have embarked on their own quest to understand the broader universe, seeking signs of life beyond our planet. The search for extraterrestrial life has become one of the most ambitious and exciting endeavors in contemporary science, driven by the belief that the universe, with its infinite expanse, may harbor life forms yet to be discovered. One of the primary methods scientists use to explore this possibility is the study of planets within our solar system, particularly those that show signs of having conditions suitable for life, such as water. Missions to Mars, for instance, have focused on examining soil samples for organic molecules that could suggest the presence of life, both past and present. Similarly, scientists are turning their attention to the icy moons of Jupiter and Saturn, where subsurface oceans might harbor microbial life. Beyond our solar system, the search for life extends to distant exoplanets, planets that orbit stars outside our solar system. Using powerful telescopes and advanced techniques like spectroscopy, scientists analyze the light that passes through the atmospheres of these distant worlds. By identifying specific gases, such as oxygen or methane, they hope to detect the chemical signatures that may indicate biological processes. The process of spectroscopy works by analyzing how the light from a star interacts with a planet's atmosphere, revealing its composition. This technique is akin to using a fingerprint to identify someone. Each atmosphere leaves a unique mark that can tell us a great deal about the planet's potential to support life. In addition to these observational methods, projects like SETI, Search for Extraterrestrial Intelligence, focus on the search for radio signals from advanced civilizations. Scientists involved in SETI scan the vast reaches of space for any unusual patterns or signals that could suggest intelligent beings attempting to communicate. This search involves analyzing enormous data sets and listening for anomalies that stand out from the background noise of cosmic radiation. Scientists are also conducting laboratory experiments that simulate extraterrestrial environments, testing the resilience of life forms in conditions similar to those found on other planets. By recreating extreme environments, such as high radiation, freezing temperatures, or lack of oxygen, researchers can study how life might adapt to survive in these hostile conditions. These experiments are providing valuable insights into the potential for life to thrive in places where we once thought it impossible. The cumulative effect of these diverse methods, planetary exploration, the study of exoplanets, the search for intelligent signals, and laboratory simulations, enriches our understanding of the universe and the possibility that life exists beyond Earth. This multifaceted approach to exploring extraterrestrial life is not just a single mission or theory, but a complex, interconnected scientific endeavor that pushes the boundaries of human knowledge. The quest for extraterrestrial life is not just a matter of scientific curiosity. It challenges the very nature of what it means to be human. If life were discovered on another planet, it would fundamentally alter our understanding of the universe and our place within it. The sheer scale of the cosmos, with its billions of stars and planets, suggests that life may not be unique to Earth. Rather, it could exist in many different forms, in environments vastly different from our own. This idea expands our definition of what makes a planet habitable, pushing scientists to consider extreme environments, such as the deep subsurface of planets or even the clouds of gas giants, as potential havens for life. Such a discovery would also spark profound philosophical questions about the nature of consciousness and existence. It would challenge our assumptions about the singularity of human experience and perhaps lead to new understandings of intelligence, evolution, and the very essence of life itself. The implications would reach far beyond the confines of biology or chemistry, forcing us to reconsider our worldview and our relationship to the cosmos. As scientists explore the mysteries of the universe, they uncover truths that continue to astonish and perplex us. From the strange phenomena of black holes, which warp space-time itself, to the invisible forces of dark matter and dark energy that shape galaxies, we are confronted with a cosmos far stranger and more complex than we could ever have imagined. These forces, black holes, dark matter, and dark energy, are not abstract concepts, but real, measurable aspects of the universe that have been confirmed through rigorous observation. The existence of black holes, for example, has been verified through the detection of gravitational waves, and dark matter's influence on galaxy formation is well documented, even though it remains invisible to traditional telescopes. The universe is a vast and strange place where quantum particles behave in ways that defy classical physics, and time flows differently depending on gravity and velocity. These revelations raise fundamental questions. Are we alone in this infinite expanse? Could there be parallel universes existing alongside our own? What lies beyond the observable universe in the regions we cannot yet detect or measure? The origins of the universe itself are a subject of deep fascination and ongoing exploration. One of the most widely accepted theories of cosmology is the Big Bang theory, which proposes that the universe began as an incredibly small, hot, and dense point. This initial state, akin to a tiny dot, expanded rapidly in a process called cosmic inflation, creating all of the space, time, and matter that make up the universe today. The aftermath of this explosion still reverberates throughout the cosmos as we observe the expansion of space itself and the background glow of light, known as the cosmic microwave background radiation, which serves as the faint afterglow of the Big Bang. The idea of cosmic inflation, which suggests that the universe expanded exponentially in the first fraction of a second, helps to explain the remarkable uniformity of the universe. Despite its vastness, the universe appears to have similar properties in all directions, a mystery that inflation theory attempts to solve. There are also alternative theories, such as the cyclic model, which suggests that the universe goes through endless cycles of birth, expansion, and contraction, like a heartbeat, continuously rising and falling over infinite time. These theories offer various perspectives on the origins and ultimate fate of the universe, each adding a layer of complexity to our understanding. Ongoing research continues to push the boundaries of our knowledge as scientists seek to uncover the true nature of the cosmos. The Big Bang theory remains our most robust explanation for the origins of the universe, suggesting that space and time were born in a single moment of expansion roughly 14 billion years ago. This event set into motion the gradual cooling and formation of particles, atoms, stars, and galaxies, an evolutionary process that continues today as the universe continues to expand. Observations show that galaxies are still moving away from each other, a phenomenon that supports the idea of an ever-expanding universe, constantly stretching outward from its initial point of origin. The search for knowledge about our universe is ongoing, ever deepening our awe and wonder at the grand, mysterious cosmos we inhabit. The universe, vast and endlessly expanding, is a testament to the incredible complexity and scale of existence. The Big Bang theory provides the most comprehensive framework for understanding the history and development of the cosmos, from the intensely hot and dense origins of the universe to the complex, ever-evolving system of galaxies, stars, and planetary bodies that we explore today. It paints a picture of a universe that has continuously transformed, expanded, and evolved over billions of years, creating the space-time continuum we now inhabit. But how did it all begin? What clues can we gather about the universe's fiery origins, and how can we verify such extraordinary claims? At the heart of this theory lies a range of evidence, gathered over decades of research, that suggests the universe began from a singular event, an explosion of unimaginable scale. One of the most significant pieces of evidence supporting this theory is the cosmic microwave background radiation, or CMB. Imagine, if you will, a faint glow, a soft afterglow that pervades the entire universe. This glow is a remnant of the heat from the Big Bang itself. When scientists first detected this radiation, it was like discovering the lingering echoes of a long-forgotten explosion. This faint signal, traveling through the vast expanse of space, represents the universe's earliest moments, carrying with the primordial warmth left behind from its fiery origins. The discovery of the cosmic microwave background radiation stands as one of the pillars of evidence for the Big Bang theory. It is a faint but ever-present signal from the universe's infancy, still rippling across the fabric of space-time billions of years later. But this is not the only evidence that points to a cosmic explosion. Another crucial observation comes from the redshift of galaxies. As light from distant galaxies shifts toward the red end of the spectrum, scientists have inferred that these galaxies are moving away from us. This phenomenon, known as the redshift, provides a key piece of the puzzle. The universe is expanding. In a manner similar to the way the pitch of a siren changes as it moves away from you, the redshift of galaxies tells us that, as time passes, everything is moving away from one another. The further away a galaxy is, the faster it appears to be receding, offering clear evidence that the universe began as a single, extremely compact point and has been expanding ever since. Beyond this, the abundance of light elements such as hydrogen and helium further supports the Big Bang model. These elements were created in the first few minutes after the explosion, when the universe was hot and dense. By examining the ratios of these elements in distant regions of space, scientists can confirm predictions made by the Big Bang theory about the chemical makeup of the early universe. The fact that the observed abundances of these elements align with theoretical predictions reinforces the idea that the universe began in an extremely hot and dense state. Yet another critical concept that plays a role in understanding the universe's origins is cosmic inflation. This idea proposes that, in the earliest moments of the universe's existence, it underwent an incredibly rapid and exponential expansion. If the Big Bang represents a fiery birth, inflation suggests that in the first fraction of a second, the universe expanded at a mind-boggling rate, far faster than the speed of light. The evidence for this inflationary period comes from the tiny fluctuations observed in the cosmic microwave background radiation. These fluctuations, when carefully analyzed, align with the predictions made by inflationary models, further reinforcing the credibility of the Big Bang theory. Each of these pieces of evidence, the cosmic microwave background radiation, the redshift of galaxies, the abundance of light elements, and the patterns seen in cosmic inflation, combine to form a compelling narrative. This narrative paints a picture of a universe born from a singular, cataclysmic event and continuously expanding and evolving ever since. However, while the Big Bang theory provides a well-supported framework for the universe's origins, it has not been without controversy. One of the main points of debate among scientists centers around the question of what exactly happened in the first moments after the Big Bang. This early period, sometimes referred to as the Planck era, is extremely difficult to observe or model, leading some scientists to question whether our understanding of the universe's birth is complete. The details of these initial moments remain elusive, sparking ongoing discussions about the limits of our current theories and the accuracy of our models. Another area of contention is the idea of cosmic inflation. This concept suggests that the universe underwent a brief but intense period of exponential expansion in the first fractions of a second. While this helps explain certain observed patterns, such as the uniformity of the cosmic microwave background radiation, it raises further questions. For example, cosmic inflation implies that the universe must have begun under very specific conditions. Some researchers argue that current observations do not fully support this specific set of conditions. The lack of direct, conclusive evidence for inflation has prompted some to explore alternative theories of the universe's birth. Furthermore, the existence of dark matter and dark energy adds an additional layer of complexity to our understanding of the universe. These mysterious substances, which we can infer but cannot directly observe, play a crucial role in the universe's expansion and overall structure. However, their exact properties remain largely unknown. Some critics of the Big Bang theory argue that our inability to definitively detect and understand dark matter and dark energy challenges the completeness of the model, suggesting that there may be gaps in our understanding of cosmic evolution. Beyond these scientific debates, the Big Bang also touches on deeper philosophical questions about time, causality, and the nature of existence itself. For example, is it meaningful to speak of before the Big Bang? If time itself began with the Big Bang, what does that imply about the concept of causality? These questions dive into existential territory, blending science with metaphysical inquiry. As we try to understand the origins of the universe, we are also forced to confront the very nature of reality. Can the Big Bang be the definitive beginning of everything, or is it merely a chapter in an ongoing cycle of cosmic rebirths? These questions make the Big Bang Theory not just a scientific model, but also a philosophical platform for exploring the mysteries of existence. One particularly intriguing idea is the concept of multiple Big Bangs, suggesting that our universe is not the result of a singular explosion, but rather part of a larger cycle of creation and destruction. Imagine, if you will, a universe that is reborn repeatedly in a never-ending cosmic cycle. If there were indeed multiple Big Bangs, it would imply that our universe is just one of many, each one potentially governed by its own set of physical laws and structures. This idea hints at the possibility of a multiverse, an infinite collection of universes, each emerging and ending in its own unique way. The implications of such a concept are profound. If our universe is just one part of a grand, interconnected cosmic story, it could forever alter how we view time and space. Rather than following a linear path, these elements might cycle through different phases, creating new universes in their wake. The existence of multiple Big Bangs could also help explain certain phenomena we observe, such as the uniformity of the cosmic background radiation and the distribution of galaxies. In this scenario, our universe might just be a temporary chapter in an endless ongoing cycle. Finally, the concept of cosmic inflation offers a crucial layer to our understanding of the Big Bang. While the Big Bang Theory alone explains how the universe began as a hot, dense point and expanded rapidly, it didn't fully account for the uniformity we observe in the large-scale structure of the universe. Inflationary theory addresses this gap by positing that the universe underwent a period of incredibly rapid expansion immediately after the Big Bang. This rapid expansion would have smoothed out any irregularities, creating the homogeneous and isotropic universe we see today. It also helps explain the tiny temperature fluctuations observed in the cosmic microwave background radiation, fluctuations that ultimately gave rise to galaxies, stars, and clusters. Quantum mechanics, which governs the behavior of particles on incredibly small scales, plays a vital role in understanding the origins of the universe. At the beginning of the Big Bang, the universe was so hot and dense that the classical laws of physics, which describe the behavior of everyday objects, broke down. In their place, the bizarre rules of quantum mechanics took over. In this strange and mysterious domain, particles could exist in multiple states at once, and randomness reigned supreme. These quantum fluctuations are believed to be the seeds of the universe's large-scale structure. Variations in density, created by these fluctuations, provided the initial conditions for the formation of galaxies, stars, and planets. Without these fluctuations, the vast and varied universe we see today would have been impossible to explain. In the end, the Big Bang Theory continues to be refined and debated, but it remains the most robust framework we have for understanding the origins and evolution of the cosmos. Whether through the discovery of new evidence, the development of alternative theories, or the exploration of deeper philosophical questions, the journey to understand the universe's beginnings is ongoing. Each new discovery brings us one step closer to answering the greatest questions humanity has ever asked. How did it all begin? What is the true nature of our universe? And where does it all lead? Quantum mechanics unveils a realm of reality that challenges our traditional understanding of the universe, suggesting that what we once thought of as empty space is anything but. Instead of being a void, the quantum vacuum is teeming with potential energy, constantly fluctuating with activity. These fluctuations, which occur on incredibly small scales, are capable of giving rise to particles seemingly out of nowhere. This phenomenon, known as quantum fluctuation, provides us with a glimpse into the underlying chaos and order of the cosmos. It's believed that these fluctuations were pivotal in the universe's early development, particularly during a crucial period known as cosmic inflation. Cosmic inflation took place in the moments just after the Big Bang, a brief but explosive period of rapid expansion. During this inflationary phase, the universe expanded at an unimaginable rate, smoothing out initial irregularities and setting the stage for the large-scale structures we observe today. It was this period that laid the groundwork for the galaxies, stars, and planets that would eventually form in the vast evolving expanse of space. Quantum mechanics thus plays a fundamental role in our understanding of the universe's origins, helping us comprehend how the very fabric of reality can shift and change under extreme conditions. Through this lens, we begin to understand how small, seemingly insignificant differences in the early universe could cascade into the vast complexity we see today. The story of the universe's origins has been imagined in countless ways by civilizations throughout history, with each culture developing its own unique narrative. These myths and beliefs reflect not only the worldviews of the societies that created them, but also the values and emotions central to their existence. In many indigenous cultures, for example, the creation of the universe is intertwined with a profound connection to nature. The Earth and the cosmos are often viewed as deeply interwoven, with legends featuring powerful beings or spirits who shaped the world. These stories emphasize the importance of balance, harmony, and respect for the Earth, portraying creation not as a singular event, but as an ongoing, harmonious process. In ancient Mesopotamia, for instance, myths spoke of a primordial chaos, a vast void from which gods emerged to impose order on the universe. The Sumerians, in particular, told stories of freshwater and saltwater mixing, giving birth to life and shaping the heavens and the earth. Such imagery captures the eternal struggle between order and chaos, mirroring humanity's own search for understanding in a world that often feels unpredictable and disordered. In contrast, Hindu cosmology views the universe not as a one-time creation, but as an endless cycle. The universe begins with a cosmic ocean where a divine being slumbers. Upon awakening, this being initiates the creation of the cosmos, and the universe expands. However, this is not a linear process, but one of constant rebirth. After each period of creation, the universe contracts, only to begin anew in an eternal cycle of birth, preservation, and destruction. This cyclical view highlights the belief that beginnings are not finite, but part of an ongoing, eternal process. The ancient Greeks, too, contributed rich philosophical insights into the nature of existence. Philosophers like Plato pondered the concept of a realm of perfect forms, which led to deep philosophical debates about the material world and the origins of everything within it. Their discussions, rooted in logic and observation, formed the bedrock of Western thought for centuries to come. Meanwhile, many indigenous African traditions emphasize the creation of the world through spoken words. A high god or divine force is said to have uttered the words that brought the world into being, highlighting the incredible power of language and communication. These creation myths are often intertwined with moral lessons, teaching about the connection between the divine and the human experience. In these traditions, creation is not merely an event in the distant past, but a continuous unfolding that links the divine with every aspect of human life. These ancient creation stories, diverse in their specifics, share a common thread. They reflect humanity's eternal quest to understand our place in the cosmos. Each civilization, rooted in its environment and shaped by its cultural context, has developed its own narrative of how the universe came into being. While scientific explanations have since provided a more precise framework for understanding the universe's origins, these rich myths continue to offer insights into the human spirit and our unyielding desire to comprehend the mysteries of existence. One of the most profound mysteries of the universe is the existence of dark matter, an elusive substance that comprises a significant portion of the cosmos, but remains hidden from direct observation. It cannot be seen, nor can it be measured with conventional tools. Picture standing in a room where you can't see anything clearly, yet you feel the presence of something substantial. You know it's there because you can sense its gravitational pull, but you can't interact with it in the same way you would with ordinary objects. This is the essence of dark matter. We can't see it directly, but we can feel its effects through its gravitational influence on the visible matter around it. Current scientific understanding suggests that about 26% of the universe is made up of dark matter. The term dark refers to the fact that it neither emits, absorbs, nor reflects light, making it invisible to our telescopes. Instead, its presence is inferred by observing the gravitational forces it exerts on visible objects, such as stars and galaxies. For instance, when we study the movement of galaxies, we find that they spin much faster than would be expected based on the visible matter alone. It's as if an invisible force is at work, exerting extra gravitational pull to keep everything in place. Without dark matter, the structure of galaxies would likely be unstable, and the universe as we know it might look very different. Dark matter also plays a key role in shaping the large-scale structure of the cosmos. It provides a kind of invisible scaffolding around which visible matter gathers, influencing how galaxies form and cluster together. In this way, dark matter is essential to the universe's expansion, shaping the fabric of the cosmos on the grandest scales. Despite being invisible, dark matter's presence is revealed through its gravitational effects, offering tantalizing clues to scientists who continue to explore its nature. Detecting dark matter is no easy feat, though, because it doesn't emit any form of electromagnetic radiation. This makes it completely undetectable by traditional telescopes. However, scientists have developed ingenious methods to study dark matter, primarily through its gravitational influence on visible matter. One of the key techniques used to study dark matter is gravitational lensing. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, the gravitational field of that object bends the path of the light. This bending of light can create distorted or magnified images of the distant galaxy. By carefully studying these distortions, scientists can infer the presence and quantity of dark matter in the intervening mass, even though the dark matter itself remains invisible. This method allows us to glimpse the invisible structures that hold the universe together, hinting at the profound influence of dark matter in shaping the cosmos as we know it. Scientists are currently embarking on groundbreaking experiments deep underground, armed with highly specialized detectors engineered to capture the faintest interactions that dark matter might have with regular matter. These detectors, nestled in the Earth's crust, to shield them from the constant barrage of cosmic rays and other forms of background interference, are designed to maximize the likelihood of detecting extremely weak signals. These signals, should they exist, would be caused by dark matter particles colliding with the atoms around them. While dark matter itself cannot be observed directly, its presence is inferred from the extraordinary effects it has on the structure and behavior of the universe. In essence, it serves as an invisible force that shapes the very cosmos we observe, acting as a critical component in the ongoing unraveling of some of the most profound cosmic mysteries. Should dark matter be proven not to exist, it would force a monumental shift in our understanding of the universe. Dark matter was conceived as a theoretical construct to explain a wide range of unexplained phenomena, such as the way galaxies spin and the gravitational effects we observe in galaxy clusters. It operates as an unseen glue, subtly holding galaxies together despite not emitting any detectable light or radiation. If this theory is proven false, researchers would be faced with the daunting task of rethinking the fundamental laws of physics as they apply to cosmic structures. The current models used to explain how galaxies form and behave might need to be drastically reworked, as these models are built on the assumption that dark matter exists, providing the missing mass that explains the gravitational effects we see in the universe. Without dark matter, scientists would have to entertain alternative explanations for these phenomena, possibly turning to modified gravity theories. These theories propose changes to the currently accepted laws of motion and gravitation, suggesting that our current understanding of physics may be incomplete. Such a shift in thinking could spark a flurry of new experiments and theoretical models, leading to fresh avenues of exploration in astrophysics. It could even push the boundaries of what we know, leading to new paradigms in our understanding of the cosmos. The implications of disproving dark matter would reach far beyond the realm of theoretical physics. It would profoundly reshape our understanding of the very composition and history of the universe. Such a discovery could set in motion a series of investigations into the nature of cosmic forces, urging scientists to explore new dimensions of reality that we have yet to comprehend. If dark matter were to be ruled out, it would open a Pandora's box of unanswered questions, driving us deeper into the quest for fundamental truths about the universe's origins, structure, and ultimate fate. To fully appreciate the magnitude of this scientific pursuit, it's essential to distinguish between two distinct and mysterious forces: dark matter and dark energy. Although both play pivotal roles in the universe, they serve very different purposes. Dark matter is often described as a hidden form of mass that neither emits light nor energy, making it invisible to conventional telescopes. Despite its invisibility, dark matter's gravitational influence is undeniable. It acts as a cosmic adhesive, holding galaxies and galaxy clusters together, providing the stability necessary for these cosmic structures to form and persist. Imagine a group of dancers moving on a stage. The dancers themselves are the galaxies, and dark matter is the invisible force that keeps them in their proper positions, preventing them from drifting apart. This gravitational pull is essential for the formation of galaxies and the large-scale structures that populate the universe. However, while dark matter binds these structures together, dark energy operates in an entirely different manner. Dark energy is the mysterious force responsible for the accelerated expansion of the universe. To conceptualize dark energy's role, think of a balloon being inflated. As air is pumped into the balloon, its surface stretches, and the points on the surface move further apart. Similarly, as the universe expands, galaxies are moving away from one another. But here's where dark energy comes into play. It's the force driving this expansion, pushing galaxies away from each other at an ever-increasing rate. This is in stark contrast to the traditional role of gravity, which tends to pull things together. While dark matter works as a kind of cosmic glue, dark energy acts as an anti-gravity force, propelling the universe toward faster expansion. Understanding the behavior of both dark matter and dark energy is critical for unraveling the secrets of the cosmos. These two forces are integral to the structure, behavior, and ultimate fate of everything we observe in the universe. Dark energy, in particular, remains one of the greatest enigmas in cosmology. It has a profound impact on our understanding of the universe's expansion and its long-term destiny. Initially, one might think that the expansion of the universe would slow down over time as gravity works to pull everything back together. This would be analogous to a hand pressing down on a balloon, resisting the outward force. But rather than slowing, the universe's expansion is actually accelerating. This surprising discovery pointed to the existence of a force we call dark energy, which works against the pull of gravity. Despite accounting for roughly 70% of the universe's total energy, dark energy remains largely invisible and elusive. Scientists have never directly observed dark energy. Rather, its existence is inferred from its effects on galaxies and cosmic structures. For example, dark energy is thought to be responsible for the accelerating rate at which galaxies are moving away from each other. This realization has led cosmologists to consider a variety of theories about what dark energy is and how it works. Some of the most intriguing theories propose that dark energy might be related to the vacuum of space itself, or perhaps represents a form of energy inherent in empty space. Other theories suggest that dark energy might even point to entirely new physics beyond the established framework of general relativity. This ongoing mystery continues to captivate scientists, philosophers, and anyone with a curiosity about the cosmos, sparking debates and furthering the exploration of the deepest questions of existence. As we seek to understand the nature of dark energy, we are pushed to expand the boundaries of our knowledge and rethink our assumptions about the universe. This quest is far from over. The implications of dark energy's discovery could shape not just our understanding of the cosmos, but the very nature of reality itself. And while much remains unknown, each step forward in this scientific journey brings us closer to unraveling the greatest mysteries of the universe, from the formation of galaxies to the ultimate fate of everything that exists. Thus, the interplay between dark matter and dark energy is at the heart of some of the most pressing questions in modern science. Dark matter keeps the universe's structures intact, while dark energy is driving its expansion. Together, these forces form a cosmic dance, one that we are only beginning to understand. The search for dark matter and dark energy is a quest that promises to reveal new truths about the universe, potentially reshaping our worldview in ways we can scarcely imagine. Around the halfway point of the universe's existence, something profoundly transformative occurred. A mysterious force, one that we have come to call dark energy, began to dominate the landscape of the cosmos. Though no one fully understands its nature, dark energy acts in opposition to gravity. While gravity pulls matter together, dark energy pushes it apart. The exact mechanisms remain elusive, but what is clear is that it has a significant and accelerating effect on the expansion of the universe. In fact, this strange force causes the universe to expand at an ever-increasing rate. This acceleration marks a stark contrast to what one might expect. Rather than slowing down over time due to gravity's tug, the universe is speeding up, propelled by a hidden energy that continues to baffle scientists. Understanding dark energy has thus become one of the most critical challenges in cosmology today. It holds the key to the ultimate fate of the universe, suggesting a cosmos that will stretch out endlessly, growing faster and farther into the vast unknown. Researchers have developed a range of methods to study dark energy and its profound effects on the universe's expansion. One primary technique involves observing distant supernovae, the explosive deaths of massive stars. These cosmic events are not only spectacular in their brightness, but also serve as powerful markers for measuring distance. By examining how these supernovae appear from Earth, how their light shifts, and how fast they seem to recede, scientists can infer how the universe has expanded over time, revealing the invisible influence of dark energy. Another tool used to study this enigmatic force comes from large-scale galaxy surveys. These surveys map the distribution of galaxies across the universe, offering a snapshot of the vast cosmic web. By tracking how galaxies cluster and move apart, researchers can begin to understand the impact of dark energy on galactic formation and evolution. This cosmic dance provides essential clues as to how dark energy shapes the universe on a grand scale, guiding galaxies into their current arrangement. The cosmic microwave background radiation, CMB, is also a crucial piece of the puzzle. The CMB represents the faint afterglow of the Big Bang, a relic from the very birth of the universe. By studying minute fluctuations in this radiation, scientists can reconstruct the early moments of the cosmos and look for signs of dark energy's influence in those first formative years. These fluctuations tell the story of a young universe where the effects of dark energy could have played a pivotal role in shaping its early structure. Gravitational waves, ripples in the fabric of space-time caused by massive cosmic events, offer another route for investigation. These waves travel across the universe, carrying with them information about some of the most extreme phenomena, such as colliding black holes or supernovae. By detecting these waves, scientists hope to gather further insights into the role dark energy plays in the universe's ongoing expansion. Perhaps most remarkably, computer simulations now allow researchers to recreate the universe's expansion under various conditions. These simulations model the universe's growth and evolution, providing a test bed for different theories of dark energy. By running these simulations, scientists can compare their models with real observations and refine their understanding of how this invisible force operates across the cosmos. Through these combined efforts, researchers are gradually piecing together the puzzle of dark energy. Each new discovery brings us closer to understanding this mysterious force and its role in shaping the universe. But unraveling the true nature of dark energy and its relationship with dark matter could revolutionize our understanding of the cosmos. Dark matter, despite comprising a significant portion of the universe, remains invisible to our senses. We cannot detect it directly, but we know of its existence because of how it influences the matter around it. Acting like an invisible glue, dark matter holds galaxies together, helping to govern their motion through its gravitational pull. If scientists could identify what dark matter is, it would shed light on the very structure of the universe, revealing how galaxies came to be and how they have evolved over the course of billions of years. Dark energy, on the other hand, is even more elusive. It is the driving force behind the universe's accelerated expansion, pushing galaxies apart at an ever-increasing rate. Understanding dark energy could answer some of the most profound questions about the fate of the universe. Will the cosmos continue to expand forever, or is there a possibility of a future where the expansion reverses? What happens when these two forces, dark matter and dark energy, interact? These are the questions that, if answered, could challenge our current understanding of physics and redefine our place in the universe. These discoveries could also lead to breakthroughs in both cosmology and particle physics. New theories may emerge, potentially unifying gravity, quantum mechanics, and the fundamental forces of nature in ways we can scarcely imagine. The ultimate goal would be to develop a framework for understanding the universe, one that incorporates dark matter and dark energy and redefines the very nature of existence. One of the most dramatic manifestations of the universe's complexities lies in the formation of black holes. These are regions of space where gravitational forces are so intense that nothing, not even light, can escape their pull. To understand how black holes form, we must first look at the life cycle of massive stars. These stars are born from clouds of gas and dust, which collapse under their own gravity. Over the course of their lifetimes, stars engage in nuclear fusion, converting hydrogen into helium and releasing energy that counters the inward pull of gravity. This balance keeps the star stable, preventing it from collapsing in on itself. However, when a massive star exhausts its nuclear fuel, it can no longer maintain this equilibrium. Without the outward pressure generated by fusion, the core collapses under the weight of its own gravity. This collapse results in a catastrophic explosion, a supernova. The outer layers of the star are ejected into space while the core remains behind. If the remaining core has a mass greater than a certain threshold, several times the mass of our Sun, it will continue to collapse, eventually forming a singularity, a point of infinite density. This singularity is surrounded by the event horizon, the boundary beyond which nothing can escape, not even light. Black holes can also form through other processes, such as when neutron stars collide or when vast amounts of dust accumulate in a region of space, compressing under gravity. Once formed, black holes can grow even larger by merging with other black holes or by accumulating matter from their surroundings, becoming more massive with time. Black holes epitomize some of the most extraordinary consequences of stellar evolution. They also highlight the complexities of gravity, presenting challenges to our understanding of physics. They exist at the intersection of two fundamental theories, general relativity and quantum mechanics. General relativity, formulated by Albert Einstein, explains how gravity works on a grand scale, describing how massive objects like stars and planets warp space-time and create gravitational fields. According to this theory, the immense gravity of a black hole distorts space-time so severely that nothing can escape. Yet, when we turn to quantum mechanics, the story becomes more complicated. Quantum mechanics governs the behavior of particles on the tiniest scales, where the laws of physics operate differently than at larger scales. The clash between these two frameworks, the smooth curvature of space-time predicted by general relativity and the uncertainty of quantum mechanics, creates a paradox at the black hole's core. Here, gravity is so intense that space-time itself breaks down, and the laws of physics cease to make sense. This conundrum raises fundamental questions about the nature of reality. What happens to matter and information when it crosses the event horizon of a black hole? What lies at the singularity's heart? These questions remain unanswered, but they highlight just how much we still have to learn about the universe and the strange, paradoxical forces that govern it. Black holes, enigmatic and profound, pose one of the most captivating challenges to our understanding of the universe. These dense regions in space, with gravity so powerful that not even light can escape, stir up profound questions that extend far beyond their immediate existence. At the heart of this dilemma is a fundamental conflict between two major theories of physics: quantum mechanics, which governs the behavior of the microscopic world, and general relativity, which explains the forces at play on a cosmic scale. Scientists are actively exploring ways to bridge this gap, with promising new theories emerging, such as quantum gravity, which aim to unify these two realms of physics. The exploration of black holes, in this sense, serves as a testing ground for the most extreme conditions in the universe, and by studying them, we inch closer to a more complete understanding of the universe's most elusive laws, laws that could one day reveal new dimensions of reality itself. The event horizon, a term synonymous with black holes, represents the boundary beyond which no return is possible. This invisible line in space marks the point at which the gravitational pull of a black hole becomes so overwhelming that nothing can escape, not even light itself. Imagine standing at the edge of a cliff. Once you fall past the point of no return, climbing back up becomes impossible. The event horizon acts similarly. As an object approaches it, time itself seems to stretch, as though the object is frozen in space, unable to move forward or backward. For an external observer, it appears as if the object is slowly being stretched and slowed as it gets closer to the event horizon, creating an illusion that time is standing still for the object, even as it disappears from view. This phenomenon illustrates the powerful and bizarre effects of gravity on time and space, an idea rooted in Einstein's theory of general relativity. The event horizon's significance goes beyond just a boundary in space. It plays a central role in the study of black holes, linking it to the deeper questions of the nature of information and the very structure of the universe. If something crosses the event horizon, does it lose all the information it contains, or is that information somehow preserved in a different form? This question has prompted numerous debates within the scientific community, with some proposing that the information might be preserved, perhaps encoded, in a form we don't understand, maybe even on the event horizon itself. Furthermore, the event horizon forces us to reconsider our ideas about space, time, and the fabric of reality itself. It has become a focal point in the ongoing search for a unified theory that could reconcile quantum mechanics with general relativity, helping us to answer the most profound questions about the universe's workings. As we continue to study black holes, we are not just learning about the forces that govern the cosmos, but are also gaining insight into the potential existence of new laws of physics, laws that could reshape our understanding of time, space, and perhaps even the very nature of existence itself. The study of black holes offers us a unique glimpse into the unknown. These objects, often referred to as cosmic laboratories, are some of the most extreme environments in the universe. The gravitational forces within a black hole are so powerful that they challenge our current understanding of physics, offering a rare opportunity to push the boundaries of our knowledge. For example, black holes can help scientists test the limits of gravitational theories and the behavior of space-time in ways that would be impossible under more normal conditions. A black hole's influence extends far beyond the region immediately surrounding it. As matter falls into a black hole, it heats up and emits a tremendous amount of radiation. This release of energy, often in the form of X-rays, helps scientists measure the black hole's mass, size, and spin, giving us valuable data about the forces at work in these powerful objects. The accretion disks, which are made up of gas and dust swirling around black holes, also offer insight into the dynamics of galaxies. As matter spirals inward, it generates high-energy radiation, which can be observed by telescopes, providing a direct way to study these cosmic giants. But black holes are more than just powerful gravitational wells. They are integral to the functioning of galaxies themselves. Most galaxies, including our own Milky Way, harbor a supermassive black hole at their centers. These supermassive black holes can be millions or even billions of times the mass of the Sun. Their gravitational pull influences the stars, gas, and dust that make up their host galaxies, shaping their structure and guiding their evolution. A supermassive black hole's activity can have far-reaching effects on the entire galaxy, influencing the formation of new stars and the dynamics of existing ones. Moreover, when black holes collide, they produce gravitational waves, ripples in the fabric of space-time that travel across the universe. These waves offer a new way of studying black holes, revealing phenomena that are invisible through traditional observation methods. The detection of gravitational waves has opened an entirely new field of astronomy, allowing scientists to observe events that were previously undetectable, like the collision of two black holes or the merging of supermassive black holes in distant galaxies. Despite their apparent inaccessibility, black holes provide clues about some of the most significant unanswered questions in modern physics, including the nature of dark matter and dark energy, two mysterious forces that make up most of the universe. By studying how black holes interact with their surroundings, scientists can glean information about these unseen forces that influence the universe's expansion and structure. In this way, black holes serve as key players in the cosmic drama, helping us unlock the secrets of the universe's origins, structure, and ultimate fate. At the heart of every black hole lies a singularity, a point where gravity is so intense that space and time collapse in on themselves. This point represents the ultimate extreme of our universe, where current theories of physics, particularly general relativity, break down. According to general relativity, the gravitational pull inside a black hole becomes infinitely strong, and the curvature of space-time becomes infinite as well, creating a singularity that seems beyond comprehension. Yet, the singularity is not just a theoretical curiosity. It presents a real puzzle that challenges our fundamental understanding of the universe. While general relativity works well on a cosmic scale, it cannot explain the behavior of matter at the quantum level, especially under the extreme conditions found in black holes. This gap in our understanding has prompted physicists to search for a unified theory, a theory of everything, that could explain both the immense forces of gravity and the delicate probabilistic nature of quantum mechanics. The quest to understand what happens at the singularity lies at the heart of one of the greatest scientific challenges of our time. Moreover, singularities raise another fascinating question. What happens to information when it falls into a black hole? If information is lost inside a black hole, as it seems to be, then quantum mechanics would be violated. On the other hand, if the information is preserved in some way, it could fundamentally alter our understanding of how the universe works. Some scientists speculate that this information may be encoded in a way we don't yet comprehend, perhaps stored in the event horizon itself. However, no definitive answers have been found, and the debate continues to evolve. Black holes are not only pivotal to our understanding of astrophysics, they are also essential to understanding the dynamics of galaxies. There are two primary types of black holes: stellar black holes, which form from the collapse of massive stars, and supermassive black holes, which reside at the centers of most galaxies. The presence of these supermassive black holes has a profound impact on the evolution of galaxies. Their enormous gravitational pull affects everything from the movement of stars to the formation of new galaxies. When two galaxies collide, their supermassive black holes may eventually merge, forming an even larger black hole. This process, known as a black hole merger, produces gravitational waves that ripple across the universe, allowing scientists to observe and study these catastrophic events from vast distances. These mergers can also affect the rate of star formation within their host galaxies, either accelerating or slowing it depending on the black hole's activity. Despite their invisibility, black holes have become central to our understanding of cosmic evolution. Their presence influences the structure and growth of galaxies, and their mysterious nature continues to push the boundaries of human knowledge. Thanks to advancements in technology, we are now able to observe black holes more directly than ever before. Telescopes that observe different wavelengths of light, such as radio and infrared, allow us to peer through cosmic dust and uncover the secrets of black holes. For example, the Event Horizon Telescope's groundbreaking 2019 image of a black hole's shadow in the distant galaxy M87 was a monumental achievement in black hole research. This image provided the first direct visual evidence of a black hole's existence, confirming many theoretical predictions and offering a glimpse into one of the universe's greatest mysteries. Moreover, the ability to study the movements of stars around black holes has further enhanced our understanding of these cosmic entities. By tracking the orbits of nearby stars, scientists can infer the mass, size, and spin of the black hole. These observations provide crucial data about the properties of black holes, helping to refine our models and deepen our knowledge of these enigmatic objects. As technology continues to evolve, so too does our ability to study black holes. From cutting-edge telescopes to advanced computational models, we are now able to simulate and observe black hole interactions in unprecedented detail. These advancements have opened new doors to understanding the most fundamental aspects of the universe, from the nature of gravity to the very structure of space and time. Machine learning algorithms, in particular, are playing an increasing role in analyzing vast amounts of astronomical data, helping scientists detect and study black holes with greater efficiency than ever before. With each breakthrough, we are peeling back the layers of mystery surrounding black holes, and with it, gaining a deeper understanding of the forces that shape the universe. Through all of this, one thing is clear: black holes are not just fascinating objects of study, they are key to unlocking the deepest secrets of the cosmos.